Hey guys, welcome to the section 4, session number 17. So let's understand about the minimum cost spanning tree over there. So we are going to understand about what is the minimum cost spanning tree and why it is being used over there. Okay, so basically what is meant by minimum cost spanning tree? Before that, we'll understand what is spanning tree, right? The spanning tree is basically again a DSA concept that's basically a kind of a subgraphs. Okay, we are going to call it as a subgraphs. So where that both trees are connected with no cycles. Okay, a spanning tree is something, a graph that is connected, but it is not forming any kind of a cycle over there. Okay, and spans of all the vertices of the original graph, which means it includes every vertex in the original graph. If we take this example 1 2 3 4 5, okay, it is a kind of a cyclic graph and it is having the connection between some nodes, or it might be there or it might be not there, but at least there is a single, at least one connection, right? And it is forming a cycle. You can see 1 2 3 is forming a cycle, and 2 3 5 is another forming a cycle, and entirely thing it is forming a cycle. But the spanning tree is a kind of a spanning tree that should not form the specific cycle over there. That should not form a specific cycle. Okay, but all the vertices should be there. So all the vertices should be present. That should be at least either one, it should be get connected, but there should be no cycle over there. Okay, we'll understand with an example. So the characteristics of it, the connectivity, acyclic and minimal edges here. These are the three main characteristics of the spanning tree. A spanning tree connects all the vertices. As I said, it is going to connect with all the vertices in the original graph. That ensures there is a path between any two connections. That is, there is a path between any two vertices. At least there should be one path between any two vertices. But that should not form the specific cycle. So we are telling us it is acyclic. It means a spanning tree is acyclic, meaning there is no closed loops. They should not form any kind of a loop or a cycle. Okay, that's property is the spanning tree. And there will be minimal edges here. The minimal edges in the tell when there is a spanning tree contains the minimal possible number of edges required to span all the vertices. In other words, it has a least number of edges needed to maintain the connectivity. So this will, the last point you are not going to understand directly with the theoretical part. We'll understand with the specific problem here. Okay, so for right now you understand there will be a tree, there should be no forming a cycle, but all the vertices should be connected, at least one edge should be there, and there can be n possible specifics, n possible probabilities for the getting a graph. If I give you one graph, you can give me 10 graphs. So in specific 10 graphs which is having the minimum cost, that is going to be the minimum cost spanning tree. Okay, so let's understand with the algorithms, and we'll understand with the different types of spanning trees here. The major three very important specific spanning tree that's going to find the minimum cost is, first one is the prims, second one is the Kruskal's, third one is the Dijkstra algorithm. So we are going to see one by one with the sessions, and we are going to write a Java program for it. But right now we are going to first understand the spanning tree example over there. Okay, let's look with this specific example. Let's come back to our writing pad. So I'm just going to open the specific minimum cost spanning tree here, right? So as I said, the spanning tree, let's this definition of the specific spanning tree. What is the specific definition of the spanning tree here? It means it has all the vertices. I'm just going to tell all vertices. It is going to all having the all the vertices V, and it is going to be the n-1 edges. Okay, this is going to be the definition of spanning tree, and no cycle should be there. No cycle should be there. Okay, and it should be the minimum edges. I'm just going to tell minimum edges. So these are all the major three properties of the specific spanning tree. This is going to call it as a spanning tree. A spanning tree. Okay, if you include this minimum edge, it is going to be the minimum cost spanning tree. So let's take an example over here. Let's write an example. We have an edge 1 here, we'll be having a 2, again we are having a 3, 4, again 5, and we are having a 6 over here. Let's write the normal specific here. Okay, so here if we just tell the specific, if I just try to write the what is the vertices, let's write it for the spanning tree. I'm just going to tell vertices are 1 2 3 4 and 5 comma 6. These are all the vertices. If I try to write the edges for it, the edges are very simple. If I just start from the 1, it can be 1 to 2, again it is going to be 2 to 3. Okay, again if I try to tell as a 3 to 4, again I'm going to tell as a 4 to 5. Okay, again I can just tell here as a specifically 5 to 6, right? 4 to 5 and 5 to 6. So these are all the going to be your, this is going to be your spanning tree. This is going to be your spanning tree over here. So what I mean that it mean you can see 1, 2, 3, 4, 5, 6. We are having a specific vertex is equals to 6. How many edges I can form? 1, 2, 3, 4, 5. I can just form the specific 5 edges. So I can say this is going to be the 6C5. This is going to be the 6 combinations for this vertex. This is going to be the 6C5 is the major combination for the spanning tree. If you are having a 6 vertex, there will be the 5 edges for it. Okay, that is what about the spanning tree. Now, how many spanning tree I can form to it? I can form a number of forming tree. Let's take an example over here. Okay, let's say here as we have 1, 2, 3, 4, 5 and 6 over here. Let's try to form one spanning tree. So I can just tell this is going to be one specific forming tree. I'm going to tell if I just start with 1. Let's start with 1, 1 to 2 will be having. So I can just tell like this, right? I can just tell here like, okay, it is not giving me this right line. So I can just give it like this. If I just tell here as like this, it is going to be the one specific forming tree. I wanted to maintain a very neat scenario because we are maintaining neat things, right? Let's try to use these specific shapes over there. Okay, let's try to use this specific like this. Okay, then this, let's try to add this one. So we have this can be one spanning tree. This can be one spanning tree, right? Again, I can just tell this is going to connect with this. This is going to be another spanning tree, and from 3 to 4 it can be a spanning tree. Again 4 to 5, again 5 to 6. You can see now it is this one spanning tree because it is not forming any kind of a cycle over there. It is not forming any kind of a cycle over there, right? That can be the specific one spanning tree. Again, if I just tell here as 1, 2, 3, again 4. So I'm going to give it as this is going to be 4 here, and it is going to be 5. Again, it is going to be 6 over there. Okay. So if I just talk about here, so this is the one spanning tree. So here I'm just going to tell this is the one spanning tree. That is going to be here. This is going to be one spanning tree, and this is going to be one spanning tree, and this is going to connection with from here to here, and connection between here to here, and a connection between here to here. So this is going to be another specific spanning tree over there. Okay. So again, I can just tell here this can be another spanning tree. 1, 2, 3, 4, 5 and 6 over here. So in this case, if I start with 3, so 3 to 4 is a connection. Again, I'm just going to tell there is a 3 to 4 there is a connection, 4 to 5 there is a connection, 5 to 6 there is a connection. Again, from here to here there is a connection. Again, we'll be having a connection between 1 to 2. This is another specific spanning tree for you. Okay. Again, if I just try to tell here as 1, 2, 3, again 4, 5, 6. Now I'm going to start with the specifically we have started previously with the through to the right. Now we are going to start with the 4 over there. So if I just start with the 4 to 5 connection, this is one connection here, and there can be this connection. This is going to be a connection. This is going to be another spanning tree, and the last combination according to this specific graph is going to be like this. If I just start from 5 to 6, it is going to be 1. Again 6 to 1 will be there. Again 2 to 1, here to here, here to here. Okay, this is also one kind of a spanning tree. So this is all about the spanning trees. Okay. These are all the possible combinations of the spanning tree for a given input, for a given specific graph over here. Okay. So again, we are going to find the what is the minimum cost, right? So this is basically just about the spanning tree, right? Let's take an example for another one. So let's imagine we are having a minimum cost spanning tree here. So let's take this specific example. So in this specific minimum cost spanning tree, let's have another example. Like let me create one vertices values here. Like okay, so let's try to add one specific thing. Like this basically is going to be a weighted graph. Okay, this is basically a weighted graph. So I'm going to tell here there is a 1, and there will be the 2 here, and there will be specific 4, and here we are having this specific node 3, 1, 2, 3, 4 node. So let's try to give a node cost is 1 to 2 cost is 5, and this is 2, and this is going to be here as a 3, and this is going to be here as a 4, and this is going to be here as a 6 over there. Okay, so this is going to be your weighted graph. So this is going to be your weighted graph, right? So for the weighted graph, now I wanted to create one specific spanning tree. As I said, right? So once minimum cost spanning tree means there should be no cycle. You can see this is one specific cycle. So now what I am going to do here is I'm just going to add the one specific cycle to it. So I'm just going to tell here, I'm just going to select this stroke razor here. So now what I want to do here. So I wanted to get like this. So if I remove this, at that case also this will be one cycle. If I remove this specific one, this middle one, it is causing the cycle, right? So first I'm just going to remove the middle element over here. I'm just going to remove the minimum edge. So again, still there is a cycle now. So what I'll do here is I wanted to 1, 2, 3, 4 over here. I wanted 1, 2, 3 and 4. So I'm just going to remove this one. So this is the one specific spanning tree, right? So again, here also again, I'm just going to come here. So in this case, I'm just going to remove this cycle. So I'm going to tell 2, 1, 4, 2 is the one another specific spanning tree, right? So I'm just going to remove the edges between one here. So again here what I'm going to do, here again I'm just going to tell here as this is the right side is done. Again I'm just created one more, so I can just tell here the 1 2 3. I can just create like this 1 2 3. In this case I'm going to remove this cycle, still it is forming a cycle. I'm going to remove this one. This can be another specific spanning tree. Again, so I can have a n here, right? So I can just tell here as a z. I can have this specific z also. So I'm going to remove. This is the another one. I'm going to remove it. So again, what else I can have? So what else I can have this specific spanning tree? So this is basically 1 2 3 4 spanning tree we created, right? So 1 2 3 4 4 edges, 4 C 3 should be there, right? So this can be the specific another spanning tree. So let's try to have another. So we can have like this. Okay, we created like this. We created from here. And if I just tell here 1 2 3, so already we have, right? So if I remove this 2, let me remove, let's keep this one. If I remove from here to here, there can be z, already it is there. Again if I just have it like this, it is also already there when I remove this. Again if I try to remove, this one is there. So if I try to remove, this is there, like this we don't have. So this can be one spanning tree, right? Yeah, this is also can be spanning tree. Again I can have u also, right? I can have one more thing called as a u. I can have something called as a u also, like this. I can have like this as well, right? So this can be also one specific spanning tree. So I'm just going to specifically control C, control V. Okay, so I'm going to paste this again, another thing. So let me select again, it got mismatched. So let me control C, control V. Okay, so like this we are having it. So in this case I'm just going to remove this one, this specific thing I'm just going to remove along with that, but I'm just going to give the one specific line to it. So I can just write the specific line, like I'm just going to tell this can be also another spanning tree, right? This is also a spanning tree which is not forming any cycle now. Okay, so now let's say what is the minimum cost of it. Okay, so we have created all the spanning tree for it. So let's try to add the values to it. So I'm going to tell here as a 1 2 3 4 here. What is the cost? Here we are having a 5, and here we are having a 3, and we are having a 6 here. So again I'm going to tell here as a 1 2 4 3. What is the cost here? 5 is the cost here, the 4 is the specific cost here, 6 is the specific cost. Again I'm going to tell 1 4 2 3. What is the cost is 2 here, and it's going to be 4, and it's going to be 3 here. So let me take another example here. So we are having a 1 2 4 3. If we take this z here, so this is going to be 5, this is going to be the cost 2, and it's going to be the cost 6 here. Let me take this one, 1 2 3 and 4. The cost here is 4 here, the cost here is 5, here the cost is 3. So let me take again 1 2 3 and 4. So here what is the cost? 4 6 and 3. So now let's try to do the sum of it. Let's try to do the specific sum of it. Okay, so if I try to do the specific sum of it, so for the specific sum for this one, if we say what is the specific cost of it, what is the cost? 5 plus 3 is 9, 8 plus 6 is 14, right? This is going to be the cost is equals to 14 here. The cost is 14. So what is the cost of this one? So 5 plus 4 is 9, 9 plus 4 is 15. Cost is equals to 15 over here. So if I just tell here as a what is the cost of this? 4 to 6, 6 plus 3 is cost is 9. If I tell what is the cost of this? The cost is 5 plus 2 7, 7 plus 6 is 13. Okay, this is the cost is going to be 13. So what is the cost of this? 9 plus 3 is, again the cost is going to be 12 over here. So what is the cost of this? The cost of is 4 plus 6, 10, 10 plus 3 is 13 over here. So in this, which is the specific minimum one? So which is the minimum one? This specific cost 9 is going to be the minimum. So this is going to be your minimum cost spanning tree. This is going to be your minimum cost spanning tree. Okay, this is going to be the minimum cost spanning tree. I hope you have understood this, right? So whatever the connections we have, we'll be getting n number of solutions for. We'll be getting n probabilities, right? N combinations for it. So in that, which is the minimum cost I can traverse all the nodes. So you can see in this specific graph, every node is connected. You can see in all this spanning tree, every node is connected and there is not forming any kind of a cycle. This is the major two things. So when I talk about the minimum cost spanning tree, the minimum value should be, so to traverse all the node, there should be the minimum cost over here. You can say I can traverse, if I start with 1, 4, 3, 2, I am starting it. This is the minimum cost where I can traverse all the nodes here. I can traverse all the nodes. This is the minimum cost. I hope you understood what is the minimum cost spanning tree. So in the next coming sessions, we are going to start with the algorithm. So there we are going to understand with the Java program over there. Take care. Bye-bye. Hey guys, welcome to the section 4, session number 18.1. So let's discuss the greedy algorithm. So we have seen about the graphs and we saw how the representation graphs is going to work. So now we are going to work for the greedy methods to find the minimum cost spanning tree. So as we discussed, there are 2-3 methods like Prim's algorithm is there, Kruskal's is there, and Dijkstra is there, and Bellman-Ford is there, so and so on. So we are going to see one by one in depth. So first let's begin with the Prim's algorithm over there. So what is Prim's algorithm over here? So in the Prim's algorithm, we are going to find the specific minimum cost spanning tree of a connected undirected graphs. The minimum spanning tree of the graph is subgraphs, you know, right? So that include all the vertices of the original path basically. So now what we are going to do here is, in this specific thing, first we are going to find the which is the specific minimum edge. Okay, then we are going to start connecting the specific graphs so that it is not going to form the specific cycle. Okay, it has been developed by the computer science scientist, that is a Robert C. Prims over there. That's why they have named it as a Prims algorithm. So let's talk about the algorithm, how it is going to work. So basically we are going to start with the arbitrary node vertex as initial minimum spanning tree. This can be any vertex of the graph. Okay, as we are finding the as we are going to start from the minimum edge, right? So which is having the minimum edge cost, we are going to choose that. We are not going to choose with the vertex. Okay, it can be any kind of a vertex we can start with. Then we are going to create a set of vertices majorly and initially empty, which will represent the virtual vertices, basically all the vertices. So here we are going to create a set of edges as initially empty, which will represent the edges of the MST. So there will be the edges and there will be the vertices as we are going to discuss. So basically we are going to run one while, like since the set of vertices which is not given to the not equal to the vertices of the graph. So we are going to connect the specific vertices one by one. So such that the specific edges are minimum, having the specific minimum weight over there. Okay, then we are going to connect it. So while connecting, if it's forming this specific cycle, then we are going to just ignore that specific vertex. Okay, so this is how this specific things is going to there. So let's discuss a better way with the specific example. So coming back to the pad over there, so let's discuss how it is going to be there. Okay, so in this specific example, I'm just going to initialize with some kind of a values over there. Okay, so I'm just going to say some values here. So let's take it, this is going to, let's name the vertex as a 1 here. Let's make it here as a 2. This I'm going to make it as a vertex 3, vertex 7, and vertex 4 here, vertex 5, and a vertex specific 6 over there. So let's give some weightage for it. So let's give as 1 2 6, we are having a 10 here, and this is 28. It is basically an undirected graph, right? So whatever we have drawn, that is an undirected graph. So I'm just going to tell this is going to be the weight 14, and I'm just going to tell this is going to be a 16 here, and I'm just going to tell here the weight is 12, and I can just tell here the weight is 18, here the weight is 22. So then what else? Here I'm going to give the weight here is 25 over there. Let's make it here as a 24 over there. Okay, so this is the specific this is the specific graph, and with the specific weightages over there. So here the first point to be noted. So I'm just going to write specifically select the specific minimum cost edge. I'm going to select the specific minimum cost edge. So this is the first point. Okay, first always connect the specific one edge to the another edge over there. So let's imagine from this specific entire graph, so which is having the specific minimum cost over there. So the minimum cost here is 10, right? The specific minimum cost is 10 for the vertex 1 to 6. So I'm just going to select these two vertices with the specific edge over there. Okay, I'm just going to tell it here. I'm just going to tell here as a 1. So I'm just going to tell here as this specific 6 over there. So this is going to be the minimum cost. Okay, so if I just draw the specific straight line over here, you can see this kind of a magic, right? I really like this. When I put it around, it's just getting with the very neat way. Okay? I hope it works for everything. Okay, so now I'm just going to mark it. This is going to be your first step over there. Okay, this is going to be your first step. Okay, this is having the minimum cost. So then this is completed. I'm just going to mark. Okay, this has been completed. So the next minimum, what is the next minimum cost from this specific thing? So if I take it here as a next minimum cost here is a 12, right? So 12 is the next minimum cost that is having the vertex 3 and 4. So this is going to be your step 1. Okay, you can do it like step 1, step 2, step 3, keep on doing like that. But what I'm doing, I'm going to do it into a single way, in the single iteration itself, in the specific single graph itself. Okay, 1 6 has been done. So I'm just going to write it here next to the minimum cost here is 12 over there. So I'm just going to write it here. Let me write it here as a 3 here. Okay, this is going to be your 3, and next I'm just going to tell here as a 4 over here. So this is going to be the next specific graph. So this is going to tell as a 4 here. This is going to be the 3. So I'm just going to tell here this is going to be 3 and 4. So this 3 and 4 having this specific cost here is 12. Okay, this has been connected. So then I'm just going to mark this is also completed. Okay, this is going to be the next minimum edge is done. So then after 10, 12, then 14 is the specific minimum edge. So if I tell 2 to 7, again I am not able to see any kind of a cyclic. So I'm just going to write it here. Okay, so I'm just going to write here as a 2, and I'm just going to tell here as a 2 to 7, right? So I'm just going to write it here as a 2 to 7. So I'm just going to draw the specific. Okay, so it has been, so I'm going to tell it as a 2 to 7. So I'm just going to tell it as a 7. So I'm just going to tell this specific cost is 14 over there. 1 to 6, 2 to 7 and 3 to 4 is done. So I'm just going to mark this as well. So this is also completed. The 14 is also completed, the 8. So then which is the next specific cost? So the next 2 to 16, right? 2 to 3. So 2 to 3 is the next minimum cost. Okay. If I tell 2 to 3, if I just try to connect 2 to 3 over here. So again, I'm not having any kind of a specific, I'm just going to tell here as a, again, I'm not having any kind of this specific problem, because it is not forming any kind of a cycle. So I'm just going to connect with 2 to 3 over there. Okay. This is going to be the 2 to 3 here. So it is having me, let me write the specific cost here is basically it is going to be 16 over there. Okay. So then this is also, I'm going to mark it. Okay. This also has been completed. Then next I'm going to just mark it next value. So then if I just tell here the next 16 is done, next which is going to be the next part over there. Okay. So here the next specific thing if I talk about here is the next 14, after 14 there will be 18, right? So if I just tell here as a 7 to 4, if I try to connect 7 to 4, what happens? It is going to form a cycle. So I'm going to ignore this specific 18. So then after 18, what is the minimum cost edge? The minimum cost edge is going to be 22, right? So this is going to be the fifth one. So I'm just going to write it here as the 5. So this is going to be the next minimum cost. Then I'm just going to tell here as this is going to be your the minimum next cost here. So for this specific 5 to 4, I'm just going to give the cost here as a 22 over there. Okay, this is going to be the cost of 22. So I'm just going to remove this specific thing. Okay, let me write it again. Okay, so it was a stroke razor. So I'm just going to write it again. So I'm going to connect with this over there. So okay, so this is going to be connected. And after that, I'm just going to tell this is going to be the cost is that is 22 over there. Okay, that is going to be the minimum cost spanning tree. So then I'm just going to tell here as I'm just going to mark it. This is done. So the next minimum cost here is 24. So if I try to connect 24, 5 to 7, again it is going to form the specific cycle. So I'm not going to connect with 5 to 7. So what I need to do here is basically I need to connect with the next minimum cost I need to check, that is 25. So I'm just going to connect with the 25 over here. That is basically 5 to 6 to 5, right? This is going to be the correct one. So here I'm just going to mark this specific thing here as the specific thing. I'm just going to tell here as it is going to be the cost is going to be 25 over there. So this is what it is going to be the minimum cost spanning tree. So this is basically whatever we have developed. This is going to be the minimum cost spanning tree using the Prim's algorithm. Spanning tree. So using the specific Prim. So this is basically here we are going to connect the specific edges. So that's all. Okay. So you can see this has been done. So here if I just try to tell, I'm just going to highlight this specific thing as well. That's 25 has been completed. Okay. So this is going to be the minimum cost spanning tree using Prims over there. Okay. So I hope you have added. So if I tell what is the cost of it, if I just tell here what is the specific cost of it, if I just tell here as a cost is equals to, so 10 plus 25, 35 and 45, 45 plus 51 plus 14, 61 plus 65 plus 12, 75 plus 77 plus 22, it is going to be the 99 over there. Okay. So the cost is going to be 99 for this specific Prim's and greedy algorithm. Okay. So this is how the things is going to work over there. So now we are going to see next specific like a program into the next session. We are going to see how this specific Prim's greedy method Java program is going to be written. Okay. So I'll catch you with the next session. Take care. Bye bye. Hey guys, welcome back to the section 4 session number 18.2. So in the previous session we discussed about the Prim's algorithm and the example with the Prims. So now we are going to see the Java coding part for the Prim's algorithm now. So let's begin with the specific coding part for it. So coming back to my Eclipse over there. So inside the Eclipse I have opened the specific stuffs here. So let's start writing the code for the specific Prims over there. So first we need to create a functions that's going to be handled the specific Prim. So I'm going to create one new class here. I'm going to right click. I'm going to create a new. I'm just going to click onto the class here. Inside a class, I'm just going to name the specific class as Prims over there. Okay. So I'm going to tell as a Prims is the class. Select this and just click onto the finished here. Okay. Let's see how the specific program is going to be there. So first and foremost, I'm just going to import all the Java packages. I'm just going to tell here as import specific java util.star. After importing it, now I can just start writing the specific code for it. Okay. So here I'm just going to create one specific class, public class is there, right? So wherever you want, you can just usually write it. So that's fine. So here we are going to write a lot of functions. Okay. So where these specific things will be there. So let's try to start with writing the first function here. Okay. For first specific method. So first function to find the minimum spanning tree using the prims algorithm. Okay, this is the function. So first I'm just going to declare one private static, and I'm just going to declare one final int. I'm just going to tell here as an int inf is the specific thing that is going to have the maximum. This is going to hold the maximum value. Okay, so I'm just going to tell here as an integer dot max value. So this is going to store the specific max value for us. So once I just store this specific max value, now we are going to start writing the specific method for it. Okay, so the method is going to be like, so the first I'm going to write the function to find the minimum spanning tree using prims here. So for that I'm just going to write one method, that is I'm going to tell here as a specific public class. I'm just going to tell it as a public class. So this is going to be what this is going to be the specific, I can just tell it as a public static void. Okay, so this is not going to return anything. This is going to write, let's try to write it as a minimum spanning tree. Okay, this is the name I have given, prim minimum spanning tree. So this is going to take the int of array. Basically we need to pass the specific multi-dimensional array, that basically to declare what is the graph. So we are just going to pass the graph here. So we saw, right, how to create a graph using the cost adjacency matrix, cost adjacency matrix, right? So we are going to create one cost adjacency matrix, so that we are going to pass as an input for this specific method to form a specific graph. Okay, and I'm just going to pass the int of vertices here as well, int of v. This is going to be the starting thing like that. Okay, so once in this specific function, I'm just going to declare array to store the specific constructor specific. We are just going to create one array that store the constructed that is MST, that is basically minimum spanning tree. Okay, so let's create that thing. Let's say as an int. So now let's create it as a p or ent. Parent is equals to, that is going to be a new of int of v. So we are going to pass the specific vertex's value to it. Okay, this is going to be stored over there. So once it is done, I wanted to create a key values used to pick the minimum edge. Okay, so basically first it is going to store the vertex, and the next int array is going to store the minimum edge here. Okay, this is going to store the minimum edge. So I'm just going to tell int key is equals to specifically, and I'm just going to tell here as a new of int of specifically v over there. Okay, so I'm just going to pass like this. So this is what it is, a specific function. Then I'm just going to create one boolean value based on some condition it has to select, that is basically to represent the specific set of vertices including over there. Okay, so this is what we are going to do it. So what we are going to do here is, we are just going to represent a vertices including the minimum spanning tree. So that is what we are storing inside the boolean. So I'm going to tell here as a mst set is equals to, specifically I'm just going to tell this is going to be the new boolean value. Okay, so whatever the v value will be there, so I'm just going to pass it over there, new boolean of v here. So once it is done, now we need to initialize the array, all keys as infinite. Let's initialize first in the starting way, whatever the things will be there, we are going in this specific we are creating, right? In this specifically I'm just going to initialize everything with the maximum value. Okay, so that we need to do it. So here I'm just going to tell here that initialize the array. So I'm going to use the arrays dot fill. I'm just going to use the inbuilt method, that is arrays dot fill. You can see it is taking the mst set, that is basically whatever the boolean value, then along with that it is going to take the inf is basically which we have declared it onto the top, right? Is going to be stored as a maximum value for us. This is going to be stored as a maximum values to us. Okay, this is going to be used over there. Okay, so I'm going to tell arrays dot fill. Here I'm just going to pass it here as not the mst boolean. Here I need to just pass the key first. Okay, key and the inf maximum value. So we have initialized all the keys as infinite, all the edges as infinites over there. Okay, once it is done, now we need to include the first vertex in the minimum spanning tree. So basically I mean to say, I am just going to draw the first edge between two vertices over there. So for that I'm just going to tell here, first I'm just going to access from the indexing key of 0, from the specific key vertex 0, initialize with 0 over there. Okay, then I'm just going to tell it as a parent. So whatever the maximum minimum can be, 0 is equals to, I'm going to declare with the -1. So here what we are doing here is, so key 0 of 0 means make key 0 so that this vertex is picked as the first vertex. Okay, we are making 0 so that the vertex is picked as the first vertex. The parent of 0 is basically means first node is always a root, right? The first node is always a specific root over there. So I'm just going to write, I have already I'm just going to write the comment so that you will be understanding easily. Okay, this is basically I'm going to tell array to store the constructed minimum spanning tree, then key value to store the specific spanning tree. Okay, then I'm just going to tell whatever the boolean value we have created, this is basically does what it is specifically to represent the set of vertices including the minimum spanning tree over there. Okay, that is what we are doing it here. And what is the array? Basically we are initializing the what we did, we are initializing the all the keys as the infinite over there. Okay, that is what we are doing it. So always we need to include the specific first vertex. So this is the comment I'm going to write it so that you will be understanding more better way. Okay, this is also very important to understand the code. Then next, always we need to select the specific first vertex. So we are just giving that is make key 0 so that this vertex is picked as the first vertex. Then next, again the first node is always the stuff, right? So I'm just going to tell the first node is always the roots of the minimum spanning tree over there. Okay, this is going to deal. So now we are going to run one specific loop. The MST will have the V vertices. So I'm just going to run one specific loop that is going to have the minimum spanning tree over there. So we are going to run the loop now. So here I'm just going to tell the specific for loop. I'm just going to make use of the for loop. So in this I'm just going to create int of let's start with the count is equals to 0 here. Okay, then the count value should be less than the vertex V minus 1 over the vertex V minus 1. Then along with that I'm just going to increment the count value, that is count plus plus. So what this loop is going all about? So basically we are going to pick the minimum key vertex from the sets but this is not yet included. Okay, we are just picking the specific minimum edge vertex over there. So I'm just going to paste it over here. Okay, so what we are doing, pick up the minimum key vertex from the set of vertices not yet included in MST over there. So what we are doing here is we are just going to select the specific vertices which is having the minimum edges over there. Okay, that is what we are doing it. Okay, now what we need, this is basically a min key is going to, we are going to write the specific min key function here. Okay, so that like let's write the specific min key function here. So that function can be like this loop is ending here. Let me write one function for the min key. So let's create one more method, that is a public static int that is going to the min key, right? So we have created as the specific minimum key. So if this takes the basically int of key here, then it takes the boolean values of minimum set of set over there. This is going to take MST set comma and same as it is int of V over there. Okay, so we are setting key MST set and V. So we are just taking this argument. After taking this specific argument, we are just going to run one loop over here. Let's see what it is going to be there. So what I am going to do here is I'm just going to write, first I am just going to store one minimum value, like I am going to pass the INF to it and the min index is equals to -1 over there. Okay, then minimum value I'm just declaring as INF and then I'm going to run the loop. So from this specific whichever the key and index is very having the less value, less specific key, basically we are running a loop from here. We are just going to check which is the smallest edge from the specific graphs over there. Okay, that is what we are doing it. So once we got it, that is going to return the which is the having the minimum index value basically. Okay, so when it is done, it is going to give you back the u. It is going to return you the specific u over there. Okay, so once it returns back the u for you, now we need to do what? We need to apply this specific 3 stuffs which we did it, right? So I'm going to tell once I get the value of u, so what I need to do, I'm just going to tell graph of u comma v is the non-zero only for the adjacent vertices of the m. M of set v is a false for vertices not yet included in MST. Update the key only if graph of u v is smaller than the specific key of vertex over there. Okay, so what we are going to do here is we are just suppose I will take it as a number. First I'm going to take a vertex 10 which is having a 10 things, then I'm going to match all the things. If it is lesser, I'm just going to take that, or else I'm just going to increment the loop. So again I'll take 25. If it is smaller, we are going to take it over there. So that is what we are doing inside this. Okay, let's write the specific graph over there. So for how it is going to be the code here. So let's try to give it the specific graph. Okay, I'm just going to tell if this specific condition, I'm just going to make use of the graph function. In the graph, I'm just going to pass that is a u of v. So I'm just going to pass the u and v, the starting vertex to the next vertex. If it is not equals to 0, and I'm going to tell this condition should get matched, and basically if it is not equals to minimum spanning tree set, that's basically a boolean value, it returns you true or false, then I'm going to pass it as a v, and along with that ampersand, the specific graph should be graph of u and graph of v should be lesser than the specific key value, key of vertex v over there. Okay, it should be this case here. So if it is case, then I'm just going to make that specific thing as the parent of v is equals to u over there. I'm just going to make the what is the cost of it, and I'm just going to store the key of v. That's basically declaring the specific graph. I'm just going to draw the graph for the specific thing which we have been selected, that is a u and v over there. Okay, that's what we are doing it over there. Okay, this is the main condition which is need to be taken care. Now we need to create one specific graph, right? I need to create one graph. So how it is going to be the graph for it, that function I need to declare it. So for that, for the graph, we have used the graph of u of v. These all things we have done. Now what we need to do now, next we need to create the specific basically next we have created this one, right? So here we are passing a v, right? So v is less than v. So basically what I need to do here is, in our specific loop, that is v minus 1 and the count of plus plus plus, so we need to do another thing, like I need to just pick the specific vertex here. So we created the min value, right? I need to set one more thing, like adding the specific vertex over here. So let me set this one, adding the MST of u is equals to true, just making the starting vertex to true over there. Then again I need to run one more loop over here, then I need to use this one. Okay, so let's write this specific loop here. So whatever the if condition is there, so I'm just going to use v of is equals to, from this specific every vertex I need to visit, right? So I'm just going to run one loop and I'm going to close this specific loop. Now it is going to be perfect over there. Okay, so once it is done, I'm just going to call the constructed tree. So I'm just going to construct the specific tree over there. So let's construct the specific print the MST over here. So let's see what it is. It is going to take the parent and it is going to take the graph and it is going to take the starting vertex and it is going to evaluate the program over there. So once it is done, now let's try to create this in our let's try to have another method that's basically prints the parent, graph and all those stuff. So what I'm going to do, I'm just going to create another method over there. Let's try to create a method here. The method name is the prints MST, minimum span tree. It takes the parent, graphs and the vertex v. This is going to take the all the cost and takes the parent and what is the v. Then it is going to tell edge of the specific weights is so and so. It will tell parent of I and what are the parent of I of I, what is the vertex and what is the specific graph of it. Okay, this is going to print, this is going to be the final one. Now let's try to call the specific and let's try to create a graph and just pass the vertex value to 5 over there. Okay, so in this public static void main, I'm just going to create one graph here. So you can see I'm passing 02060 and 20385 030. These all basically I'm passing the specific edges here. Okay, I'm just passing the edges weight here and your vertexes will be 5 and this is the weight value of it. So now I'm just going to call the method. So once I just call this specific method, if I just try to run the program and we are going to verify as well. Okay, you can see here I'm getting the edges for 0 1 0 1 is 0 to 1 is basically I'm getting the weight is 2, 1 to 2 is weight is 3, 0 to 3 is a 6 and 1 to 4 is a 5. That's amazing, right? So you can see what happened here is it is going to go to this specific parent printing which is this print MST. It takes the specific edge. Okay, it's here parent of is basically takes the edge, what is the edge vertex, and then to I to the next specific vertex, and whatever the weight is there from the graph of I and parent of I, whatever the weight we have declared, that is going to get written over there. Okay, this is what it is going to do over there. Okay, so now let's try to see whether this specific thing is the program is perfect or not. Let's verify this. Okay, so for that let me create a graph for it. So how to create a graph, you know, right? So let's try to create a graph very quickly. So let's imagine I'm just going to open the here. Let me do like this. So yeah, let's create a specific, let's create it in the same way. Okay, to verify it here. So here I'm just going to create let me close it to here. Okay, so let's have it here. Let's try to create one graph over here. So let's say we'll have another thing like we have a weight like 0 vertex 0 to 4 we are having it, right? We are passing v as a 5 here. You can see I'm passing here as a 5. So that's why what I'm going to do here is I'm just going to create this specific vertex. Let's create here as a 0 0 and 1. So I'm just going to tell here as a 0 1 2 and I'm just going to 3. I'm just going to create as a 4 and I'm going to create it as a 5 over here. So let's tell here what is the graph we are having. So we are passing so let's take this example. So how you need to do means you need to just tell here like if I have this one. So imagine I have here like, so I'm going to tell here as a 0 1 2 3 and 4, and I'm going to tell here as a 0 1 2 3 and 4 over there. So this is what we are having it. So in this I need to write like this. So 0 to 0 we are having the cost 0 here, right? So I'm going to write here 0 0 2 0 6 0. Okay, then again 1 we are having as a 2 0 3 8 and 5. Then what is having here as a 0 3 0. Then we are having 00 and 7 here. Then we are having as a 6 8 0 0 and 9 over there. So then we are having as a 0 5 7 9 and 0. This is our having the specific cost, right? So let's write it here. Now we have created the cost. Now tell here 0 to 0 we are having a 0 here, and 0 to 1 we are having the cost here is a 2. So I'm going to tell the cost here is a 2, and 0 to 3 we are 0 to 3 we are having a 6. So I'm going to tell 0 to 3 we are having the cost is 6 here. Then again 1 to 0 we are having 2. So I'm going to tell 1 to 0 is 2. Yes, 1 to 1 is 0, 1 to 2 is 3, 1 to 2 we are having as a 3 here, 1 to 3 is 8, 1 to 3 is specifically 8. Again 1 to 4 is 5. So I'm going to tell here as a 1 to 4. 1 to 4 we are having a 5 here. Again 2 to 0, 2 to 1 is 2 to 1 is basically 3. Again 2 to 4. So 2 to 4 is basically we are having the 7 is the cost. I'm just going to tell 2 to 4 we are having a 7 is the cost. Then 3 to 0 is 6. So I'm going to tell 3 to 0 is 6 already there. 3 to 1 is 8. So I'm going to tell 3 to 1 is 8 already there. Again 3 to 4 is 9. So 3 to 4 is basically we are having a 9 over here. Again 4 to 1 is 5. So basically I'm going to have a 4 to 1, right? Sorry, 4 to 1 is 5 already is there. Again 4 to 2 is already 7 already is there. 4 to 3 is already 9. That's it, right? So yeah, we are having a 0 to 1 2 3 4, right? Yeah, definitely this is not there, right? This basically thing is not there. So I'm just going to write it. So this is going to be your graph for the given input which we have seen in the program. So now if I try to get the what is the minimum cost here, so let's try to apply the Prim's algorithm. So we are having it 2. So basically 0 to 1, the minimum cost is going to be 2. Then after that 3 will be coming to the picture. So I'm going to tell 3 is going to come into the picture. Then after that 5 is going to come into the picture. So I'm just going to tell here as a 4, that is going to be 5. Then again 6 is going to come into the picture. So this is going to be come into the picture, that is going to be 3. 0 to 3 is 6. The 2 3 5 6 is done. Then again after 6 7. So 7, if I just form the 7, it is going to be a cycle, it is not valid. If I tell here after 7 8, so after tell, if I just tell here as a 8, if I tell here as a basically 3 1 2 3, if I form again, it will going to form the cycle. Then again whatever you do, it is going to form the cycle, right? So this is going to be the final cost here. So let's verify whether this is correct or not. So let's verify this is correct or not here with the given output. Okay, so you can see guys, 0 to 1, the whatever the weight is 2 is correct. And again 1 to 2, 1 to specifically 2, what is the cost? 3. Yes, perfect, right? This is correct coming. Then again 0 to 3, so 0 to 3 is 6. Yes, this is also perfect. Again 1 to 4, 1 to 4 is basically a 5 here. This is verified. Okay, so whatever the code we have written, this is a perfect code, and this is how we are going to find the Kruskal algorithm. So this is basically, sorry, the Prim's algorithm. So this is a program to find a minimum cost spanning tree for the specific program for the Kruskals over there. Okay, sorry, Prim's. So in the next session, we are going to look onto the Kruskal algorithm. Take care. Bye bye. Hey guys, welcome to the section 4, session number 19. So let's understand the Kruskal's algorithm. So it's similar to the Prim's algorithm, but only the small difference here is a very minimal. So let's understand with this. Okay, so basically Kruskal algorithm is again popular for the algorithm to find the minimum spanning tree, right? So for the connected and undirected graph. So here basically we will be having a tree, right? So we are going to take one specific edge, sorry, the vertex. Then we are going to see what all the edges is going towards the going inbound and outbound for the specific vertex. So whichever is minimum, we are going to just select that, or else if it forms a cycle, we are just going to ignore it. That's it. Okay, and it has been developed by the Joseph Kruskal, so there the name has been named as a Kruskals over there. So algorithm, how it is going to work here is basically we're going to sort the specific vertex with the ascending order based on the weights, then creates an empty set to the represent the minimum spanning tree, and we are going to initialize the specific tree for it, basically like a collection of trees which initially contains a single vertex. So there will be initializing with a single vertex. Then we are going to run one while loop like minimum finding the minimum MST. That's not, it is not a spanning all vertices. Then we are going to select the specific smallest edge from the edges, which is from the inbound and outbound. If it's forming a cycle, see, if we tell if the edges is forming a cycle, we are going to skip that and move on to the next smaller edge over there. And basically when we do the minimum spanning tree, it contains obviously vertices plus v minus 1 edges, right? This is the formula which we have been seen in the Prims as well. So let's begin with an example. So coming back to the notepad for it, so let's see how it is going to be there. So in this, let's try to write one specific example. So the example here we are going to use, like let's imagine we are having here as a 1, and let's tell this is your vertex 2, and this is going to be your vertex 3, this is going to be your vertex 4, vertex 7, and vertex 5 here, and the specific vertex 6. So let's imagine from the 1 to 6 we are having the weight 10, and 122 we are having the weight 28. Let's tell here as a 14. Let's take it as a 16 here. Let's take this as your 12, and let's take this as your 18, and let's take this is your as a 24, and this is going to be your 22. Let's make it as a 25. So now let's make it the specific crystals over here. So what is going to be the time taken? So basically we know here the edges will be we need to get it as a vertexes minus 1. This is going to be the formula. The time complexity times space complexity is going to be big O of n square, because I need to check with the both the end, right? Every vertex I need to check twice. Okay, that's basically if it is having an n element, it's going to be the n square as a space time complexity. Okay, that is why we are using it. Now basically now we need to select the edges here, right? So let's try to start with the vertex 1 here. Let's try to start with the vertex 1. So in this specific vertex 1, so let's write it here. Okay, so let me write it into the 1 in the red color. So I'm going to write it here as a 1 here, and I'm just going to take the vertex here. So which is having this is basically a 28. Okay, this is going to be a 28 here. So what is the minimum spanning tree here? What is the minimum cost from this vertex? So tell 1 to 6 is 10, and 1 to 2 is basically taking as 28. So I'll be going with the head with the 1 to 6, right? So I'm just going to tell here as a 6 here. So in this 6 I'm just going to tell here as 1 to 6 is going to be your 10 is the vertex. Now again I'm going to check from here. So 1 to 2 is basically having a 28, and from 6 to 5 we are having as a 25. So which is smaller? 6 to 5 is smaller, right? So I'll be going to the next vertex, that is 6 to 5. So I'm just going to write it here as I'm going to tell here as this is going to be a okay, sorry. So I'm going to tell as a 6 to 5 is going to be, so the size is going to be 25 over there. That's fine. Then again I'm just going to check. So now we are having a 3 vertices has been done. Now I'm going to check which is having smaller. So now I can see here 5 to 24 is going, 22 is going, again 28 is going. So which is smaller, guys? 22 is smaller, right? So I'll be going ahead with this one. So I'll just tell here as a 4 here. So in the 4 I'm just going to go with the specific 5 to 4. The 5 to 4 is going to be 22 is the cost over there. Okay, then we are having 436 as selected. So let's see which is having the minimum at. So now from 4 to 3 we are having 12, 4 to 7 we are having 18, and 5 to 7 we are having 24 and 28. So in among this 28, 24, 18 and 12, so which is smaller? 12 is smaller. So I'll be going ahead with the vertex 3 here. So I'm going to take the vertex 3. So I'm just going to tell here as it is going to be here as a 12 over there. That's great. Next, so now we are having 3 to 2 we are having a 16, right? 3 to 2 we are having a 16, and we are having 4 to 7 I can go as a 7, 18 here. Again 24 I can go. Again I can go with the 28. So apart from this, which is smaller, 16 is the next edge which is getting smaller, that is connecting with the vertex 2. So I'm going to go ahead with this 2. So I'm just going to tell here as a specifically I'm just going to tell here as a this is going to be the specifically it is going to have this. So I'm going to write it here as 2. Okay, so I'm going to tell here as a this is going to be the next vertex smaller, that is 16 over there. I'm going to mark it as a 16. Next, now we are having a 2 to 1, we are having 28. I cannot go with 2 to 1 because it is going to form the cycle. Again I can go with the 4 to 7, it is 18. 2 to 7 is 14. Again 5 to 7 is 24. This is all the possible. 24, 18 and 14 is a possible way. So which is a smaller? 14 is the smaller. So I'll be going ahead with the 14 over here. So I'm just going to write it as a 7 to 2. So it is going to be have the specific minimum smaller stuffs over this. So I'm going to tell the 14 is this next minimum smaller. So this is going to be, this is the task is done. So this is going to be your minimum cost spanning tree, right? It's going to be your minimum cost spanning tree. I'm just going to tell whatever you have to tell. This is going to be the minimum spanning tree using Kruskal's method over there. So this is how the specific Kruskal's algorithm is going to work, and I hope you got this one right. This is how the things is going to be done. Okay, this is the another way of understanding the Kruskal. So let's take the what is the cost. You can just search for, you can just add 10, 20, 25, 12, 16 and 14. That is going to give you the cost of the Kruskals over here. So it is similar to Prims, but there we are setting the minimum edges, but here we are going to first select the vertex. From next vertex we'll select which is having minimum. Again while going it, again we are going to check with the all the possible minimum cost for the all the vertex which is coming from. Okay, that is what here it is having it here. Okay, so let's take another example. Let's take one good pink color. Okay, let's take a color here. So imagine I have one here. Let's we are having a 2 here. Again we are having here as a 4. Then we are having here as a 3 here. Then again we are having as a 5 here. So in this, let's imagine we are having a 2 and we are having the connections like this. Okay, so imagine this is the connections we are having it. So in this, let's try to have the connections like this. So I'm going to tell this is I wanted to find what is the cost is present here, and I want to find what is the cost here. Let's imagine we are having 4 here Here we are having a 2, here we are having a 3, and here we are having a 4 over there. I wanted to find what is the specific cost over here. So 2, 3 is there, and here it is 5 is there. So imagine if there was a 3, 1 to 4, if it is a 4, again 3 to 4 also might be the chance, it can be also 4. So as it is forming the cycle, we are not using the specific thing, so we are using 2 here. So it can be 4, right? Again, imagine what can be the cost of this. So 1 to 2 is there. So after 5, what can be the maximum cost? So again, if we write this, it is going to form the cycle. It might be 6 here, right? After 5, it can be the cost can be 6. So again, you can just have a understanding. Okay, in this way also, we can just find what is the minimum cost spanning tree. Okay, but not accurate, but you can have a look onto it. This is the one thing I wanted to say in this specific session. Okay. So in the next session, we are going to see the specific program for the crucicles, and we are going to see how the Java program is going to be there. So that we are going to see into the next session. Take care. Bye bye. Hey guys, welcome to the section 4 19.2 session. So let's understand the crucial algorithm Java code into this session. So let's begin with the coding part of it. I have opened this specific Eclipse over here. So let's see how this specific program is going to be there. So I'm going to create one new class for it. I'm just going to create a new specific class. Let's make it as a specific anything like C or U as crucial algorithm. Okay. So let's make it as a crucial algorithm. So I'm going to make it as a public static void main. Let's finish this one. Okay, so once I finish, so I'll be getting the crucial algorithm public class here. So first and foremost, I'm just going to import all the packages of Java. So I'm going to tell it as import java.util.star over there. Just save it. So then I need to just create one specific class here. Just basically, let's try to create a class to represent the graph edges over there. Okay, so we'll create one specific class that is going to represent the graph edges over there. So I'm just creating a class. So here you can see we are just creating a class edge that implements the comparable edge here. So we are using the implementation that we are using a more advanced Java concept using the edge, minimum edge. This is the edge which is going to take it over there. Okay. So here we are having specifically I wanted to create one variables like source to destinations and what is the weight. So what we are doing here is we are using this specific edge where whenever the function basically stores the edges based on their weights over there. Okay, it is a very like a latest code of Java for the crucial algorithm. So previously we saw for a prims that we are writing our own logics over here without using any inbuilt stuff. So but here we are using something inbuilt functionalities. Okay, that makes the more program more compatible. So here this function what it does, it takes the edge and it compares the next edge and it just takes basically the edge of the current edge and the what is the weight of the next edge over as compared to the next edge over there. Okay, this is going to be the class. So here I'm just going to create another class. The class is going to be called as a subset for union to find it. Okay, so where it is going to have a union subset parent and it is going to take the two parent and rank we have created. Okay, let's see what it is going to do. So next what we are going to do here is we are just going to create a specific what we are going to create the specific graph with v vertices and the edges. So we had that initialize the v and the edges. Okay, v basically tells the number of vertices, e is basically number of edges. So using an edge, so whatever we have created a class edge, right? For this I'm just creating an empty collections of all the edges which it is going to store with the source to destinations and weights over there, right? So we created something called as a crucial algorithm that takes the vertex v and the edges e. So basically for all vertex v and for the edges v, we are going to create every edges. We are going to create the edges and we are going to store the what is the weight for it. Okay, that is what we are going to do. This function is going to do that. That's very simple. Then next, we need to write a function to find the set of an element here. Okay, that's basically we need to find the specific subsets, right? Which is having the what is the weightage, which is having the minimum weight for the vertices, that for the minimum edges. So for that we are going to write a function to find the set of element I. So here we are creating a find method that takes the subset, basically all the small subset, and it takes the what is the I value here. So the find the root to make as a parent. So basically I need to first initialize the root, right? So as I said, we need to start with vertex root here. So I need to just start with the vertex root, then we are going to find the which is the having the minimum edge. So we are going to do that. This function does that itself. We're just going to check the subset of I dot parent is not equals to I. It is basically, imagine this is not going to be a root element, and then we are going to apply the same method that's going to match with the subset and the what is the next sub edges over there. So whichever is the smaller, that is going to just it is going to return as the specific thing over there. Okay, that is what it is going to do. Next, the very important function we are going to write. So we are going to find the union of the two sets now. So we are going to find the union of a two set. So basically a set means, you know, right, that's having the unique thing that is not having a repeated. So this union, what does it is, it is going to take the subsets and it takes the one int x and int y. So what is this int x and y here? Basically, we are going to find the root, what is the first root and what is the next specific root which we are matching it. So attaching a similar rank tree under a true for a high rank tree union by rank over here. So what we are doing here is we are going to specifically check the first root, whatever the first index root edges, what is the first index root edges weight is lesser than the next edge root. If it is lesser, then we are going to mark that as the into our tree. We are going to make a tree for it. Basically, we are going to talk about it graph. We are making a graph here, or else we'll mark to the next specific element over there. Okay, else if okay, again I'm just going to check if it is from the root, it is going, we are going to mark it. Okay, if they are having the same rank, if it is having, or else if we don't have anything, we'll just increment it, right? We are going to increment. I mean to say, this is what we are doing. When I come here as a 4, when I just searching for a 4 here, first I'm just going to see what is it from the root. I'm just going to check whether having the smaller, no, again next else. So else if means whatever the else if part will come again, whatever they will be having like this, we'll just keep on incrementing. Again we'll be working with the same loop. So it's a very important function, that's union, that's basically search, which is the minimum edge over there. Okay, from to the parent to the rank, parent to the destination. Okay, that is what here. Then next we are going to write one function, that is a crucible, that's mainly construct the specific tree. Okay, where we are initializing the results and the specific sorted array over there. So let's write that specific method. So that specific method, let me write that specific method here. Okay, so this is going to be a very big function, so I cannot type everything. If I type, it is going to, video length is going to be very high. So that's what we are going to avoid the typing for the large programs. So this is a function where we are having the crucible's MS tree, where it is basically stores the results. Basically this is a function that stores the result after evaluating all the things. So we are going to initialize the result with the starting with the 0 vertex and the 0 edge. Then we, for the starting, we are going to start with the new edge. We are going to sort all the edges, and then we are going to create a subset of all these things. Then whatever the subset we get, we are going to store it here, and we are going to mark which is the parent and which is the next vertex with this. Then along with that, we are going to create a specific, we are going to run a while loop. Then first we are going to see which is the smallest edge from all the edges. I'm going to see picking the smallest edge and we are going to increment it. Picked it and we incremented. Then again we are just taking the next subset, again we are just taking the smallest subset, again we are going to increment it. So during these conditions we are making sure that it is not causing the cycle, that's the main thing, right? And again we are just doing the same thing here. So then this is the function which is going to tell following edges are the constructor. Basically this is going to be your final output. Okay, what is the specific source to the destination and what is the weight for it, that is what we are having it. Okay, so let's take one example and initialize, and let's see what is the output for it. Okay, so let's try to give one specific example and just call the method. So I'm just going to title the example here. So you can see, let's say this is your graph. Okay, this is going to be your graph 0 to 1. So this is basically a graph. I wanted to tell here the vertices are 4 vertices and edges is going to be 5 edges here, 1 2 3 4 5 edges. And I'm going to call the Kruskal's algorithm method, and we are just marking this like edges of 0 to source is 0 and this destination is 1. Okay, and again we are marking, basically this is telling 0 to 1 what is 0 to 1, what is the weight, 0 to 2 what is the weight, 0 to 3 what is the, if I tell here 0 to 3, it is having a weight 5. If I tell here as a 0 to 3, you can see the weight is 5. In previous example for the prints, we were marking in this specific way. We are using the graph things here. So, but here using this specific graph edge method, this inbuilt method, and we are making the values to it. Then after doing the value, then we are calling the graph.crucible.mst. So with this, whenever this method calls, this is going to initialize all this, sorts this, and finds the minimum edge and gives the output. So if I try to run the program of this, if I see here, you can see I'm getting here as a 2 to 3, the minimum edge is 4 here, 0 to 3 is 5 and 0 to 1 is 10 over here. So that will be absolutely correct. So you can see if I just here, if I take an example here, so basically if I start with, basically this is starting 2 to 3, so it is starting 2 to 3, this edge is selected as 4 and 0 to 3, 0 to 3, 0 to 3, 5 is getting selected, again 0 to 1, basically it is ulta z. You can see this is the graph that has been selected. The minimum cost is going to be basically 10 plus 5 15, 15 plus 4 that is 19. 19 is the minimum cost spanning tree for the Kruskal algorithm for the specific example. I hope you got this coding problem, and it comes through practice, so you can have a practice like that and have it trace the program, and this is all about the Kruskal's greedy method. In the next session we are going to start with the Dijkstra, that is going to call as a single source shortest path as well. So we are going to see how this specific method is used to solve the given problem. Take care, bye bye. Hey guys, welcome to the section 4. So let's begin with the session number 20. Let's see what is a Dijkstra algorithm. That is, we are going to call in other word, that is a single source and the shortest path over that. So using this specific algorithm, we are going to reach from the source to the destination in the shortest way using the Dijkstra algorithm. So let's see how it is going to be there. So let's begin with the example over there. So coming back to my specific notepad, so I have created one specific example over here, right? So let's see how this is going to be working over there. Okay, so let's try to give some kind of let's make this specific graph as a directed graph. So in this specific, I'm just going to give some numberings over there. So this is going to be the node 1, this is going to be the node 2, and this is going to be the node 3, and it is going to be 4 here, then it is going to be here as entire 5, and I'm just going to make this is as the 6 over there. So I'm just going to make this entire graph to little bit center over here, because we're going to do a lot of things with the same thing. Okay, so now I'm just going to make this specific graph as a directed graph. So let's make this is as one specific direction, and let's make this is going to be another direction. So I wanted to maintain little bit neat, so please pardon me. So I'm just going to make this is as one of the directed graph. Okay, so let's tell here as this is going to be like this. Okay, so like this. Okay, so this is having the direction like this. Then I'm just going to tell this is going to be have a direction something like this, and this is going to be the another direction like this directed, and let's tell this is going to be outbounding towards it. Okay, so let's having all the direction towards it. This is how you can just have a look on it. So I'm just going to a little bit, I'll just zoom it. So okay, so in this specific thing, I'm going to select this specific point tracer. So I'm just going to create another stuff like this. So let me add like this. Okay, so like this. Okay, let's keep it. Okay, so this is in direction. Okay, so it's having the direction, all the right side direction over there. Now in this case, I wanted to give the weight for the graphs over there. Let's try to give the specific weight for the graphs. In the red color, I'm just going to give the weight. So imagine from 1 to 2 the weight is 2 here, and from 2 to 4 the weight is 7, and 4 to 1 the weight is 1 over there. Okay, then I'm just going to give the specific weight from 5 to 4 is going to be 2, and here from here to here it is going to be the weight 5, and imagine 3 to 5 the weight can be at least 3. So let's tell here it is having 4, and if you have a straight lines as well, right? So I'm just going to make this also one directed, this is also pointing towards down. So this is going to make it this specific weight is 1. Then I'm just going to make this specific directed towards here, directed to the 4, and this specific weight is going to be 2 over there. Okay, so now we have created a graph, and we have added the entire weights and the specific nodes over there. So for the initial condition, so I'm just going to write the first iteration. Let's take a simple color for every iteration. So I'm going to start with the blue color over there. Okay, so let's start with the blue color over there for every iteration. So for the specific value, let's assume it is having infinity, and here I'm going to mark it as infinity, and it is also infinity, and I'm going to mark it this also infinity, and I'm going to mark this specific as an infinity over there. Okay, so let's assume we are going to start from the 0th over there. Okay, and in this case, if there is one formula, based on the formula we are going to work onto the entire array over there. Okay, what is the formula? I'm just going to write if the specific distance of u, if the specific distance of u plus c of distance of the vertex u to v is lesser than the vertex d of v. Okay, lesser than the specific vertex v of v. In this case, what happens here is, so we are going to change the specific distance to whatever the distance is having from d to u plus c of that is u comma v over there. Okay, so in this case, this is going to be the relaxation formula. Whatever the formula you are seeing here, right, from the right hand side, I'm going to select this formula. Let me place it here somewhere onto the top or somewhere here. Okay, so based on this specific formula, we are going to evaluate the entire array over there. Okay, entire structure. So what we are doing here, if the distance of u plus c of distance of v, it is going to be, if its condition gets matches, we are going to replace this with this specific formula. The entire Dijkstra algorithm works in this specific condition. Okay, so now let's try to imagine for the first iteration over there. So let's take the black color. Okay, so imagine what is the distance. This is basically, you can assume this is going to be your u, and first if we select the vertex 1, this is going to be the u, and let's select the next vertex, that can be the vertex that is v over there. This is going to the vertex v. Let's try to evaluate this specific formula inside this specific formula. So I'm just going to use for the if d of u. So d of u is basically what? D of u is going to be 0, right? It is going to be 0 plus C of distance of u to v. That is distance of u to v is basically, what is the distance of u to v? It is 2, right? I'm going to tell 0 of 2 plus is lesser than distance of v. So what is the distance of v? This is basically having an infinity for the first iteration. So if it is having the first iteration infinity, so I'm going to tell 2 is less than infinity. Yes, these conditions get satisfied. So I'm just going to change the vertex d of v, whatever the distance of v of v is there, right? I'm just going to change it d of u plus c of v. What is the distance of u? It is already a 0 plus what is the c of distance of u to v? That is 2. So I'm just going to change it to 2 over there, right? So what I'll do here is, I'm just going to mark this, I'm just going to erase this infinity and I'm just going to mark it to 2 over here. The distance is 2 from here to here. Okay, this is how we are going to make this specific thing. So this is the one specific outgoing index from 1 to 2. Okay, this is the first index that is going from here, right? The next, let's select from this. When we are selecting this one, first we are selecting this one, we are just selecting this specific thing. So let me mark it as here. So let's select here. Okay, first I'm going to mark this first index. I'm just selecting this first vertex. Now I'm just going to visit the next nodes of this specific vertex, whichever it is going on. Now there is a second index as well, that is the infinity. Now I'm just going to apply the same formula. The distance of u, so I'm going to tell this is the first iteration. So for the second iteration, again I'm going to write it here itself. Okay, so I'm going to tell here 0 plus distance of c of u to v, distance of 1 to 3 is basically is 4. I'm going to tell 4, okay, is less than distance of v. Now it is now this specific thing is going to mark it as v. Okay, this, what is already the, what is the value of it? It is already having an infinity. So 4 is less than infinity. Yes, this conditions gets matches. So what I'm going to do, whatever the distance of v is there, right, I'm just going to mark it as distance of u is already a 0 plus distance of v is what is the distance of c to u of u comma v is having 4. So I'm just going to mark it as 4. So 4 is the best, right? Rather than having a greater value, 4 is best one. So I'm just going to mark the infinity. So I'm going to mark it. This is going to be the 4 value. Okay. So in this case, we have found the distance for the vertex 1. The vertex 1 is selected over there. Okay. So this is how you are going to do for the entire. Still last, we are going to follow the same specific approach over there. Okay. Now, next we are going to select the next shortest vertex over there. The next vertex, I'm just going to select it here as 2 here. So I'm going to select the next vertex here as a 2 here. Okay, I'm just going to select the next vertex as 2. When I select the next vertex of 2, I'm just going to select the specific pen. Let me change this color. This time I'm just going to make it as purple color. Let's use the purple color over there. Okay, so in this, now I'm just going to tell, so from the 2 we are having an outgoing bond, that is 2 to 4, and we are having an outgoing bond from 2 to 3 over there. Okay, so let's check the same formula. Let's try to apply this here. Let's try to apply the formula here. Okay, so what is the distance? Let's use the same formula here. Okay, so I'm going to tell if the specific distance of u, what is the distance? Now it is going to be u, and sorry, it is going to be u, and it is going to be v over here. It is going to be v here. Okay, it is going to be v here. So now what is the distance? When I go from the distance from 1 to 4, what happens? The specific, let me write it directly. Okay, rather, so I hope you have understood what is this, right? So this, we need to apply the same formula for the every iterations here. So let's try to go from here. So again, I'm going to select the 2. If I wanted to reach to the 4, fourth value is infinite. So basically, I'm going to see what is the shortest distance of u. So it is 2. Then 2 plus 7, 2 plus 7, it is going to be what? 9, right? So it is going to be removed and it is going to be 9 over there. It is going to replace with 9 over there. Again, when we have selected 2, there is another ingoing bond to 3 over here. So already, what is the shortest distance? We are having 4 here. So we'll see whether we'll having a more better than over here. So now if you see here, d of u value is going to be 2. So the shortest distance from 0 to 2 is 2. Again, from here to here I can reach, right? That is 2 plus 1 is 3. So 3 is better than 2, right? 3 is better than 2. So if this condition satisfy, I'm going to replace this 4 with 3 over there. Okay, 4 with 3 over here. This is going to be the shortest distance we have covered from the 2 to 4 over there. Okay, this is how the things is going to be happen. So when from the 2 bound, when we are going an inbound, so in this case, this will get selected, this will get selected. The 2 of them will get selected. Based on the value, if it is having a lesser distance, we are going to replace that value with the newer value over there. Okay, that is how the things happens. Now we are going to select the next shortest distance, that is 3 over here. The shortest vertex, that is 3 over here. So now when I select the shortest vertex as a 3, I'm just going to replace with the different color. Let's take it as a color called as orange. Okay, let's take this color. So in this case, now I'm going to select the 3 here. From the 3, we are having the shortest distance, that is 5 over here. I can go to 3 to 5 here, right? I can go to 3 to 5. So now, when what is the shortest distance from the 1 to 2 is 3, 1 to 3. This is the shortest distance. 1, 2, 3 is basically we are getting 3. So 3 plus 3 is 6. So this is going to be shortest distance. I'm going to maintain this and I'm going to make it as a 6 over there. Okay. So this is only one thing it is going to get covered over there, right? Because I cannot go from here to here. 1, 3, 2 I cannot go it. 4 plus 1, 5, still 2 is there. So it is a directed graph. It is a directed graph. So 1, 2, 3, this is going to be shortest distance over there. Okay. This is how the things is going to work, guys. So now next, let's select the next shortest vertex, that is 4. Let's select the specific 4 now. So when I select the specific 4, let's see how it is going to be there. So when I select the specific 4, let me come back to the here. Let me select the next color, like let's select the red color, or let's select this specific color. Okay. So when I select this specific color, let's imagine now. Now we are having the shortest distance from 2 to 4 is 9 here, right? Now we are having already shortest distance 2 to 4 is 9. So from here, what all the outgoing bond here? 4 to 6 I can go, right? So already the shortest distance is 9. So already a shortest distance is 9. So 9 plus 1, I can have the specific 10, right? So I can have the specific element that I can have it as a 10 here. So I'm going to tell, okay, 1, 2, 4 I can go. So this is the only path I can go. So or else if I selected the 5, then later it will be different. When I tell it from the source, this is going to be your source, and now this is going to be your destination. In this source and destination, what is the shortest path? So from here to here, the shortest path we are getting as a 9, right? So I'm going to tell here as a 9 to 9 plus 1, it is going to be 10 over here. So I'm going to replace infinity with 10 over here. So this is the next vertex we have selected. Now let's select the specific vertex 5 here. So once I select the vertex as a 5, so in this case, a lot of things might get changed because based on the specific conditions, right? I'm going to select it as a red here. So when I select it as a 5, now let's see what is the shortest distance. So what is the shortest, what is from the 5, we are having the outgoing to 4 and we are having an outgoing to 6 over here, right? So when I go to the outgoing to 4, it is already we are having a 9 here. So if it is 9, so let's imagine from the here. So what is the 4? 4 plus 3 is 7. 7 plus 8, I can have the 9. Okay, this is the shortest way. So again, I can have another condition. So I can go from 1 to 2, right? 1 to 2, what is the shortest distance? That is covered as a 2. That also can be happen. 2 plus 1 is 3, right? 3 can happen here. So shortest distance is 3. So 3 plus 3 is 6, right? 3 plus 3 is 6 here. So 3 is already there and this distance is going to be 6 here. So 6 plus 2, if I go to this 6 happens, 6 plus 2 is 8, 9. So this is the shortest. This is only going to be the shortest over here. This is only going to be the shortest path from 1 to 4 here. That is the shortest one. So again, if I just try to come here, 9 we are having, and this is having a 6 here, right? We are having a 6 here. So again, if I go from 4 to 3 directly, if I went to for the 4 to 3, it was previously it was 3, right? Sorry, 4. So 3 has been happened. 3 plus 3 is a 6. This is already a shortest one. So let's see how what is the next shortest one over here. So if I go from here 4 to say already shortest distance is 6. 6 plus 5 is going to be 11. So 6 plus 5, if I select 5, that was going to be 11. So still 11 is greater than 10. So already 10 is there. So I'm not going to replace with 11 here. This 10 is only better. Okay. Again, it can happen. 6 plus 2 can be what? 6 plus 2 is 9, right? I can have a 9 here, the shortest distance. So 9 plus 1, 10. So 10 is only going to be the shortest distance over there. So this is the specific shortest distance to cover up. This is going to be the shortest distance to cover up the specific entire, so from the source to destination over here. So if I try to write the final conclusion for it, so if I just tell you write the conclusion, so from the vertex 1 to the vertex 2, the shortest distance is going to be 2. So from the vertex 1, the source to destination 3, the shortest distance is going to be 3. Again from the source to the destination, that is 4, the shortest distance is going to be 9. And from the 1, the shortest 1 to specific 5, the shortest distance is going to be 6. Again from 1 to 6, the shortest distance is going to be 10 over here. So this is the specific conclusion of it over there. Okay, so this is how the specific Dijkstra algorithm works. So this is how this very easy. Just we need to replace. First I will be marking as an infinity, then select the each and every vertex, then complete the specific vertex. When I reach it over here, this also will be blocked over there. Okay, so this is the steps you need to follow for the specific Dijkstra algorithm process over there. Okay, so I hope you got it how this is going to be work over there. Okay, this is a specific shortest distance 6 and 9. Okay, so there can be another scenario. So okay, so let's try to understand. So this is let's check for the element number 6 here. Okay, so whatever you are seeing the specific formula, like this is going to be your relaxation formula over there. This is going to be the relaxation formula. So imagine there is a 1 to 6. So basically 1 to 6 they can be still better. Can this specific thing can happen still in a better way? No, this is going to be the final one, right? This is going to be the specific final one. So 6 2 plus basically 2 plus 9 is going to be 11, and 9 plus 1 is going to be 10 itself. Okay, it's going to be 9. So again, if I wanted to reach 4, 4 plus 3 I can have 5. So 4 plus 3 I can have, okay, this 3 for 4 plus 3 sorry, okay, this is the shortest one. 3 plus 3 is 6. 6 is already there. 6 plus 2 is 9. This is only going to be the shortest one, right? So again, it is not going to be changed over there. So this is how the specific thing is going to be in there, guys. So I hope you understood. So we are going to begin with saying the specific 1 to 5 is 9, right? Okay. Yeah. So we are going to see the next specific program, like how we are going to find the specific shortest distance using a Java program. So this is how the things is going to run. We'll verify whether this is correct or not. With the same examples, let's pass the same example, and we are going to verify whether whatever we have solved, whether this is correct or not using the Dijkstra algorithm over there in the using Java program. Now let's come back to the specific Eclipse part over there. So in the specific Eclipse, so let me come back to the Eclipse here. So I'm going to create one specific program for Dijkstra algorithm. So this is going to be there. So I'm just going to create a new specific thing, and I'm going to create a new specific class. So I'm just going to name the specific class as Dijkstra algorithm. Okay. So let's try to add that thing. So I'm going to make this specific a single source shortest path you can use, or else I'm going to tell Dijkstra. So I'm going to tell as a Dijkstra algorithm. So I'm going to create one public static void main. I'm just going to click onto the specific finish over there. Okay. So in this case, let's try to create one Java class, and let's try to see how these things is going to be there. So let me create one specific thing. So let's create one specific. First, I'm going to import the import all the Java packages over there. So this has been imported. So in this specific thing, in this specific class, I'm just going to write one by one. Okay, first I'm just going to initialize the specific vertex value. What is the vertex value should be there? Okay, so let's create the specific vertexes. How many vertexes we are having in it? Let's come back to this example. 1, 2, 3, 4, 5, 6 vertex we are having it, right? So I'm just going to tell the vertex value can be 6 over here. So I'm just going to pass the 6 vertex here. I'm going to pass the specific vertex value is equals to 6 over here. So then I'm just going to write one specific function. So I'm not going to type everything. It is going to take a lot of time. So let's understand with the example here. So a utility function to find the vertex with the minimum distance value from the set of vertices not yet included in the shortest path tree. So basically what we are doing here is we are just going to mark entire sets, entire vertexes to the infinite value. So that is what we did, right? For the initial stage we did for every vertex we mark it as an infinite value to it. So that is what we have done. So the same thing we are doing with the program here. Okay, we are marking as an min value should be maximum and the min index will be -1. Okay, the first one value you are getting. We are just going to do what? We are just going to mark the all the value to the specific maximum values over here. The minimum distance is going to be infinite everywhere. Okay. Then we are going to write one specific another function. Let's try to write another function here. So a utility function to print the constructed distance array. So basically this is going to print the solution. What is the vertex from the distance from source? What is the vertex to the distance from the specific source? Okay. What is the vertex from the distance to the specific source? So this is going to print, okay, the vertex from 0 to this is this, 0 to that is that specific vertex. Okay. That is how it is going to happen. Okay. Now this is going to be another function. Now we need to write this specific function for finding the shortest path. Okay. That is going to be one function. Let's see what is going to be the specific function over there. So for that, let's try to write the specific method. So I have created the method. So in this case, let's see what has been written. So in this case, we created a function called as a Dijkstra function that takes the graph. We need to pass the graph array value and we need to pass which is the source. So basically, we are reaching from source to destination using the single shortest path, right? So the initial specific distance we are just making the shortest distance basically from int of vertex v. Whatever we are just creating an empty array. So what is the distance from vertex to the next node? So here we are just creating one split net. So basically it's the split is set of I will be true if the vertex I is included in the shortest path tree or not. So it means like we did right, first we are selecting we are selecting the vertex 1, then we are selecting vertex 2, then 3, 4, 5, 6. Basically, once we select, then only we can travel from only those specific vertexes. So that is what we have just written it. That is why we are using the boolean value. If it is true, then we are just going to mark that specific max value, then we are going to make it as a false. That means false means we are just initialize all the infinite this SPD set. We have initialized all the distance to infinite, then we are marking one by one, we are marking as a specific thing, that is visited or not visited. Then basically the distance from source to the vertex itself is always 0. Basically the source to vertex is always, it is going to be 0 for the initial way. Then we are just now we are going to run one loop. So what happens? Now it is going to visit every vertex and it is going to mark the specific vertex which has been completed. Then it is going to update the specific distance for the adjacent vertices that is been picked. Now after that, after it is picking it, it is going to match with the condition. So this you can see, whatever you are seeing the if condition, this is the main logic of the program. The thing which we have written it over there. If d of u plus c of distance of u comma v is lesser than d of v, then we are going to make it here. So the same thing you can see here. The distance of v and along with it the graph is not equals to 0, and distance of u is not equals to the maximum value, and distance of u plus graphs of, this is the distance of the vertex u to v is lesser than distance of v. This is the main formula whatever we have written in the specific writing pad. Okay, if the specific distance of u plus graph of u comma v is lesser than distance of v, and these things will be the prerequisite, that is we are going to check whether we are having a maximum value and whether it is the graph is not having 0 values and there is already thing. This condition satisfied, we are going to tell make that specific distance of v to the distance of u plus graph of u comma v. Same formula you can see, distance of v is equal to d of u plus c of u comma v. Here c of u comma v is basically we are making as a graph of u comma v. That's it. Once it is done, we are just going to print the specific solutions over to it. Okay. Now let's try to create one specific graph over there. Let's try to create one specific graph. So that graph I need to write the what is the specific thing. We don't know. Let's see what is going to be this one. So I'm just going to write the specific graph values to it. So let's try to add the specific graph value. So what can be the graph value here? So I need to write this one, right? So let's try to understand what is this specific graph we are having. So for the previously we had we need to write it the weights only, right? So not nothing else. What is the weight of what? Let me write it here. So let's try to create one slide. Let's try to pen. I'm going to use the pen. I wanted to create one adjacency matrix. So what is the adjacency matrix of it? So for this, I'm going to change the specific background to like this. Let's make it like this. That can be better. So I'm just going to tell here we are having a vertex 1. We are having the vertex 2. We are having a vertex 3. We are having a vertex 4. We are having a vertex 5. Again, we are having a vertex 6 as well, right? So we are having from 0 to 6 over here. Little bit, I'm just going to zoom out. So it more. Okay, now it is fine. So I'm going to make like this. Okay, so we are having 1, 2, 3, 4, 5, 6. Again, I'm going to tell 1, 2, 3, 4, 5 and 6 over there. So what is the distance from 1 to 1? It is going to be 0, right? It is going to be 0. What is the distance from 1 to 2? 1 to 2 is the distance we are having in the red color, that is 2. Again, from distance from 1 to 3, the distance from 1 to 3 we are having here as a 4. Again 1 to 4. So 1 to 4 is basically 1 to 4. What is the distance from 1 to 4? Right now we don't have anything, right? So I'm going to give it as a 0 here. 1 to, we don't have a direct, right? So 1 to 5, 1 to 5 also we don't know anything. I'm going to give it as 0, 0 here. Okay. Again 2 to 1. So basically 2 to 1 we don't have. I'm going to make it as a 0. 2 to 2 is also 0. Again 2 to 4, 2 to 3. 2 to 3 we are having. The distance is 1 here. Again 2 to 4. What is the distance between 2 to 4 is 7. So I'm going to mark it as a 7. Again 2 to 5 we don't have. Mark it as 0. Mark it as 0. Again 3 to 1. 3 to 1 we don't have. Mark it as 0. 3 to 2 also we don't have. Mark it as 0. 3 to 3 we don't have. 3 to 4. 3 to specific 4 we don't have directly. I'm going to mark it as 0. What is 3 to 5? 3 to 5 we are having as a 3 to 5 we are having as a 3. Mark it as 3. Again 3 to 6. 3 to 6 we don't have direct. Just make it as 0 here. Again 4 to 1 we don't have. Mark it as 0. 4 to 2 we don't have. Mark it as 0. 4 to 3 we don't have. Mark it as 0. 4 to 4 0. 4 to 5. 4 to 5 is basically having 0. We don't have direct connection, 0. Again 4 to 6 we have, that is 1 here, right? I'm going to mark it as 1 here. Again 5 to 1. 5 to 1 we don't have. 5 to 2 we don't have. 5 to 3 also we don't have. 5 to 4 we have, that is having 2. 5 to 5 we don't have. 5 to 6 we are having, that is 5 here. Okay, then again 6. So 6 we are having, right? So 6 we don't have. 6 to 0, 6 to 1, 2, 3 we don't have directly. So I'm going to mark it as entirely. I'm going to mark it as 0, 0, 0 and 0 over there. We don't have anything, right? So I'm going to mark it as 0. 626, 625 we don't have. Okay, I hope I have created this as in a correct way. So after doing this, now let's try to give the same inputs to the user. Let's try to give the specific inputs, the same inputs in our specific array. So in this I'm just going to tell here the first one, I'm just going to make it here for this one, I'm just going to mark it here. That is going to be 1, and is going to be a second, and again I'm going to make it as a third over there. Okay, so basically 1, 2, 3. So again I want 3 more. I'm just going to make it as a 3 more over there. So in this case, what we are going to do here? So in this case, we are going to get the value. So it is 0, 2, 4, 0, right? So I'm going to tell here as a 0, 0, 2, 4 and 1. So basically I need to give it as a 000. So I'll as 0, 0, 0, 0. This is the first graph. Then 0, 0, 1, 7, 0, 0, 0, 0, 1, 7, 0, 0. Okay, 0, 0, 1, 7 and 0, 0. This is the next one. Then what is the next? That is all zeros, last 3 0. I'm going to tell it as 0, 0, 0, 0, 0, 3, 0. This is the third one per text value. Then fourth one, all 0, last is 1, right? So I'm just going to mark all 0 and last is going to be 1. 1, 2, 3, 4, 5 and 1. This is going to be the last. Then next fourth value is going, fifth one is 000, 205. Okay, I'm going to make it as 000, 2, 0, 5 is the next vertex. So if I just tell what is this, all zeros over there, right? In this one we are having all zeros, 0, 0, 0, 0 and 0. This is going to be the vertex values over there. So I'm just going to mark it like this. So this is done. So once we have created the specific int of graph is done. So I wanted to call the specific Dijkstra algorithm for it. So in this I wanted to pass the graph value and I wanted to start the vertex with specifically, let's assume that is 0 over there. Okay, start with the vertex 0. So once it is done, so there is an error. So what is an error here? The syntax error, delete the specific token. Okay, let's delete the specific token over there. So once I save this, so we have created the Dijkstra algorithm and we have done with the thing. So let's try to execute and let's see what is going to be the distance, what is going to be the output of it. So let's execute here. Guys, you can see here we got the output here. So vertex 0 to 0 is basically 0. The vertex 1 to 1 from we are getting as a 2. So let's verify whether this is correct or not. Okay, so 2 to 3 we are getting it, and from 3 to 8 we are getting it, 6 we are getting it, and we are getting 9 here. So if I just if I just come back to this specific notepad, if I validate here, you can see first vertex 1 will be 0 itself. Okay, if I take the vertex first value, it is going to be for the first starting vertex we have not added here, we have added only 5. So if I take it as the vertex 1, that is going to be 0 itself. Okay, for the vertex 1 to 1 is going to be 0 itself. So if I tell here like if I tell here as for the vertex 1 to 1 is going to be 0 itself. You can see 0, 2, 3, 9, 6, 10. So if I just map here 0, 2, 3, 8, 6, 9. So here 0, 2, 3, 6, 9. 6 is basically for the 5 it is giving. Okay, and then it is giving as a 9. So here 6 and okay, so 1 to 5 is basically having 6. Yeah, this is basically correct. But last one I am getting as a false here. It is telling I should get 9, but I am getting here as a 10, right? So if I just come back to the validate the program, so everything is correct. So 0, 2, 3, 8, 6, 9. Okay, 8, 6, 9 is perfect. So 8, 6, 9 is perfect. But last vertex value it is coming as basically 2, 3, 6, 9. Okay, this is correct, but the last vertex I'm getting as basically it is getting as 10 over here. So there is some mistake I have done it. So let's see what is that specific mistake I have done. So when I just try to come back and let's verify, so I need to get 9 it seems here. Already we are having 0, 6, 9. So let's see what is the specific thing I'm getting it here. Okay, so 3 we are having 3 plus 2 is a 6. So let's see what is the mistake we have done. So if I just validate into this, let's verify this one. Okay, 6, 9. So again we need to check here one more thing, like 6, 9 is there, right? So basically 6 and 9 we need to get it. So after 3, 1 to 4 should be value should be 8, 6. So is there anything that is we are getting? Yeah, you can see here is a false value. We need to get 8 and 6 here. 8, 6, 9 we need to get. But here as a 2, 3, 8, 6, 9 I need to get. Still it is the last 3 values are wrong here, right? The 8, 6, 9 it should be there. So I mean to say this is the value whichever we have seen. Let's try to write it into the red color. I need to get it here as this is, I need to get it as a 8. This I need to get it as a 6. Then I need to get it as a 9 itself here. So basically the distance here is from the 1 to 4 I have some mistake over here. So let's see what is the mistake we are having from the 1 to 4 here. When I come from the 1 to 4, already we have a distance that is 2 and we are having 7. Previously it was 9, right? So I can go from here to here. So distance was 2. This is 3. 3 plus 3 is 6, right? 6 plus 2 is 8. So this is the shortest distance, right? I couldn't update this time. When I have selected 2, 3 and 5, when I was at the fifth specific thing, when I was doing for the orange color, right? Mainly when I was doing for the orange color. So at that case, I have missed one thing, that basically I could have visited from 5 to 1, 5 to 4 as well, right? So I updated to the 6 here, but I didn't update it to this here because this is the shortest. So 2 is the shortest, then 3 was the shortest. So 2 plus 3 is basically 6, right? 6 plus 2 is 8. So I could have updated 8. 8 is better than 9. So I could have updated here as a 8. So I'm just going to update it. So this is getting satisfied. Okay, this we have debugged it. Next we need to have 1 to 5. So 1 to 5 was 6. This is correct itself. This is the shortest distance. 3 to 3, that is 6. This is going to be the shortest itself. That is correct. Then after now coming back to the here. So previously I could have a 6. Previously this was not 10. So previously after this, in this case, I'm going to erase this one. So this is not going to be the 10 output for us. So this is going to be the specific. Then when I'm going to come here, so it is going to be the shortest. 8 is there. It is shortest. 6 is there. 6 plus 5 can be 11. So 8 plus 1 can be 9, right? So 9 can be the shortest one. So this is going to be updated. This is also correct. And this is already verified that is correct. Now you can see unfortunately I did this mistake previously, right? Now you can see we have debugged it. So based on our program, whatever the inputs we gave, that is 0, 2, 3, 8, 6, 9. You can see here 0, 2, 3, 8, 6, 9 is the major correct output for us. So if I just tell here as a, so I'm just going to draw, that is a 0, 3 and 8, 6, 9 is our correct output. So and we have verified with the specific program as well. Okay, that is how we are doing it. So that's all for this session, guys. I hope this session got an amazing understanding for you about the Dijkstra, that is a single source shortest path. In the next session, we are going to look on to the Bellman-Ford's algorithm, and why we are going to use Bellman-Ford algorithm, we are going to discuss over there. Take care. Bye bye. Hey guys, welcome to the section 4, session number 21. So let's understand the Bellman-Ford's algorithm. Even this specific algorithm is used to find the single source shortest path. So this specific algorithm handles the negative weights as well. So for some extent, so if the specific cycle is forming a cycle and if it is not giving you the negative values, then you can find the specific shortest path over there. Then there will be a shortest path exist. There is a two demerits and demerit with the Bellman-Fords. So sometimes it gives the weightage whenever it validates. Will be getting the weightage in the negative ways as well. So that is not going to get handled using this. So and sometimes for this small negligent negative weights, we can handle it in using this Bellman-Fords here. So let's understand how this specific things there. So it's basically similar to the Dijkstra, but there will be a iterations over there. So let's take this specific example for you. Let's take this specific example. Okay. So in this specific example, let's imagine we are going to mark the specific vertexes over there. Let's imagine I'm going to give the vertex names here. So let's imagine this is your vertex 1, this is going to be your vertex 2, this is going to be your vertex 3, and this is going to be your vertex 4, and this is going to be a 6, 5, and specific 7 over here. So let's give the weightage here. So let's imagine this is having a weight 5, this is having a weight here as a 6, 5, and here we will be having here also we'll be giving as a 5. Here let's give the minus 2 as a weight. Here also let's give the minus 2 as a weight, and minus 1, sorry, let's give it only positive 1 here. Let's make it erase it this specific thing. Let's give it only as 1 here, and here let's give it here as a 3. Here let's give it here also 3, and here let's give it as a minus 1. Okay, this is the specific weights which we have given for the specific directed graphs. So the difference between Dijkstra and here is we are having the negative weights here. So how we are going to handle the negative weights here? Let's see this part in this session. So imagine I'm going to write this specific relaxation formula here. So we understood what is the relaxation formula, right? So the relaxation formula was same as it is if the specific d of distance of u plus c of distance of u to v is lesser than the specific distance of v. So if this specific relaxation formula occurs, we are just going to make it the distance of v is equals to distance of u plus c of distance of u comma v. So this is the formula, relaxation formula which we have been used for the Dijkstra. Even here also we are going to use the 7 here. Total how many vertices here totally? So totally we are having these 7 vertices over there. and we need to find there will be a 6 number of iteration over here. So we need to tell vertex minus 1, that is 7 minus 1, that is going to be 6. So basically there will be the 6 iterations here. So in the Bellman Folds algorithm, we are going to have the specific 6 iterations here. So let's write the specific edge list here. Okay, so let's try to write the specific edge lists. I'm just going to tell here as the edge list is equals to, so how many can be the edges here? So 1 to 2 there is a edge, right? So I'm just going to write 1 comma 2 is there is a edge. Then again we'll be having the 1 comma 3 we are having. So I'm going to tell there is a edge between 1 comma 3 and there is a edge between 1 comma 4. I'm just going to tell there is a edge between 1 comma 4. Then let's come back to the 2. So we have a edge between 2 to 5, right? So I'm just going to write there is a edge between 2 comma 5 here. Then 3. So from 3 we are having the 3 to 2 and 3 to 5 we are having it, right? So let's write the same. We are having a 3 comma 2. Then we are having the 3 comma 5. Then we are having a edge for 4 comma 3. Then we are having the edge for 5 comma 7. Then we are having only edge for 6 comma 7. So this is all the specific possible edge list which we are having from the specific graphs. We have written the specific edge list over there. So now let's begin with this specific iteration over there. So let's begin with the first iteration. So I'm going to take it as the blue color for the first iteration. Okay. So I'm just going to tell is as the first iteration here. In the first iteration, so let's imagine for the first iteration, let's have all the infinite values here. So there will be infinite here, there will be infinite here, also infinite value, infinity value, and here also infinity. Also I'm going to write it as the infinite values over there. Okay, the starting vertex value, let's start with 0. 0 is the infinite. So if I just tell if I just apply the same formula, so let's imagine. So this you should be very concentrating, you should listen. Okay, so the vertex first I'm going to check 1 to 2. 1 to 2, what is the distance? We are having 6. 6 is better than infinity, just remove and mark it as 6 here. Okay, let's scratch and mark it as 6 here. Then we need to find for this is done. 1 to 2 is done. Then 1 to 3. So 1 to 3, 1 to 3 we are having the distance is 5. 5 is better than infinity. I'm going to mark it as 5. So this is also is done. Then again 1 to 4. 1 to 4 we are having a specific distance is 5. 5 is better than infinity. I'm going to mark it as 5. So this is also is done. Then 2 to 5. So 2 to 5 is basically we are having the infinity here, right? So if we have a 6 distance, 6 minus 1 will be 5. 5 is better than infinity. Mark it as 5 and just mark it here. Then 3 to 2. So 3 to 2. So 3 to 2, if I have a 3 to 2 is already we are having a 6. So 3 weight is 5. So 5 minus 2 is 3. 3 is better than 6. So remove this 6, mark it as 3 over there and just make it, this is done. Next 3 to 5. So if I just go to the 3 to 5, 3 to 5 already we are having a weight 5. So if I just take it here, 3 was already 5. So I just make it here as a 5 plus 1. If I make it as the 5 plus 1, that is going to be 6. So still 5 is better. So I'm just going to keep as it is over there. So 3 to 5 is done. Then 4 to 3. So if I just make it as a 4 to 3. So if I just tell already we are having a 5 here. Already we are having a 5, right? 4 to 3 already we are having a 5. So here if I just tell 5 minus 2, that will be 3. 3 is better than 5. I'm just going to remove the 3. So I'm going to mark it as 3 here. So this is also is done. Then 5 to 7. So 5 to 7 is been done. So 5 to 7, where is the 5 to 7? So 5 to 7 is infinity. Already a previous weight is 5. 5 plus 3 is going to be 8. So I'm going to mark and I'm going to replace with 8 here. Then 6 to 7. 6 to 7 already we are having 8. So if I just, okay, 4 to 6 we haven't removed. If 4 to 6 I have not added here. So let's try to add the 4 to 6 as well. So okay, let me add 4 to 6. This I missed it. So I'm going to make it here. Let's make it into the black color. So here we have 4 comma 3. Then here also we are having a edge between 4 to 6. Then we are having 5 comma 7. Then we are having 6 comma 7, right? So this is basically we are having it. So now let's come back and take the specific color. Okay. So first let's imagine for the 4 to 6. So for the 4 to 6 we have infinity. 5 minus 1. 4 is better than infinity. I'm going to mark it as 4 here. Then here 6, right? So basically this 4 to 6 is done. 5 to 7 already done. Then 5 to 7 done, right? 5 to 7. Yeah, 5 to 7 was already 5, 8. Okay. Then 6 to 7. 6 to 7 is at a 4 comma 3. 4 plus 3 is basically 7. 7 is better than 8. So I'm going to remove this 8. I'm just going to replace with 7. So this is done. Okay. So 6 is done. So basically the first iteration is completed over there. Okay. This is the first iteration is completed. Now we need to perform 6 more iterations over there so that we'll be getting the minimum cost of it. We're going to get the minimum cost and minimum short steps over there. So now we are going to use the color, like let's use the specific purple color now. Okay, so let's imagine I'm going to use the purple color. So let's use the specific purple color. So again from 0 to 1. So again I need to follow the same path. So I'm going to tell 1 to 2. So 1 to 2 is basically having 6. So 1 to 2 is already having a weight 3. So this is a shortest. I'm going to make it as correct. Okay. Again 1 2 3, 1 2 3 already we are having as a 3, so 3 is the better, so 3 is better, right? So that I'm going to keep it as it is. Again 1 to 4, if I tell as a 1 to 4, 1 to 4 already we are having a 5, the 5 is better accordingly. I'm just going to make it as correctly, okay. Then again I'm going to make it as 1 to 1, then 2 to 5, right? So 2 to 5, so 2 to 5 is already we are having a 5, so if I just reduce it, so 3 minus 1 will be 2, so I can reduce to 2, right? So I'm going to make it as 2 here. I'm going to remove and going to replace with 2. Again 3 to 2, so 3 to 2, 3 to 2 is already a 3, so there are previous distance we have a 3, so 3 minus 2 is going to be 1, 1 is better than 3, so I'm going to remove this, I'm going to mark it as 1, so this is also been excluded. Then 3 to 5, so 3 to 5 is already we are having 2 here, so again if I just tell 3 plus 1 will be 4, still 2 is better, I'm just going to keep it, still 2 is better, right? I'm just going to keep it better, so I'm going to keep that thing as it is. Then 4 to 3, 4 to 3 if I just make it, the 4 to 3 if I just have a look on a 4 to 3, so 5 minus 2 is 3, 3 is still better, I'm just going to keep it here. Then 4 to 6, if I just make it as a 4 to 6, so already 4 is there, if I tell here a 5 minus 1, that is going to be 4, still 4 is better, so I'm going to keep it 4. Then 5 to 7, 5 comma 7 is already a 7, so previously it was 2, 2 plus 3 is 5, so 5 is better than 7, right? So I'm just going to replace 7 with 5 over there, okay, this is good, done. Then again 6 to 7, 6 to 7 is a 5, so 4 plus 3 is 7, so still 5 is better, so I'm going to keep it 5 itself, so I'm going to keep it, this is the shortest one, we have kept it. So the second iteration is also completed, okay. So we'll do the next iteration over there. So in the next iteration I'm just going to choose the specific color with the specific let's take it as a red color itself, okay, or anything like this, okay. Let's take the black color now. So for the third iteration I'm just going to choose the black color, okay. So in the black color now I'm going to tell as a 1 to 2, so 1 to 2 will be having remaining same, so 1 is there, this is I'm not going to change. Again 1 to 3, 1 to 3 is basically having 3 is the better, I'm going to keep. 1 to 4, 1 to 4 is already a 5, I'm not going to change anything, let's keep as it is, okay. Then 1 2 to 5, so basically if I come as a 2 to 5, so now in the 2 to 5 if I just tell 1 minus 1, that is going to be 0, so 0 is better than 2, so I'm going to make it as a 0 is the shortest distance, so I'm going to replace 2 with 0, that is done. Then 3 to 2, so if I just make it as a 3 to 2, so 1 is there, so if I just tell 3 minus 2, that is 1, it is not going to change, keep it as it is. Then again 3 comma 5, so I'm going to tell 3 comma 5, so 3 comma 5 is 3, 3 was there already, 3 plus 1 4, so 0 is better, keep as it is. Then 4 to 3, so if I just make it as a 4 to 3, so 4 to 3 is basically 5 minus 2, 3 is better, I'm going to keep as it is. Again 4 to 6, so 4 to 6, 5 minus 1, 4 is better, keep as it is. Then 5 comma 7, basically we have a 0 weight, so 0 plus 3, so 3 is better than 5, right? I'm just going to replace and remove it 5, I'm just going to replace with 3, 3 is better, keep it as it is, 3 is better, so I have replaced it. Then 6 to 7, so 6 to 7 is we are having a weight here as 3, so 4 plus 3 is 7, still 3 is better, so I'm not going to change anything, this is the third iteration is completed, okay. So let's come back with the fourth iteration. So in this specific fourth iteration I'm going to choose this specific color, so in the fourth iteration now let's see what if we get any kind of a change or not. So let's imagine how we are going to get it here. So in this fourth iteration now I'm going to tell here as a 1 to 2, is there any change? No, we can see 0 to 6, 1 is better, keep as it is. And 1 to 3 we are having a 3, so 3 is better, keep as it is. Again 1 to 4, 5 is the best cost for it, so we don't have any change, so I'm going to keep as it is. Again 1 to basically next 2 to 5, right? 2 to 5 is 1 plus 1 minus 1, 0 is only there, no change, keep it as it is. Again 3 to 2, 3 to 2 is having 1, so if we do again like 3 minus 2, 1 only will get, no change, keep as it is. Again next 3 to 5, we are having a 0, so basically if I do 3 plus 1 4, still 0 is better, keep as it is, no change. Then 4 comma 3, so 4 comma 3, if I just tell here as a 4 comma 3, that is a 2, 4 comma 3 is basically a 3 here having 5 plus 2, that is 3 is going to remain, no change. Again 4 to 6 is already 4, 5 minus 1 4, there is no change, keep it as it is. 5 comma 7, again 5 comma 7, 0 plus 3 only will be there, no change. Again 6 to 7 is 4 plus 3 7, still 3 is better, keep same, so no change. So here in the fourth iteration we are not getting no change over here. Same way it will run for the fifth, sixth as well. Basically 4 5 6 there will be no change, so definitely this is going to be your final output, this is going to be the final result. So this is the best way I have explained you guys. I hope there is no confusion here. So let's try to write this specific final result for you. So let's try to write it into the some color, like choose this purple color, okay. So I'm going to tell here as the specific final result. I'm just going to tell final result the vertex. So I'm just going to make it as a vertex. Here I'm just going to make it as a weight. So what is the vertex weight for 1? The vertex maximum weight is going to be 0. So for the vertex 2, so I'm just going to tell for the vertex 2 the maximum weight is 1, is going to be the maximum weight 1. And for the specific vertex 3, I'm just going to tell maximum weight is going to be 3 here. And for the vertex 4, the maximum weight is going to be 5. So for the vertex 5, the maximum weight is going to be 0. For the vertex 6, the maximum weight is going to be 4. The vertex 7, the maximum weight is going to be 3. So this is going to be your final result. So this is how, guys, the Bellman-Ford algorithm is going to work. So now let's understand and verify with the specific Java program. So in this specific Java program, let's see how the Java program is going to be there. So let's come back to this specific Eclipse. So I'm going to give you this all these specific pictures so you can have a look and you can practice it. So coming back to our Java program here. So this is basically previously we did for Digistra, right? I'm going to create a new specific Java class. The Java class name I'm just going to make it as a Bellman-Ford. Okay. I'm going to create a public static void main. Let's click on to the specific finish part over there. So inside it now in this specific program, let's try to create the specific Java part over there. Let's see how the program is going to be there. So basically that's very simple, like how we have given created for the Digistra. Same thing even here also the logic is going to be there. Just there will be the number of iteration will be more. Okay, and it is going to handle the negative weights as well. So here I'm just going to first import the specific java.util.star package. Then I'm just going to create one more class inside it, and let's try to create one class to represent the weighted edge kind of a thing. So here I'm just going to come back here. So I'm just going to create one specific class, that is a Bellman-Ford algorithm is the class. And here I'm just going to replace, I'm going to just tell here in this specific class we are just representing the source to destination and what is the weight, we are declaring it. And we created a constructor. Whenever the construct class edge will get called, we are just making the, for the initialization, we are just making the source destination weights value is equals to 0 over there. So it is all about the game of vertex and the edges, right? So I'm just going to initialize that specific here. I'm just going to initialize v for vertex is going to be the edge, and I'm just going to use the edge concept here. So I'm just going to use the specific edge is going to be the initialized with the entirely with the weight 0 and everything will be 0 here, empty array. Now I'm going to create a graph with the vertex and the edges. Okay, so let's create a graph using the vertex and the edges, whatever we have getting. So Bellman-Ford algorithm, whenever I call this method, we pass the vertex v and the edges. So whatever the vertex value will be there, whatever the edges will be there, we'll pass it. And whatever the new edge, whatever the edge we will be creating, so we are going to run the loop. Whatever the edges values, whatever the vertex and edges value will be there, we just created specific graph. Still we are not adding any kind of a weights here, just we are creating a graphs like vertex with the edges over there, that's it. Okay, then the specific main functions comes into the picture. So there are a lot of steps where we will be having. So let's try to write that specific method, right? Okay, so the main function of the Bellman-Ford algorithm. So here I'm just going to paste it. So what is the main function here? So basically you can see we have just created a Bellman-Ford as the main function. This basically takes the source and we need to go to the destinations, right? So the starting initialization of distance we are making of the vertex v, whatever the value of the v. The first step is going to be, we need to initialize the distance from source to all other vertices as the infinite. That is what we did, right? The first iteration, in the every first iteration, whatever the first value of the all the vertices distance, we made it as the infinite value to it. So once we made the infinite value, then we are just filling all the array with the maximum value of it. Okay, then in the step 2 we need to relax it. First we need to take one vertex and I need to just visit all the vertices. I need to just visit all the specific vertices based on the formula. These are edges, right? In for you need to visit all the edges. I need to update the what is the minimum weight that can be there over there. So this loop is going to do what? From the source to destination, it is going to update the weights. You can see it is going to update the weights. And again the same formula comes into the picture. This is a relaxation formula, right? See, distance of u plus the weight is less than distance of v. We are going to make distance of v is equals to distance of u plus weight. This is the main formula of your program, right? So based on this only entire thing is there. So this is the things we have been updated. Now here there is another step. Still here it is similar to the Digistra, but there is an extra step here is checking the negative weight cycles here. So whenever I am evaluating it, I should not get any negative values here. See, whenever I am evaluating it, even the edges can be negative. That is only handling the Bellman-Ford. But whenever there is a weightage, whenever we are evaluating the weight should not be the negative value, right? If it is getting a negative value, then that will be the demerit of Bellman-Ford, and that will happen in few cases. Okay, so this is, you can see, we are just checking for the negative cycles. If it is getting a negative weight, I'm going to tell the graphs contains the negative weight cycle. Okay, and I'm going to stop the program. So suppose this program while running, if there is a graph getting a negative weight cycle, then I'm just going to stop the program by telling negative weight there is a containing. Okay, or else I'm just going to simply print the specific distance of it over that. That's it. Okay, so this function is just basically prints the specific things over there. Now I'm just going to, let's try to create one formula. Let's try to create a new one over there. So we have a vertex of it. Let's tell the number of vertex will be, let's try to tell there is a 5 vertex. Imagine there is a vertex, we are having a 5 vertices and we are having the 8 edges over there. Okay, in the 4 v is equals to 5 vertices and we are having the number of edges in the graph, there is a 8 over there. So I'm just going to initialize the Bellman-Ford of it. I'm just going to tell Bellman-Ford algorithm, I am going to initialize a graph for it. So here I'm just going to add the what all the edges I need to see for all these graphs over there. Okay, so once I just pass it, I'm going to pass all the distances, like I'm just going to create a graph and I'm going to pass the values to it. So I'm just going to pass the values. So now see, this is the values we have passed it. So here I can tell, so from the vertex 0 to 0 will be source to destination will be there, the weight is negative -1, 0 to 2 will be 4, and 2 to 1 to 2 will be 3, and 1 to 3 will be 2, and this basically we are just passing the edges. This same thing we did it for I guess in some other Kruskal's or Prims I have shown you with the same thing, right? I think in the Kruskal's algorithm we used it, right? So there I have shown you how this is going to be there. So you can just again, there is a one assignment for you guys. You can, the example which we have created here, you guys can do what? You guys can use the same weightage and create a graph and solve. First you need to solve with the paper, and once you get the final output, then you can verify with the program. Okay, that is absolutely that is going to be working over there. So here it is giving me the error. It is telling me here what? Insert the, okay, I need to insert another block body. Okay, let me insert it like this. Okay, now it is fine. So once I just save it here, so I think I need to save it here, this specific graph I need to save it onto the top here. I'm just going to close with the program here. Okay, so I hope there is no error. So basically there is some error. So what is the error? I'm getting it here. I'm going to remove this. So we are having the two closing tags over there. So if I just go to the public static void here, right? So yeah, this is all the things is having correctly. So still I'm getting an error, right? So there is somewhere I'm not closing the brackets over there. So this is correct and all the things is perfect. Basically we have just created the public static void main, and we are having the graphs over here. Let me remove this. Okay, still it is there. So I think from the top I have removed from somewhere. So we have this, and we have been getting closed here. Okay, so let's see what is an issue. So let's save this one. Okay, so we created a graph and we are having all this thing, but here it is giving an error. So let's see what is an issue. So I'm going to close. Let's check what, where we are not closing the stuff. So basically in this case, right, so we just created the, we have given the graph weightage and whatever the source to distance and what is the weight value. Now we need to find the specific from the source 0 to all the vertices, what is going to be the output for it. Okay, so that is what we need to do it. So there is going to be the public static void main, so it takes strings and all those stuff. So this is the one thing. So now let's see what error we are getting it here. We have run the loop here also, everything is done. So what here it is showing here, what is giving me here is syntax error, insert insert this to complete the class body. It is asking me I need to use this to complete the class body. Okay, if I give like this, I think there is an extra flower brackets. So where is the extra flower bracket? It is having somewhere here. So it is having one, and I'm just going to remove from here. So I'm going to remove from here. This correct itself. So somewhere I have given the extra bracket. So this loop is getting ended here. So this specific loop is starting here, and this is ending here, and this is starting here, this is ending here, and whichever it is ending here. So this specific loop where it is ending. So this is not ending, right? So this specific loop is not ending at all. So what we need to do, we need to add another I need to end this specific loop, right? So here I need to return it. So once I return, these two things are getting, this is getting ended, this also is getting ended. It is correct, and I guess here somewhere I have missed it. So here if I just go to the top, here it is not there. So here let me debug and resume the video. So yeah guys, so I have removed there was one top extra thing, so there was a two different classes, so I removed this Bellman class. One class was extra, so I just removed that and replaced with the Bellman fold. Okay, so because this is a class name we have kept, right, so we have just replaced all everywhere that is as a Bellman fold, and there is an extra class Bellman fold algorithm, so I have removed it. Okay, while pasting, copy pasting, it has been created an issue. Let's try to run execute this specific program. So once I execute this specific program, let's see it is working. Yes, exactly, it is working fine. So you can see it is giving from 0, 1, 2, 3, 4. Specifically, it is giving you the weightage over there. Distance from 0 to 0 will be 0. Distance from 1 to 0 to 1 will be -1. Distance from 0 to 2 will be 2. Distance from 0 to 3 will be -2. Distance from 0 to 4 will be 1 over there. Okay, so this is basically a drawback of a Bellman Ford algorithm. Okay, so which is gives the negative weights as well, and the drawback again, if there is a negative cycle, basically it is going to stop it. So if the graph contains the negative weight cycle, okay, imagine there is no positive itself, everything you are getting as a negative, it is going to give you the negative weight cycle over there. Okay, this is how the things is going to work. So I want you guys to validate this specific program. Like let's create what is the adjacency list. I'll pass after adjacency list, pass getting you the, once you get the adjacency list, you need to replace these things. You need to start with, okay, you can just tell here as a source is 0, destination is 0. Source is 0, destination is 0, and what is the weight. So you can just pass the weights here. So if I just pass here for the 1, I can just tell 1 comma 1 comma 0 is your weight. Okay, then next if you pass it as a 2, so basically from the source, that is source to destination, basically that is from the 1 to 2. So here wherever you are having looking as a 0, that you should start with 1 here according to our example which we have solved. Okay, so that is 1 to 2 is going to be basically 1 to 2. What is the weight? The 1 to 2, the weight is 6, so you need to make the specific value as the 6 over there, like that. Okay, so I hope you have understood this session. So let's begin with the next session in the next session. So thank you guys, take care, bye bye. Hey guys, welcome to the section 4, session number 21.2. So let's look onto the drawbacks as Bellman-Fold algorithm, that is onto the single source or shortest path. So we saw already the Bellman-Fold algorithm, so where we are going to reach from the vertex 1 to the vertex n, so where they are going to relax all the specific vertices on specific iterations. So if we are having a 6 vertices, we are going to do the 6 minus 1 iteration for the relaxation. So whenever we are doing this, Bellman-Fold says the last 2 iteration values will remain same. It is not going to change. The whatever the shortest cost is, it is going to be that. But if we are having a negative value, so the Bellman-Fold algorithm also resolves this, but for few of the cases, it is not going to resolve as well. So if you are keep on doing the iterations, keep on, the values will get changed into a negative value. So that is one of the major drawbacks of Bellman-Fold algorithm. So let's begin with one specific example over there. So coming back to my specific writing pad over there. So let's take one specific example and understand how it is exactly it is going to be the specific problem in the Bellman-Fold over there. So if you take one example, so let's have an example over here. So I'll just select one specific vertex, so 1 over here. Okay, and we are going to have a specific vertex 2 here, and we'll be dating here as a vertex 4, and I'm going to rate it here as a vertex 3 over here. So now I'm just going to draw one specific vertices over there. So imagine we have a specific vertices over here to here, and we have a specific path from here to here, and here to here, here to 4 to 3 we are having it, and we are having a specific things over here. So here I'm going to tell here the values I'll be giving cost. From 1 to 4 the cost is going to be 5. So from the 1 to 2 the cost is going to be 4, and from the 4 to 3 the cost is going to be 3, and 2 to 4 the cost is going to be 5 here, and the specific 3 to 2, let's give the cost here is minus 10 over here. Okay, so we are given some negative values here as well. So for the starting, so the vertex 0 will be having, so for the all the vertices value I'm just going to give the infinite value 4 over here. Okay, so now we are going to see first what all the edges are there here. So what all the edges are we are having it. So for relaxation we need to find what all the edges we are having, right? So for the relaxation we are having a basically a 4 vertices. So the value it can be up to specific 3 iterations, right? So 1 4 2 minus, that is 3 is going to be there. So for n minus 1 value is going to be 3 here. So let's see all the edges over here. So the edges we are having, that is 1 comma 2 is the one edge, 1 comma 2 is the one edge, and 1 to 4 is another edge here. Okay, so these are the two things we are going it. Again we are having from 2 to 4, and 2 to 4 is the another edge we are having it, and again the edge again we are having, that is 3 comma 2 we are having. This is the another edge, that is a 3 comma 2, and again we are having a 4 comma 3 we are having. So I'm going to write it as a 4 comma 3. So these are all the specific edges we are having inside the specific scenario. So let's take example and try to relax this specific thing over here. Okay, so first I'm just going to relax from the 1 to 2 over here. So for the 1 to 2, what is the cost we are having? We are having 4. I'm just going to, 4 is lesser than infinity. I'm just going to update the value of 4. Again from the 1 to 4 we are having the infinity, so the relaxation is 5, so I'm going to make it as a 5. So this also is done. Again 2 to 4, so the 2 to 4 we are having the specific value here as 5 is the cost, already is 5 is present, so that is the minimum, so I'm going to keep as it is. Then 3 to 2, so 3 to 2 we are having the cost of 4, right? So what we are having, the cost here is 4 we are having, that is a 3 to 2. So already the cost is 4 here, and here we are having a minus 10 here, right? So when we are having a cost is equals to minus 10 over here, so which is the lesser, minus 2 minus 10 or 4 is less, so minus 2 minus 4 is going to be less, right? So that is going to be the first scenario. But here right now we are just taking the vertex number 1, so I'm just going to keep it as it is, that is minus 3 comma 2. And 4 to 3, 4 to 3 we are having as a 3, so 3 is better actually. 4 to 3, 4 to 3, 3 is better than infinity, so I'm going to update the value here as a 3. So this is also has been completed over there. Okay, so this is the first scenario over here. So you know, right, what all that is our Bellman Ford algorithm is going to say. So let's specifically note down those specific points here as well over here. So we are going to unable to solve the specific values of n minus 1 over here, right? So basically this specific thing, what happened, the drawback here is, so the minus of 1, the basically whatever the negative value items will be there, so it is going to be solving is little bit, solve is critical over here. Okay, this is the one specific major point into the Bellman Ford drawback. So if I'm going to tell here one condition, if the specific if the cycle is formed, if the specific cycle is formed and has the negative value, if the cycle is formed and has the negative, right, then this algorithm doesn't fall. This algorithm, if this algorithm does not solves over here, this is the major point. Okay, if the cycle is getting formed, again it is having a negative value, this specific algorithm is not going to solve over here. So now let's see this thing with the proper example over here. Okay, so this I'm just going to keep it a little bit of it bottom over here, so I'm just going to keep it over here. Okay, so here the value was already a 5, I'm just going to update properly, so the value was here as a 5 here. Okay, so now I'm just going to update this table also little bit to the bottom over here. Okay, so now it is fine. Now let's see the second iteration now. So let's take an example for the second iteration. So for the second iteration, again I'm going to tell 1 to 2. So 1 to 2, 4 is already a smallest path, right? So 4 is already a smallest path, so I'm just going to keep it as a 4 itself. Okay, so it is going to be 4, so that is going to be again now 4 itself. Again 1 to 4, so for the 1 to 4, 5 is already path, the 5 is already is there, so I'm going to keep it 5 itself already. So again I'm just going to keep it 5 itself, so it is also done. So then 2 to 4, so 2 to 4, so 2 to 4 we are taking the second as a relaxation time, right? So 1 is been relaxed over here. So now second iteration 2 to 4, 2 to 4 is already 5, so the same thing will be there, 5 will be remain as it is. Again 3 comma 2, so 3 to 2 we are having a 4 here, right? So we are having the specific value as a 4 over here. So if I tell minus 10 and 4, what is the value we are going to get here? So minus 4, if we are going 3 to 3 to 2, if already we are having a value here as 4, the relaxation value is 4. If I pass minus 10 and minus 4, what is the value is going to get? 6 we are going to get, right? So still 6 is 4 is better than 4. Okay, 4 and minus 10, what is the value of 4 and minus 10? It is going to be minus 6, because 10 is having the minus sign, so 4 is minus 6, right? Minus 6 is better here, so minus 6 is going to come here. So this 3 comma 2 is also there, and 4 to 3, so 2 to 4 we have done. Yeah, 2 to 4 is already okay, 2 to 4 is done. So then again 3 to 2 is also done. 4 to 3, 4 to 3 we are having 3, so 5 minus 5, so still 3 is better than 3 itself. So 3 is going to remain as it is over here. Okay, so 3 is going to be remain as it is. So this is the second period is also is going to be done over there. Okay, so this is going to be the relaxation time over here. So 3 is better for 3 is already is going to be better. So that is already it is going to keep. So this is going to be the second iteration. So now let's take another example over here. So let's take an yellow, like take it as this purple color. Now, so 1 to 1 to 2. So 1 to 2 is what 4 value here, right? So minus 6 is better. So minus 6 as it is, I'm going to keep it. Again 1 to 4. 1 to 4 we are having as 5. 5 is already there. So I'm going to not change. Again 2 comma 4, that is 2 to 4. So for the 2 to 4, we are having an element that is 2 to 4 we are having, that is a 5. So 2 to 4 value is 5, right? So the cost, what is the cost, I can say. So the cost is minus 6 here, right? The cost is minus 6. Minus 6 plus the cost is from 2 to 5 is already the better. So from the cost from here to here is minus 6. So minus 6 and 5, it is going to be minus 1, right? So it is going to be minus 1. So minus 1 is going to get changed. So it is going to keep as it is. Then again the cost of 3 to 2. So cost of 3 to 2 is minus 6 already. So if I have the 3 to minus 10, what happens? Minus 6 only is going to remain. So it is also that this is better than that. So I'm just going to keep as it is. Again 4 to 3 is 3. So here it is going to get changed. Minus 1 and 3, it is going to change it to 2, right? So it is going to be changed to 2. So I'm going to change again, the value is going to come over here. Okay, so this is another iteration. So the 3 iteration is done, right? So according to us, the how many vertices are that n minus 1, that values again after this the value should not get changed. So now you can see again the values is going to get changed again. So 1 to 2. So basically if I take 1 to 2, so already 0 cost for 0 plus 4 for minus 6 is as it is better. So I'm going to keep as it is. Again 1 to 4. So for the 1 to 4, what is the cost? That is a 0 minus 1. What is the cost? 0 minus 1, minus 1 only is there. So it is going to keep as it is. And 2 to 4. And 2 to 4, the cost is already minus 1. So here is minus 6. So minus 6 and minus 6 and 5, minus 1 will be there. This is going to be same. Again 3 to 2. So 3 to 2 is basically a minus 6. So 2 minus 10 is minus 8. I am going to get the value, right? So 2 minus 10 is minus 8. See here you can see again the value is getting changed. So it is going to keep on happening. Again 4 to 3. 4 to 3 is 2. The cost is 2 here. Minus 1 minus 3 is going to be 2. So this is better over here. So you can see here the specific cost is getting changed here. So again if I try to write another one more iteration, that is a 1 to 2, we are having the cost that is minus 8. The 1 to 2, the cost is minus 8, right? So it is going to not change. Again 1 to 4. 1 to 4 is 0 and minus 1 here is, it's not going to change. And 2 to 4. So 2 to 4 you can see again the value will get changed. So minus 8 is there. Minus 8 and 5 will be minus 3. So minus 3 is better than minus 1. So you can see it is getting changed here again. So this keeps on happening it. So that is, it is not going to not solve the specific problem, not solve the specific problem, because it changes the cost even the relaxation is done. Okay, even after the relaxation of vertex is done. Okay, even the relaxation of vertex is done for the n-1 iteration, this specific problem is not going to get solved, because this even though after the relaxation is completed, it is not going to solving over your problem over there. So this is the major drawbacks of Bellman-Ford algorithm. So that's all for this entire session. Take care. Bye bye. Hey guys, welcome to the section 5, to the nonlinear data structure, that is trees. So in this specific entire section 5, we are going to look on to the trees. We are going to see how the tree is going to be there, and what all the terminologies of trees, how the tree is going to get represented, and what all the traversal methods we have in trees. We are going to see the binary trees and binary search trees, AVL trees, and much more into this entire section. So it is more on the theoretical part. So it's a very amazing concept in trees, and it's related to kind of a tree family, tree structure, and where we are going to learn a lot of things over here. So let's begin with this first session to the introduction on it. Basically, trees basically plays a very crucial role in data structure. Why? Because it is a non-linear data structure concept. Okay, because whenever we take any specific various applications, this tree concept is being used over there. Okay, based on the tree hierarchical structure, this specific things is going to get assigned. So imagine there is a network, Airtel tower, Geo tower, and all. So how the specific network is going to reach to your phones? Okay, it's basically they use the concepts such as like a tree concepts they are going to use there, tree DSA concept they are going to use there. So that how you are going to connect. So basically you are going to act like a nodes to them, and what are the connections will be there, it is going to be act like an edges. So where they are going to mainly use kind of a trees over there. Okay, this will be trees basically connected with the nodes and the edges in a specific and hierarchical manner. That is going to be called as a trees over there. What are the main terminologies of trees? So we have a root, we have a parent, child, leaf, internal node, depth, height, siblings, ancestors, and so on. So we're going to understand one by one what is root, what is parents, what is child, what is leaves, internal node, depth, height, siblings, and ancestor. So it's something we have, right, kind of a family, right? So that's why the tree is going to call as something like a tree family structure. Okay, so they are all names that is belongs to the family names. So let's see with an example over there. Coming back to my specific notepad over there. So let's begin with one specific all the example, like what is trees, what is specific parent, what is node, and all those things. So for that, let's begin with the rating pad. So I have created one specific example for the tree over there. So I have created one specific example for the tree. So let's imagine how it is going to be there. So if I take here, if we take this specific example of a tree, so let's name these specific nodes, and let's name it some numbers over there. Let's tell here this is something a 9 number, let's take it here as a 10, let is your 12, it is going to be your 15, this is going to be your 9, this is going to be your 8, 7, 6, 4, and 3 over here. This is going to be your number in the numberings for this. Okay, so now let's be write the specific names for the node. Imagine this is your node A, and this is going to be your node B, this is going to be your node C, this is going to be your node D, and it's going to be your node E, and I'm just going to tell this is going to be your node F, this is going to be your G, this is going to be your H, and A B C D E F G H, and it's going to be your I, and it's going to be your J node over there. Okay, this is going to be your nodes over there. Okay, imagine this is your specific nodes. So basically first the terminologies which we discussed, right, that we said I'm going to little bit reduce the thickness. So imagine the first I was talking about the what is root, right? So root is basically the topmost of your node. So what is meant by root? That is basically we are going to tell it is going to be the topmost node. So in this specific tree, which is the topmost node, this is your 9 is the specific topmost node. So this is going to be declared at the specific root over there. So in this case, the specific the node 9 is going to be the topmost node. That is why we are going to call it as root. Okay, that is going to be the root node over there. So in the second point, we discuss something what is parent. So whenever we talk about in the real world, if we call they are the parents, that means they will be having the children's, right? That's why we are going to call the who has children's, those parents, we are going to call it as parents, right? So even here as well. So 9 is the parent of 10, 12, and 15. And again 10 is the parent of 9 and node 8. Again the node C is the parent of nodes G and H. D is the parent of node I. J is the parent of node I. Sorry, J is the child of node I is the parent of node J. So like this. Okay, so whatever these things we are having, so basically a parent who has children's more than one children, that specific node is going to call as a parent node over there. So we can just mention node which which connects the child. Okay, I'm just going to mention which connects the child. That specific node we are going to call it as the parent over here. So if we can, in this case, what all who all the specific parent. So I can say something like example, A is the parent of, A is the specific parent of node that is B, and the node C and the node D. So this is how we can say it over there. Okay, again node C is the parent of, node C is the specific parent of G comma H. So this is, you can point it over there. This is and so on over there. This is going to be your parent node over here. So let's imagine what is the child. So child which connects by the another specific node, right? What are the childs over here? The child is basically, so 10 BCD is the child of A, EF is the child of B, G and H is the child of C, right? And I is going to be the child of D, and J is going to be the child of I. So this is going to be taken over there. So this specific definition we can tell node which connects another node, right? Node which connects another node. Basically this node is connected by another node, this is connected by this is connected by this. So these all nodes can be treated as the child nodes over there. Okay, so then we have something called as a leaf node here. So we have something called as a leaf or external node. I can just mention leaf or the external node. What is mean by leaf or the external node? Node which doesn't have child. Okay, node, I can just mention node which doesn't have child. Such node we are going to call it as child node over there. So in this node we can treat it, this is as your one of the child. E is your child, F is your child, G is the G is your another node which is not having any childrens. Again H is not having any children, and J is not having any children. So basically in your entire tree structure, the last nodes which will be having, those nodes we can treat it as the leaf node. So for such node there won't be any kind of a child over there. Okay, so in this case what all the specific scenario will be coming. So E is your the specific leaf node, F is the leaf node, again G comma H comma J, these all are your child nodes over there. Okay, the next comes under the leaf is there. So then we have something called as an internal node. So what is internal node? Internal node means a specific parent, a node which has at least one child. Okay, if a specific node is can call as an internal node if the specific node has at least one child here. So in this case I can call the specific I is your specific internal node. Even D is also your one specific internal over there. Okay, it can be at least means they are saying at least one, it can be more than one other, at least minimum there should be one child. Such nodes can be called as the specific internal nodes over there. Okay, this is the one of the main terminologies inside the tree. So I can mention the node which has basically an at least one child. Such nodes we are going to call it as a internal node over there. So in the same way we have something called as a depth over here. So number of edges from the root to the node. If I call about the number of edges from the root to the node, so if I talk what is the depth of here, if I just talk here the number of nodes from the root to the specific number of edges from the root to the specific node. If at all here, this is a one edge, this is the two edge, and this is a three edge. This is going to be called as a depth of the specific tree. Okay, this is going to be depth of the specific tree over there. Okay, so then I can just tell here the definition, the specific number of edges basically from the root to the node. Such kind of things we are going to call it as the depth over there. Okay, so again we can see here, so what all the edges, how many edges we are having, how many depth. So if I talk about for the specific E, let's take an example for the node E, how many edges we are having from the root. So from the root to the E we are having 1 and 2, so we can just tell we are having the specific 2 edges over there. Okay, again if I talk about the J here, if I talk about the J, how many edges we are having, we are having the edges that is going to be 3 over there. If I talk about the node H, we are having the 2 edges, so that I can call it as this is going to be the depth of the specific tree over there. Okay, so this is how we are going to call over there. Then next again we have something called as a height. We are having something, we named it something as a height also. Height is basically the node from top to bottom, what is the height of it. So I can just tell this is going to be your 1. So I can just tell here as this is going to be 1 dash, and these nodes again I can just tell, I can divide, this is going to be another, and I can just tell this is going to be your the next height, and I can just tell this is going to be the here. Okay, I can just name it. Okay, this is 0, this is going to be 1, this is going to be the 2, this is going to be 3. So the height can be maintained as, this is the height of the specific tree is 3 over here. This is the another specific terminology inside the trees over there. Again I can just talk about the another thing called as a ancestors. So ancestor, if I talk about the J's ancestor, who is the J's ancestor? So J's ancestors comes the root A, right? The topmost of it goes to the, and root A, D is going to be the ancestor. A and D is going to be the ancestor of the node J, because I is the parent of J and D and A is going to be the ancestors of it. Again, if we talk about the node H ancestors, C is the parent of the specific H and the A is going to be the ancestor. The topmost, what are the ancestors, right? Even in the family, what is mean by ancestor? Our grandfathers and fathers. So such things will come under the ancestors over there. That is what we are calling over here in the same in the trees as well. The next thing we have another terminology, something called as a siblings over there. So what is meant by siblings? Siblings are basically sisters and brothers, right? If I talk about the what are the siblings of B? So if I talk about the siblings of B, in the siblings of B, C comma D is the siblings, because they are the belongs to the single parent, that is a node A, right? C and D is going to be the siblings of the node B. If I talk about the F, E is the sibling of F. If I talk about G, H is the sibling. If I talk about I, there is no sibling. If I talk about J, there is the no specific siblings over there. Okay, so this is all about the specific main terminologies of the specific trees and the specific terminologies. So in the next session, we are going to discuss with the new concept. Take care. Bye bye. Hey guys, welcome to the section 5, session number 23. So let's discuss about the binary tree and its specific type over there. So what is meant by binary tree? A binary tree is a hierarchical again data structure concept which node has at most two children. A node which has at most two children, those specific trees we are going to call it as the binary tree, which are refers to as a left child and the right child. So basically a tree which has the specific at most two children, such nodes we are going to call it as the binary tree. Again, in the binary tree, we are having a wide range of applications basically used in computer science, storage, and for searching algorithms. We are going to use binary search to binary trees. Again, we are going to use for the storage purpose. We are going to make use of the binary tree data structure concepts. This is all. Let's see what all the related concept with binary trees. So the terminologies which we discussed in the previous session, that about the root. What is the root? Is basically a topmost things we saw with an example. And node, every node which presents in a binary tree, that we are going to call it as a node. And basically a parent or a child, parent and a child nodes. In a binary tree, a node can have, see, in a binary tree, a node can have 0, 1 or 2 children. There cannot be more than 2 children for a specific node. Okay, such nodes we are going to call it as a binary node. The binary tree. So that's why in the definitions we saw a binary tree is basically having at most 2 children. At most in the sense it can have 0, 1 or 2 itself. Okay, not more than 2. That is the one thing we need to keep it into the mind. So again, the leaf node, we know the leaf node basically that means we don't have any kind of a children's. We saw the depth of the node basically from the root node 0 to the last node, and the height of a tree we understood that's in the previous session as well. So this is all a little bit definition of it. Along with these things we have been covered. So we are going to see the types of binary tree in this session. That means what is the full or strict binary tree, how it is going to look, and what is the perfect binary tree, and what is the complete binary tree, what is degenerate trees, that is a skewed trees. So this we are going to see into this specific session. So let's look up with an example over there. So coming back to the specific thing, the notepad. So I'm going to create one more thing called as a, I'm just going to name it here as binary tree. Okay, so I'm just going to tell it as a binary tree over here. So this is going to be the binary tree data. So let's take some examples and let's imagine how it is going to be there. Okay, so now coming back to the specific binary tree, so let's create one example over here. So let me show you how it is going to be there. So let me select the specific pointer to this thickness little bit. I'm going to take it as a red color over there. So imagine we have the specific node A, and imagine we have the specific node B. Again, imagine we have a node C over there. So if I talk about here, if I just talk about this like this, A, B, C. So in this case, basically imagine the node, it is basically having 2, and it is going to be having 1, and it is going to be having 0 over there. So imagine I'm just going to select this. So I'm just going to delete this specific thing. So let's take it very neatly. So I don't prefer to draw into a very weird manner. So let's take it these examples. Okay, so let's imagine we are having a node A, again we are having a node B, again we are having this specific node C. So in this specific node, so let's connect these specific nodes. Okay, so let's connect from here to here, and let's connect this specific thing node here to here over there. Okay, so after connecting it, let's try to give let's imagine this is the one condition. Okay, so I wanted to keep again the same thing. So I'm just going to control C and control V over there. So I wanted to control I want to copy the specific entire node. I wanted to keep it to the bottom again one more time. Control C, control V. Okay, so this is the another tree, and this is going to be another tree. I wanted to draw another shape over there. So let's try to draw another specific shape over there, and let's try to connect this specific node with these nodes over there. Okay, now I wanted to check which is the specific tree which is going to be the correct or which is not going to be correct one. So if I talk about an example, let's take it here color. So imagine I have a node A here, and we have a node specific B. This is the node specific C, and again I'm just going to tell there is a specific node A, and in this we have a B, C, D. So I wanted to tell which is the specific binary tree and which is not the binary tree. So this is going to be your binary tree because it has the 2 children here. This is not going to be your binary tree because it is having the 3 children, more than 2 children. Okay, so this is going to be your binary tree, and this is going to not be your specific binary tree. So this is the one thing we need to keep it into your mind over there. Okay, this is another thing we have to take care over there. This is not going to be the specific binary trees over there. So in this scenario, if you have a node A and a node B, let's try to give what is the specific A is going to be your root node, and is going to be your normally things over there. Okay, so now let's discuss the one by one how the specific types of the binary tree is going to be there. So I'm just going to discuss what is the types. So the first type we can just talk about this is a binary tree. So basically I'm going to tell as a specifically full or a strict binary tree, right? So we saw first we are going to check full or the specific strict binary tree, full or a strict binary tree. So let's see how it is going to be have an example for the specific full or a strict binary tree. So let's imagine we have a specific node. Let's imagine we have a specific node A here. So this is going to be a specific node A, and again I'm just going to tell here as a B, and again I'm going to make it as a C here, and again we have this node and this node. So imagine I'm going to connect these two things, and again I'm just going to connect with these two things over there. So we have a node A, and let's imagine this is going to be your node B, and this is going to be your node C, and is going to be your node D, and is going to be your node E. So imagine which is the specific full or a strict binary tree. So what is the definition I can say here? So the definition of this specific, I can say node has either 0 or a 2 children. A node can have 0 or the specific 2 children. I'm just going to tell in the brackets, I can just tell nodes that have either 0 or 2 children. So such specific nodes we are going to call it as full or a strict binary tree. So in this case, if I talk, if this specific node has 2 children, okay, this condition is satisfied. The node C has 0 children, again this specific condition is getting satisfied. Node A has 2 children. So this specific things I can treat it as, okay, this is going to be your strict binary tree. I can just tell, yes, this is going to be your full or the specific strict binary tree. So let's take another example. Let's take an example node A. Let's take an example of a node B over there. Let's take an example for the specific node C. So let's take an example for the specific node C. So let's try to add this connector. Then again imagine this is I'm going to tell node D here. Again I'm just going to tell here as a node F. Okay. So in this case the condition is getting satisfied. No. In this condition the node B having only one children. The node C having only one specific children. So in this case this specific cannot be treated as, this is I'm going to tell mark it as a wrong. This is not going to be your full or a strict binary tree. Even though if you have here something node called as yes here. So in this case this is having 2 children, this is having 2 children, but the node C is not having 2 children, it is having only one specific children. So this is not going to be belonging to the full or a strict binary tree. Okay, so I hope you got it what is going to be there. So now let's understand the next specific type of the binary tree, that is going to call it as the perfect, right? The perfect, Mr. Perfect binary tree. Mr. Perfect binary tree. So let's take this one example how it is going to be there. Okay, let's take this another example. Let's imagine we have a specific node A. Again we have a specific node B over there. Again we have a node specific C. So in this specific node I'm going to add this specific connector. So in this connector I'm just going to again I'm going to ABC. So I'm going to tell as a D here. Again I'm going to treat it as a F. Again I'm just going to tell here as a yes. Let me tell it here as something comma H. Okay. So this specific example is an example for the perfect binary tree. So what can be a definition here? Let me read this first definition. I'm going to tell here as an internal node, internal. So I'm going to tell as a internal node. I'm going to mention this is going to be the internal node have specifically 2 children. Internal node has specifically 2 children, plus internal node has at least have 2 children. Along with that, all the leaf nodes are on same level. I'm going to tell all the specific leaf node, all the leaf node are on same level, or on basically a same level. So if this specific condition satisfied, then that specific tree I can say it as the specific perfect binary tree. Okay, in this case it is going to be the perfect binary tree. So what is meant by internal node? So in the internal node we discussed right in the previously, if I just go to this example. So what is meant by internal node? The node which has at least one children, right? The node which has at least one children, that is going to be the specific internal node. Now what along with that what we are going to what we are looking here? Along with that we are looking all the leaf nodes should be on the same level. All the leaf nodes should be on same level. So in this case all the nodes having at least 2 children, internal nodes having at least 2 children, and along with that the leaf nodes are on the same level. You can see it is a perfect binary tree. I can mark it, this is going to be your perfect binary tree. So again, I can just tell another example, this which is not going to be the perfect. Imagine there was a root here. Again, I'm just going to tell here like this we had. Again, we have like this. Again, I'm just going to mark like this. In this case, we had like this. So in this case, it is not going to be the perfect binary tree. Why? Because this one condition is getting satisfied. Node having at least 2 children. This is getting satisfied. Okay, and it is and all left nodes are on same level, and all the specific left nodes are on same level. Basically, you can see all the leaf nodes are on same level. So you can see this is not having this specific, these are the leaf nodes, right? This is the leaf node, and this whatever I am marking, this is going to be your leaf node. You can see this level is not matching with this specific level, right? So basically the level should have been same. So you can see the level of the specific mark 0, 1, 2, 3 here. So in the third level also we are having a leaf node. Again, in the level number 2 is also having the leaf nodes over here. So that is why this is not going to be your perfect binary tree. Okay, this is the another example over there. So this is how the specific binary tree, that is the second type, that is a perfect binary tree, is going to be there. So now let's see about the third specific type. The third type is going to be the complete binary tree. So let's imagine, I'm going to scroll a little bit down. So let's try to write the third one, that is the third type over there. So the third type, I'm just going to write it here, that is going to be the complete binary tree. So we have something named called as a complete binary tree. So what is going to be the definition of the complete binary tree? The complete binary is a tree, all levels are completely filled. I'm just going to tell here in this bracket, I'm just going to tell here as a all levels are completely filled. Such trees we are going to call it as complete binary tree, except the possibility of last level. So in this, all levels are completely filled, all levels should be completely filled. There is another exception here, so I'm going to tell except the specific possibilities of the last level over there. Okay, last level must have its key as the left as it's possible. Okay, so I can tell last level can be not complete, but last level is there, right? In this is a one point I can mention, the last point I can mention, the specific last level is there, right? The last level must have its key node is specifically key node as left as possible. BILE possible over there. Okay, so I'm going to tell as left as possible over there. This is the another specific scenario. So I'm going to write it neatly. So I'm going to tell as left as possible. So this is all you have to make a notes into your notes. Okay, while listening it. So it's all very important to be understood. Okay, so the all levels are completely filled except the possibility of the last level, and basically the last level must have its key as much as left as possible. So let's take one example for this. So let's take an example for this. So imagine we have a node here. Again, I'm going to tell here is it one node, and here is another node, and again I'm just going to write it here as one node. I'm going to write it another node over there. So let me write here, this is the one node, and I'm going to be at another node over there. So in this case, I can just can I call this specific tree as a complete binary tree? Yes, this specific tree is the complete binary tree because it is a completely filled, right? It is a full binary tree, and it is also a complete binary tree as well. So let's take an second example. Let's take this example number 2. So imagine we have the specific tree. So like this, imagine we have like this. So I'm going to tell this one. Okay, so in this case you can see this is also a complete binary tree. How? Because all the levels are filled, but last level is not filled here. But there is another condition, last level should be as left as possible. You can see the node which is there, this is having at the left side, this is going to be a left right, right? So basically a root left right, right? Again root left right, the whatever the left, there is a left node here. So again I can mark it, this specific can be the specific complete binary tree, because the whatever the key is there, right? Key is the last level here, and it's on left side, it's basically a left side. That is why it is also be the complete binary tree. So let's imagine there is another, let's take an example, another tree. So imagine we have a node here, again we have the specific node, again we have the specific node here. Let me connect this node with this and this, and again I'm just going to tell this has the another thing. Let's imagine this is, so this is not going to be your complete binary tree, because the whatever the last level is there, that is there at the right side, right? That is going to be there at the right side. So it is can treated, this is going to not the complete binary tree. It is not going to be the specific complete binary tree over there. That is what you can have a look onto it. Okay, this is going to be the third type of the specific binary tree. So let's see what is the next. Basically, let's see what is going to be the next one. The fourth type, right? Basically, let's imagine there is another type, that is the fourth, that is a degenerate. So we had in the PPT that we have named it as the degenerate tree. So what is meant by degenerate tree? And the fifth type was the specific skewed tree. Okay, let's take this an example, next example over there. Okay, so what is meant by degenerate tree? Every parent knows has exactly one child. What is meant by degenerate tree? I'm just going to tell here as a every parent node has exactly only one specific child. Such nodes we are going to call it as a degenerate tree. So in this case, I can have this example, this and this. This is the degenerate tree. If I take this is not going to be your degenerate tree, because here it is having a two children, right? So if I take this, yes, this is your exactly a binary tree. Again, if I just talk about this is also going to be the degenerate tree as well. Okay, this is a degenerate tree. And what is meant by skewed tree? So basically in the skewed tree, whatever the degenerate tree is there, right? Imagine we have like this. So we are going to call this as the left skewed tree. Again, if I have something like this kind of trees, we are going to call it as the right skewed tree. Okay, right, I'm just going to tell right skewed tree. Okay, this is going to be the right skewed tree over there. So I hope you understood what is mean the types and the binary tree. So basically we are having the we saw the types: full or restricted binary tree, perfect binary tree. We saw about the complete binary tree, degenerate tree, and the specific skewed binary tree. So this is how these types of binary trees are there, guys. So in the next session, we are going to look on to the next concept. Take care. Bye bye. Hey guys, welcome to the session number 24. So let's understand the representations of trees over there. So the representations of the tree can be into the two categories, that is the array representation and the linked list representation over there. So let's look at with an example over there. So coming back to our specific pad over there. So I'm just going to come back here. So let me write, it is going to be the representation of the trees. So for that, let me create one specific tree over there. So I'm just going to create one tree. So let's create, this is a one tree, and imagine we have this tree like this. So this is going to be a tree, right? So this is going to be a tree. Let me create one tree. So this is going to be like this, and this over there. This is going to be a tree. Let me add the specific connection from here to here. It is connected, and again here to here we have connections. And I'm just going to connect this with this specific tree. Again, we'll just connect with this specific tree over there. Okay, so let me change a specific color now. So I'm just going to change the color for this one. Okay, purple. So again, I'm just going to create another tree. So let's imagine we have a connection. Again, this is a 2, this is going to be a 2, and I'm just going to tell this is having a right connection over there, and also this also will be having a right connection over there. So I'm just going to connect it. This you just imagine this is going to be an red color which you are seeing, that is going to be the original tree. Okay, so after that I'm giving the specific modification for the purple color. Okay, so let's imagine like that. So let's imagine in that way. So in this way, so let's imagine we have this specific tree. Okay, let's give the specific names here. Like try to give the names. So I'm going to tell here as a node A, this is going to be node B, C, D, E, F, G. Okay, this is going to tell here as a H, I, J, and K. Okay, imagine this is going to be your nodes over there. This is going to be an array representation. So this is going to be called as a representation of trees over there. The first one we are looking for the array representation. Okay, if I talk about the array, so let's imagine we are going to talk it of an array over here. Okay, so we have a node A. So imagine the node A, we are just giving a number, like we are storing a node A in the array, and we are storing here B, then we are storing C, and we are just storing D, then we are storing E, then we are storing F, then we are storing G over there, right? So if I talk about the red color one, imagine the whatever you are seeing in the purple color, that is coming afterward. Okay, so imagine this is the case, A, B, C, D, E, F, G is the specific node over here. So what is going to be the size? The size is going to be the array size is going to be 7 over there, because like this. Imagine we are just trying to add it over there. We have tried to add it over here. So after adding, how this specific tree is going to be there. After adding, how it is going to be there. So if we tell A, we'll be having B, C, and again we'll be telling here as a D, E. Again I'm just going to tell F. Again I'm just going to tell it as a G over there. Okay, So imagine how we are going to sell. So for first imagine A, B, C we have done. Then again we are going to do like those okay. So imagine we done it like this, right? So after doing this specific thing, we have another thing called as a HI over here. So imagine FG is been done, that is correct. So again I'm just going to write it for the H. Again we are going as a I. So imagine for the E there will be this, the left node is getting missed, right? So this is getting missed. Again for the F the two nodes are getting missed. So in this case this is going to be the null value, this is going to be the null value, this is going to be the null value. Again there is another thing that is missing here as well, right? That is also is going to be missed over there. So again I'm going to tell FHI. So after there will be a null value, then again there will be a J. So again there will be the null, again there will be the null value, again there will be the null for the G, then the last item will be, so what we have given as a, that is a K, right? So we have given as a K. So this is how the representation of the specific array is going to be there. Okay, so whatever the missing left and right will be there, we need to replace that specific thing as the null values. Okay, so we need to create this specific space for that as well. Okay, in this case the size, whatever the size will be there, so whatever the size 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, so size is going to be the 15 over there in this specific case. Okay, so this is how the specific things we are going to treat it over here. This is how the specific array representation will be there. So let's see another representation. So the second representation of it. So in the second representation I'm just going to maintain, this is going to be your linked list representation. I'm just going to tell linked list representation. Okay, linked list representation. Let's take another example over there. So let's take another example. Let's imagine we have a node 2 here, again we have a specific node 1 here, again we have a node specific 4 here. So let's try to connect these two node with 1 and 4, and this specific node is also is there. So this is connected with the node 12. Let's imagine this node is been connected with the node 11, and this is not having, this is having only the right side node over here. So now I wanted to create the linked list representation for it, linked list representation of the node. So for that, imagine the linked list will be having what we have seen, right? The linked list is basically, let's try to create a newly from here. So let's create it shapes over there. Okay, so we have, this is a one thing, and let's imagine this for the one node 2 we have the, I'm just going to tell for the node specific 2 we are going to have the two specific linked list that is going to be like this, right? So there is a 1 and the 4. Again for the 1 we are having 2 aligned 11, right? So I'm going to tell, so this is going to be for the 1, this is going to be for 1, and for the left we don't have anything, we are going to write it here only as a 3 over there. So for that let's try to create the, then let's try to copy this. Let's imagine here. So imagine we have a node 2. For the node 2 this is going to be your previous value, this is going to be your next value. So this is going to be have the data, and we have a pre and a next. Again we have here as a 4, we have a pre and a next value. Again we are having a 12 here, so I'm just going to tell here as a pre and a next. Again we are having something here as a 11, this is going to be a pre and a next, and here we are having a 3 over here, right? So in this case I can just imagine, okay, this previous is been connected with this next is connected with this. Again this specific we have a previous and null, this previous is connected with the node 12, the next of it's connected with 11. So here we have a previous, so previous is going to be connected with the null value, and this the right side that is going to be connected with the third one. Okay, and the last nodes, so whatever the last nodes we are having, right? So all previous values and the next values I can treat, that is all things we can just make it here as a null, and I'm going to tell this is going to be the null, this is also going to be the null, this is also going to be the null value, this is also going to be the null, and this also is going to be the null value. Okay, so this is how we are going to link with the linked representation. I can tell this is going to be your doubly linked list, right? So whatever we have seen, that we have already seen in the previous session, but this is a representation of the trees. So this is basically we are representing with the doubly linked list. So this is all the representations of the guys. So in the next session we are going to see the in order, post order, and pre-order traversal. Take care, bye bye. Hey guys, welcome to the section 5, session number 25. Let's discuss about the traversal in binary tree. So there are three types of traversal, that is pre-order traversal, post-order traversal, and in-order traversal. So let's discuss one by one with the practical example. So let's begin with the rating pad over there. So I'm just going to write the first on the pre-order traversal over there. So I hope you'll be we have seen all those a lot of things in the trees, like how tree is going to look like, what is nodes, what are the edges and all. So now let's discuss about the traversal over there. So the first here we are having something called as a pre-order traversal, right? So we are having pre-order traversal over here. So how pre-order traversal is going to work here is, this is the specific syntax that is going to start with the root. Then we are going to look on to the left sub tree. Then we are going to look on to the right sub tree over there. So this is going to be the syntax of pre-order traversal. So when we talk about the post-order traversal, so post-order traversal is going to be like, so first we are going to look on to the left sub tree. Then we are going to look on to the right sub tree. Then we are going to look on to the root over there. This is going to be the post-order traversal syntax over there. So the same way we are having an in order, right? So how in order is going to be, right? So in order we are going to start with the left sub tree. Then we are going to look on to the root. Then we are going to look on to the specifically that is a right sub tree over there. So this is going to be the syntax for the pre-order, post-order and in-order traversal over there. So first look on to the pre-order traversal over there. So let's take one example over there. So let's try to draw one specific root over there. So imagine I'm just going to draw one specific root that is a 4, and imagine we are having a 1 here. Then we are having something 6 over there. Then we are having here as a 5. Then we are having some 2 over there. Okay. So I'm just going to draw this tree. So in this specific tree, if I just say you to find the specific in order, pre-order and post-order traversal. So I wanted to ask you to draw these. I wanted the nodes for pre-order traversal, post-order traversal and in-order traversal over there. So let's take how this is going to be there over there. Okay. So let's try to write the for the first order over there. So this is going to be your root tree, right? This is going to be the root tree over there. So let's write for the that is pre-order. So I'm just going to write it here as a pre here. So for the pre-order traversal, what it is going to be there. So the pre-order traversal, we know it is going to be the root. Then we'll be having here as a left. Then we'll be having here as a right, right? So this is going to be the syntax of it. So what is the root node here? The root node is 4 here, right? So I'm just going to mark it as a 4 over here. So I'm just going to write it here as a 4 over here. Then next, left and right, right? So what is left here? So one is going to be left, right? So I'm just going to write one is going to be the specifically left over there. Okay. Then again we have another left for 1, right? That is 5. So we need to go till last of it. So 1 is there. Then I'm just going to the, I'm going to go to 5 over there. Okay. Left is there. So after that again, once I am reaching the last node, then again I am going to talk with the pre-order syntax, that is a root. So root is already written. So left is already written. Then after left, then we need to write it is right, right? So I'm just going to write it as a 2 over here. Okay, this is going to be the left. So once in the left tree all that is finished, then we are having a right. So right only we are having a one node, that is going to be 6 over there. So the specific syntax is going to be like 4, 1, 5, 2, 6 is the specific pre-order traversal over there. I can just tell here as a 4, 1, 5, then 2, 6 is going to be your pre-order traversal for this specific tree over there. So the same way, I'm just going to write this specific pre-order. Now I'm just going to write it here as a post-order traversal over there. Let's write it for the post. So for the post, what is the specific left, right and root, right? So I'm just going to write left will be there. Then we are going to have the right. Then we are going to have the root, right? So what is the root node? So the 4 is the root node. I'm just going to write it at the last over there. And what is the specific thing that is left? So in the left again, if I just come to the left, 1 is there, right? So 1 is there at the left over there. So again, I wanted to apply, there will be another, I need to go to the left of it. So one more, there are children's of it, right? So for this specific, if I just take this specific entire node as a left node, let's imagine if I just take this entire node as a left node, now I'm just going to apply the same thing, that is a left, right and root here. So what is left here? Left is 5, right is 2 and root. So I'm just going to write it here as a, that is a 5, left and right, then root. Okay, this is done. So then after that we are having only a 6. So I'm just going to be write it as a 6 over there. So when I talk about the final here, 5, 2, 1, 6, 4 is going to be your post order traversal over there. So let's write it for the in order traversal now. So for the in order traversal, we are having what? So for the in order traversal, we are having something like left, root and right line. So I'm just going to tell here we are having a left, then we are having a root, then we are having something here as a right here. So what is left here? Left again, I'm just going to come over here. So again, I will be taking this entire node here. So if I take in the entire nodes, I will be taking an entire thing again. In this, if I apply for the left, so for the left, what we are having? So 5 will be there and root is 1. So I'm just going to write it as a 1. then right is going to be 2 over here. So root as it is, I'm just going to place here. Then for the right, what is that? Only 6 we are having it. So I'm just going to tell here as a 5 comma 1 comma 2 comma 4 comma 6 is going to be your in order traversal over there. So this is going to be the in order traversal, post order traversal, and pre order traversal for you. So I'm just going to give you one entire scenario for you guys, like one tricks. Okay, let's understand with one specific tricks over there. So that is trick is going to be amazing trick. So like we don't need to understand what is left, right, and all. Just there is a one specific trick to find the in order, pre order, and post order traversal for you. Okay, so let's try to do that one now. Let's try to draw one tree. So the tree, I'm just going to draw one specific tree, like I'm just going to create one. So here there should be one node and there should be one more node here. Again, I'm just going to write one more node here, and this node will be connected with the two more nodes here. Okay, so let's write it here. Okay, like this. So again, this specific node also will be having two nodes over here. Okay, so I'm just going to draw this specific node in this way. So I'm just going to select this and just make it a little bit wider over there. Okay, so not an issue. Then I'm just going to draw this. I'm just going to do it here. Then this specific node, I'm just going to make it little bit here. Then this is, I'm going to make it little bit over here. Okay, so now I'm just going to draw the specific shapes for it. So imagine this is node is connected with this. Okay, and this specific node, again it is connected with this. Again this node is connected with the left, and is going to be connected with the right node, and this is going to be connected at the left. Again is going to be connected with the right node over there. So now I have created this specific tree over here. So now I'm just going to give you the entire overview of it, like how a node can be created in a very simpler way. So that simpler way, so this is going to be the trick. You can use this specific trick anywhere over there. Okay, so in this specific trick, I'm just going to name some of the root names over here. Let's try to write it in the black. Easier. So I'm just going to imagine this is your 50 is your root node, and 40 is left, and 60 is going to be your right side, and again 20 is going to be here, again 30 is will be there, again here it will be 45, again it will be something called as 47 over here. Okay, imagine this is your nodes over there. So in this specific node, so I'm just going to little bit wide it over there. So this node I wanted to wide it, right? So I'm just going to make it Control Z. Okay, so we are at 48 over here. So there is something we are having the specific scenario for like we have something like called as like what we call the tricks inside it over there. So let's imagine this is going to be an entire tree. I'm just going to take an entire thing, entire nodes. I'm just going to Control C and Control V over there. Okay, so I want 3 times to be there over there. So I'm just going to keep it here one more, and I want to keep again one more. So I'm just going to keep this at the last over there. Okay, so I know we are having a 3 trees over there. So now see, for this I'm just going to draw the tricks over there. So for the first one, I'm just going to create one red color over here. So this red one over there. Okay, so imagine this is going to be your pre-order traversal, this is going to be your post-order traversal, and this is going to be your in-order traversal over there. So for the pre-order traversal, I'm just going to tell left, I'm just going to draw one specific left like this. Okay, for all the node I'm just going to draw like this. Okay, this is going to be the trick for the pre-order. And for the post order traversal, I'm just going to draw to the right side like this. I'm just going to draw like this. Okay, I'm just going to start doing like this for the post order. And for the in order traversal, I'm just going to make it downwards. Okay, I'm just going to draw like this, one kind of a stunt to it. Okay, now I'm just going to write one specific scenario. Let's try to create it now. So I'm just going to draw like this. Okay, I'm just going to draw one specific connection like this. I'm just going to draw. It will start from the root, and you have to go like this. So for everything you need to go like this. Okay, so I'm just going to draw like go like this, and I'm just going to here. I'll just connect over here. Then after that, again I'll just go it. I'll be connecting to the last node over here. So this is the one thing over there. So again I'm just going to draw for the another thing. Let me draw for this one. So again I'm just going to start with the root. Again I'll just go like this. It will be connected here. Then I'll just call it is connected over there. It is connected over there. Again I'll just go like this. Okay, so I'll be going towards like this, toward the last over there. Okay, so again I need to connect same way. We need to start with the root, and we need to go till the specific root over there. Okay, so here I have not went, so I'll go till here as well. Okay, so this is how we need to go it over there. Okay, so in this case, this is the one more thing. So let's create another one. So for this, I'm just going to again start with like this. Again, it is connected here, then it will be connected over there, and it will be connected like this. And here it is connected. So I'll be going like this. So no matter how many nodes are there, like this, you start with the root and go with like that over there. Okay. So in this case, now let's try to write the in order, pre-order, post-order traversal for it. So imagine this is connected here and this has been connected here as well. So basically it has been connected. Imagine this has been connected like this. So in this way you need to write, in this way you need to draw it over there. Now let's try to write the specific in order, pre-order, post-order for it. Now just whichever the nodes it has been connected, right? So this is, it is connected here, and here it is connected, right? And here it is connected, and after that it is connected this one. Again I'll go, again this has been connected, again this has been connected, again after this it has been connected. So in this way I need to specifically connect the nodes and I need to write the pre-order. So first write the pre-order for it. So first 50 is connected, I will write 50, then 40 is connected, then 20 is connected, then after it is going to the path, then 30 is connected, then after 30 60 is connected, then again 45 is connected over there, then after 45 47 is connected, then it has been connected. So you can see this is going to be your pre-order traversal. Okay, so if you write the formula substitution, if you substitute this with formula, this is going to be same again. So again let's write the post order. So again it has been starting over here. So the first node that is connected here is this, is 20 is connected, right? So 20 is connected, then again 30 is connected, right? Then after 30 40 is connected over there, then after 40 if I just go here, again 45 is connected, again 45, and then 47 is connected, then after 47 60 is connected, then at the last 50 is connected. So this is going to be your post order traversal over there. Okay, and again if I try to write the for the last one, so it is starting here. So first here 20 is getting connected, after 20 40 is getting connected, then again 30 is getting connected, after 30 50 root node is connected, then after that 45 is connected, then after that it is connected with 40. Okay, after that I have not drawn here, right? So I need to draw here as well. So this was I forgot. 45, after 45 the node 60 is connected, then 47 is connected. So this is how the specific in order for it. Okay, so even if you try substitute with the formula, it is going to be the correct one. So this is the one of the tricks for you guys to understand how the pre-order is going to work and how the specific post-order traversal is going to work over there. Okay, so in next session we are going to look onto the coding example for in order, post-order and pre-order using Java program. Take care. Bye bye. Hey guys, welcome to the section 5, session number 25.2. So let's understand the coding part in traversal in binary tree using Java program over there. So let's begin with the Eclipse part over there. So coming to my Eclipse over here, so let's create one specific new class for this tree. So I'm just going to create a new class for it. So where it went, so just right click over there and just click onto the new. I'm just going to create one specific class. So I'm just going to tell here as a traversal something, traversal tree. Okay, and I'm just going to create a public static void main for it. Just finish it over here. So once you finish this one, so we'll be getting a trees over there. So I'm just going to write the program for it. So the program is going to be very simple over there. So let's try to create one specific class, basically represents a node in a binary tree. So how we are going to create that specific things here? Yeah, I'm just going to create one specific class called as node class here. So this specific node class is going to be, it takes some int data. Okay, and after taking it, I'm just going to initialize this node and I'm just going to tell as a left, and there will be something called as RIGHT right of it. Okay, so basically in a tree will be having a data and will be having a left and will be having a right over there, right? Root, left and right over there. So then I'm just going to initialize the node over there. So it has to take the specific int of item. So I'm just going to, whenever I'm going to create a tree, I'll be passing what is the node over there. So whenever I pass that one, it has to initialize the specific node as the data of it. Then I'm just going to tell where you need to place it, either a left or either in the right or either in the root, like that. So for the first time, I'm just going to tell left is equals to right is equals to, it is going to be the null value for the first time over there. Okay, so it's going to be the things over there. Next, I'm just going to create another class. The class I'm just going to create it as a binary tree over there. Okay, so this is going to be the binary tree. So I'm just going to tell it as a binary and tree over there. So this, in this specific binary tree class, I'm just going to tell which is the root and which is the left and which is the right over there, right? So first I need to understand which is the root node as it, right? So in this case, I'm just going to pass the node as a root. So whenever this specific function gets called, that is a binary tree. In this specific, I'm just going to declare for the first time, I'm just going to initialize the root with the null value over there. I'm just going to tell initialize the root with the null. Okay, this is going to be the second class of it. So once this specific thing is done, so again inside this, I'm just going to write the methodology for the in order, post order and pre-order traversal for it. So for the first time, I'm just going to write the method that is going to be a void function. I'm just going to tell here as a void. Okay, so I'm going to tell here as a in order traversal. Okay, in order traversal is going to be the method name, and inside that I'm just going to pass the node, whatever the nodes you are passing, I'll just going to pass it over there. So I'm just going to tell if the specific node, whatever the node is there, right, if it is not equals to null value, if it is not equals to null or a root like that. So what I'm going to do here is I'm just going to call the same method, that is in order traversal. So after calling the same method, I'm just going to mark this specific node should be towards the left. Okay, I'm initializing a node, right? So in the in order, how it is there. So if I show you here, so in the in order over there, let's take the above one. Okay, so for the in order traversal, so for the in order traversal, what is the condition here? So that is a left, root and right, right? So same thing I'm just going to tell here as well, left, root and right. So you need to do what? You need to call the in order traversal, just mark the first node to the node dot left over there. Okay, then after we need to make it as a root, right? So what I'll do here is for that root, I'm just going to print syso system.out.println. I'm just going to tell I need to just print the data basically. So whatever the data will be there, I wanted to just print it. I'll just tell node.data, that is going to be the data is going to be your root node here. Okay, this is the one thing. So after printing, I'm just going to create one space like this. So after that, node.left, node.right and node.left, right? So I'm just going to call the same method here again. I'm just going to mark that value to the RIGHT right over there. So this is going to be the in order traversal for it. So now again, I'm just going to create a same method for, I'm just going to copy, I'm just going to paste it here. So in this time, I'm just going to make it as a pre-order traversal over there. Okay, here also it is going to take the node as this, and if I just take the node is not equals to null. So here first I need to print the data, right? So first what is the syntax for the pre-order? That is a root, left and right, right? So first I'm just printing the root node, then I'm going to call the pre-order traversal for it. The pre-order traversal I'm going to assign node.left. Then again I'm just going to call the pre-order traversal, I'm going to assign the node.right to it. So this is going to be the pre-order traversal. This is a very simple program, right? And again same thing, I'm just going to create another method. So in this case, I'm just going to mark this specific method as a, so in order is done, pre-order is done, now we need to write it as a post order, right? I'm going to make it as a post order traversal. So in this also is the same conditions will be there. So in this case, I'm just going to change the method name to post order traversal. And first here how it is going to be, here it is going to be the left, right and data, right? So left, right, and after at the last I'm just going to cut this and I'm going to paste it over there. So this is going to be your post order traversal code for it, right? That's a very simple thing. Now what we need to do, so this we have created the program, we have written the logic for it, we created the nodes, binary tree and pre-order, post order and pre-order traversal. So now what we are going to do here is we are going to create the binary tree for it. So I'm just going to create one specific binary tree. So sorry, but is a binary search it is taken. Okay, so what we have given, we need to give it as a binary tree here. So I'm going to tell here as a binary tree. Okay, for this specific binary tree, I'm just going to create a tree that is going to be the new binary tree over there. Okay, this is going to be the new binary tree. So whenever we initialize this binary tree that is equals to new binary tree, what happens? This binary tree, whatever we have created, so that is going to be taken over there, and this tree is going to get initialized over there. Okay, so once it is initialized, what is giving you the error? That's no closing syntax. What is saying? There is going to be a no closing. The traversal must be allocation with the allox instance. So with the value is local variable, tree is not used itself. Okay, so I'm telling here as a binary tree is equals to tree is equals to going to be a new binary tree. That's fine. So I'm going to initialize the values for it. So I'm going to tell here as first thing, like it's a first I'm going to initialize the tree dot root. So I'm just going to initialize what is going to be the tree dot root. Okay, for that I'm just going to initialize the new node of, basically I'm just going to tell right to give it as a 1 over there. Okay, so again I'm just going to tell tree root dot from the specific root. Okay, from the specific root dot I wanted to make this specific left value. Okay, so that is going to be like this new, that is the node of, that is going to be 2 over there. Okay, this is going to be done. So next again I'm just going to pass another thing, that is tree root of specifically right, that is going to be the node value is going to be 3 over there. Okay, then again I'm just going to write here 3 root root. So I'm going to tell here as a 3 dot root dot left of left. I wanted to create left dot left. Left of left should be the another value, that is going to be the 4 like this. Okay. Then again I'm just going to tell here as a the last one, that is a 3 root left of specifically right over there. Okay. 3 dot root dot left dot right. I'll just make it as a right node. So this node I'm just going to make it as a 5 node over here. So we are having this specific 5 nodes over there. Now what I'm going to do here is I'm just going to call that reorder first order over the traversal over here. So I'm going to tell here as a system.out.println in order traversal should be, it has to call the in order, it has to print it, pass for the in order traversal, pass the root. Again for the pre-order, pass the root, for the post order, pass the specific root data. So once we do this, now if I try to execute this specific binary tree code, so let's see what it is going to do here. Basically I'm getting one error. So the error, it is telling no enclosing instance of a type traversal accessible must qualify the allocation instance type of traversal tree. Okay, so A is the instance of it. So if I just tell here, if I right click and if I tell for the quick fix over there, so there is a no enclosing tag it seems. Okay, so let's see what it is happening over there. Okay, so yeah guys, so there was one problem. So I need to declare the class as a static here. So I have declared the class as a static, and even this class also is a static over there. Okay, so once I declared it, now you can able to see the in order, pre-order, post order for this. So once I execute the program, so you'll be able to see the output over there. You can see the in order traversal for the node is 42513 and pre-order 12453 and post order is going to be 54231 over there. This is going to be the correct one. Okay, so this is the specific Java program for the in order traversal, pre-order traversal and post order traversal. So take care, bye bye. Hey guys, welcome to the section 5, session number 26. So let's understand the binary search tree into this session. So what is binary search tree? A binary search is again a data structure concept where we'll be having, every node will be having a two childrens, that is basically denoted as a left child and the right child over there. So here we have some kind of a properties for the binary search tree. What is the property here? The property of binary search tree is the value of the every node in this specific left subtree is there, right? So that is going to be the lesser than or equals to the node value, that is basically the root node. So in a tree, the left values will left nodes, whatever will be there, those values will be lesser than or equals to the root node. Okay, and in the same way, the right values of in that specific tree, right subtree, will be greater than the specific node value. So this is the major properties of binary search tree. So this property makes binary search tree specifically useful for efficient searching and sorting operation. So first we understand what is binary search tree into this session, then we are going to understand the operations of binary search tree with the specific practical and coding example as well. Like how we are saying, like it is going to be efficient, right? Basically if I want to search, it is going to be an efficient. If you wanted to insert, delete operation, such kind of operations is going to be a major specific efficient program it is going to be. Okay, so let's see some of the key concepts with this specific binary search tree over there. Okay, so coming back to my notepad over there, so now let's understand a little bit depth for the binary search tree over there. So imagine we are having one specific tree over there. So I'm just going to write the specific node values over there. Okay, so I'm just going to tell here, suppose I'm going to write it here the 8 here, I'm just going to make it here as a 14, and let's tell here this is going to be here as something here as 5. Okay, so in this specific, whether this is going to be your binary search tree or not, I'm just going to tell whether this is BST, whether this is a binary search tree or not. So if I talk about here, the root value is going to be right here, the root value is, this is going to be your right, and this is going to be your right, and the left one, it is going to be your, basically this is going to be your left. So left and right. So we had some properties, right? So we had some kind of properties for the binary search trees over there. So what is the first property? That is basically the left subtree. The left subtree of all the nodes, the left subtree of all nodes are lesser, right? Lesser. So in this case, whether it is lesser from the root node, if I just tell root is there, so whether the 8 is a lesser value than 14 or it is greater than, it is lesser than. And if I talk about the left node here, basically if I talk about the 14 is lesser than 8, no, this condition is not getting satisfied, right? So this is not going to be a binary tree. I'm just going to tell no. I'm just going to tell the answer is this is not a binary search tree over here, because your left nodes are not lesser than the root node over there. Again, there is another condition, whether your right subtree, okay, whether your right subtree all nodes are greater. No, 5 is not greater than the root node, right? So if I tell 5 is greater than 8, this is also not getting satisfied. So it is not going to be the specific binary search tree. And there is another thing, there in the binary search tree, there won't be no duplicate nodes will be there here. So there won't be any kind of a duplicates nodes. So these are all the 3 properties of binary specific search tree over here. So let's try to draw the one correct binary subtree over there. Okay, so let's try to draw here. There will be a 9, and let's tell here as a 4 here. Let's tell this is going to be an 11. So this is going to be connected with this and this. And here I'm just going to draw again. There will be a 2. Again, I'm just going to tell here this is going to be a 7. And for the again, I'm just going to tell here as a right. So for the right, again, I'm just going to tell here as a 13. Again, I'm just going to make it as here as a 19. And I'm going to make this as something like a 12 over there. So whether this is going to be your binary search tree, yes, this is going to be your a binary search tree, because the left hand side you can see all it is having the lesser nodes here. So whatever you are seeing on the right side, it is having the right side having all the greater nodes over there, because see 4 is lesser than 9, 11 is greater than 9. So 2 is lesser and 7 is greater, right? And 11 right side should be greater, yes, greater. Again 13 to 12 is lesser than 13, yes. For 19 is greater than root node, yes. So the properties which we are talking here, that is going to be applicable for the entire root level node and for the every node. So basically I'm going to tell the properties, whatever the properties I said, that will be applicable for this 9, 4 and 11. This is one node, right? Again it is going to be applicable for 4 to 7. Again it is going to applicable for also for the specific node which is having a single child, that is also it is applicable. Again that is going to be applicable for 13, 12 and 19. And again it is going to be applicable for the entire all the nodes over there. Okay, so that is going to be the agenda for understanding the specific binary search tree. Okay, I hope you got this specific understanding on a binary search tree. So the only here is the left node should all be lesser than the root node, and the right node should be greater than the root node over there. So now we'll understand in the next session. So why we have said it is going to be efficient for sorting and searching algorithm with the examples over there. Take care. Bye bye. Hey guys, welcome to the session number 27. So let's understand the operations in binary search tree over there. So in the operations in the binary search tree, we are having a majorly 3 operations we are going to discuss into the session. That is the searching in binary search tree and how an insertion happens into a binary search tree. And along with that, we are going to look on how the deletions happens into the binary search tree over there. So these are the 3 major operations which we are going to look on to this session over there. So let's look one with an example, then we'll look on to the coding part with the Java. So first I'll just open the specific notepad over there. So inside this, let's start with one example over there. Okay, so let's try to create one specific binary tree over there. So I'm just going to draw one node over there. So this is going to be one node, and this is going to be another node, and this is going to be there, and this 2 specific node is going to be the children of this, and again this specific children of the specific nodes over there. Okay, so then again I'll just connect this thing. So let's try to connect these specific nodes. So I'm just going to connect with this to this node, again this to this specific node, and this with this, and this is going to be connected with this is going to be connected with this, and is going to be connected with this. Now let's understand how this specific program is going to be there. So let's take an example. This is going to be a node that is this is going to be your root node as a 50, and this is going to be your root node as a 40. This is going to be your 60, and this is going to be as a 20 and 45, and this is going to be as a 55, and it is going to be a 70 node over there. Okay, so in this case, which is the left and which is the right, you know, this is going to be your left node, and this is going to be your right side of your nodes over there, operations in BST. So now I wanted to first check whether this is going to be the binary search tree or not. So left node is 40 is lesser than 50, 60 is greater than 50, 20 is lesser than 40, 45 is greater than 40, yes, 55 is lesser than 60, and 70 is greater than the root node, that is 60. Yes, this is going to be the binary search tree because the conditions are satisfied. The left nodes are lesser than the right nodes over there, and according to the root node, whatever it is there I have. Okay, so now let's imagine if I try to write one specific nodes of it. Let's try to add like whatever in order traversal or post order traversal. So now I wanted to first let's apply this specific operations over there. So let's try to apply this specific first operation, like the specific I wanted to search for. First we are going to see the search operation, right? So in the search operation, imagine in this specific node, if I try to create an in-order traversal for it, if I try to create an in-order traversal, it is going to be like this, right? So for the in-order, I need to just mark it like this in the bottom. So what is going to be the in-order traversal for it? So the first I will be getting as a 20, then I will be getting as a 40, then 45, then I will be getting as a 50, then I'll be getting as a 55, then I'll be getting as a 60, then I'll be getting as a 70 over here. So what is this? This is, you can see this is going to be in the form of a sorted, right? The elements are in the specific sorted manner over here. So if the first operation talk about the searching here, so we are just searching the specific things inside it. So inside of searching, suppose I wanted to search for an element that is, imagine I wanted to search for an element that is 60 over there. So we already saw the binary search, right? So in the binary search, we were declaring some kind of things like indexing. Like I'll be telling this is going to be 0 index first, 2, 3, 4, 5 and 6. And what we did, this is going to be your low value, and this is going to be your high value, and whatever the middle value, this is going to be your mid value, right? So in this way, we were evaluating it here. So now I wanted to search for an element that is a 60. So 60 is basically a greater than the mid value, right? The 60 is basically the greater than the mid value. So what we are going to do, we are just going to search for the right side. Imagine is the target element, the same formula, the target element is greater than mid element. So what we need to do, we need to look on to the right side. Again, if the specific target element is lesser than the mid value, we were looking onto the left side. Again, repeat. So the same process, we will be repeating it until and unless we haven't found the specific element, right? So now what we are going to do here is, according to this condition, 60 is greater than the mid value, right? The 50. So 60 is greater than the value that is mid value. So what we do, we are going to search for the right side, right? So now I'm just going to mark, this is going to be the, this is going to be marked over there. So in this case, I'm just going to change the color over there to black. So in this case, the element will be like something like 55, 60 and 70. Now again, I'll be just tell here, this is going to be your low, this is going to be your high, or whatever you want. Like it is going to be what we are doing. This is going to be low, this is going to be high, this is going to be the mid now. So now what happens here, the target element is greater equals to the mid value. So the element is getting found over there, right? So in the same way, what we do in the searching in the binary search tree, it is exactly similar to the binary search tree is exactly similar to the binary search, which already we have seen in array. So in this case, it is going to take on to the root node, and the operation is going to be the same here. So first it is going to take the in-order traversal of binary search tree. After in-order traversal, then we'll be applying this specific formula to it. So what is going to be the complexity, time complexity of it? It is going to be big O of log n. So this is going to be the big O of log n is going to be the time complexity for the binary search tree over there. Okay, that is inside for the search operation over there. So I hope you understood what I mean to say it over here. It's going to be searching over there. So now what we need to do here is, let's apply the first operation, that is the insert operation over there. So let's try to create one specific, let me scroll to the top over there. Now I wanted to create the second operation. So I wanted to search for the insert operation. Okay, insert operation in the binary search tree over there. So let's try to insert some of the specific values into it. Then we'll look on to, let's insert some kind of a nodes over there. Okay, so I'm just going to insert one node over here, and again I wanted to insert another node. I want to insert another node here again, and imagine I wanted to be there like this one. Again I'll be taking here one node here like this, and imagine there will be another node, and imagine for this there will be a two child nodes over there like this. Okay, and let's try to have in this way over there. Okay, it's going to be there. So I'm just going to connect the specific nodes to it. So I'm just going to connect with this. I'll be connecting from here to here. I'll be connecting this specific node with this. So basically this node has basically two children, and this specific node will be having next two children over there, and this will be having a single children, and it's going to be another specific children over there. Okay, so what we did, we just created one specific tree, so where we'll have some of the values over there. So I'm just going to do what, I'm just going to copy this binary search tree, so because I'll be using again and again. So first we'll understand with one example here. Okay, so imagine I just tried to create into the red color marker here. I want to take the red color marker. I'm going to name some kind of variables here, like this is going to be the root 8, and this is going to be less 3. Let's make it this as a 10. This is going to, let's make this as something 2 here. Let's make this as something 6. Let's make this as something 4 and 7 here. Let's make this as something 2 12, let's make this something as something like 13 over there. Okay, so now we are having this kind of a nodes over there. Now imagine I want to insert an element here. So I want to insert an element, a number 9 here. I want to insert the 9 here. So this is your binary search tree. First I need to check whether this is binary search tree. So in the left side you can see all the values are lesser, in the right side all the values are greater. So yes, this is going to be your binary search tree. This condition is getting satisfied. Yes, this is going to be your binary search tree. This is true. Okay, now I wanted to insert an element that is 9 inside your binary search tree. So now how we are going to insert it? So where you are going to insert, that matters over here. So 9, so what is 9? So I'm going to match whether your 9 is greater than the root element. Yes, if the value which you want to insert, if it is greater than the root element, then straightforward I need to look onto the right subtree, right? So I wanted to look in over the right subtree over there. So this is the basically this is going to be the condition. Whatever I am searching, it is greater than the root node, I need to search for the right side. Suppose I wanted to insert an element called as imagine I wanted to insert an element 5. So at that time I would have look onto the left side, right? I would have look onto the left side. But I wanted to look, I want to insert an element 9, so I need to look onto the right side of it. So now again I'll just come here 8. Okay, so let's come back to the 10 here. Okay, 10 here we are having a node. So in the 10 I am going to check there is a right tree. Yes, there is a right value, that is 13. So 10 is basically, in this case, the specifically 10 value is greater than 9 value, right? So imagine if it is greater than 9 value and we have only one child here. So what we need to do, I need to match the values. Okay, 13 is there, 13 is already there. So there is a 9 I can insert in this. Yes, definitely you can insert, because if imagine I was inserting in 9 inside to the left subtree of 10. Okay, as a root 10, 9. So 9 is lesser than the root node and 13 is greater than. So here it is, conditions is getting satisfied. So the insertion is going to take place at this specific position over there. So this is how you can insert the specific element into the specific binary search tree over there. Okay, this is going to be the insertion of it. So then this is how the insertion happens majorly. Okay, so you can insert the based on the values, we need to match the values and you need to specifically insert the specific values to it. Okay, so now let's little bit understand deeply onto the like deletion nodes of it. So let's try to understand onto the deleting the specific binary tree. So I'm going to tell the third case which we discussed, that is basically is going to be the deletion in binary search tree. Okay, this is going to be the deletion in the specific binary search tree over there. So there can be three cases in this specific scenario. So what are the three cases here? So in the while deleting, it can be a case 1 and it can be the case 2 and it can be the case 3. We are going to look onto the all the three cases over there. So what is going to be the specific first case over here? Whatever the node you are deleting, the node can be leaf node. So leaf node means the last node, right? So the leaf node, the last, whatever the last value will be there in the node, that is going to be the leaf node. It can be deleted, this can be the deleted node. Again, the leaf can be non-deleted node. The node can be non-leaf node, right? Non-leaf node. I mean to say, if I wanted to, if I take this example, I can delete this. If I tell A to delete 6, it is not a non-leaf, right? So after deleting, again I need to shift the specific element where I need to shift. Again, who is going to take the position of here. So this also we need to validate, right, while deleting it. This is the another condition here. So again, the node, whatever the node you are deleting, it can be the node can be root node as well, right? Whatever the node you are deleting, that can be a root node as well. This is going to be the third conditions over there, right? So it's going to be the third conditions over there. So now let's try to create the same graph over there. So let's try to create a same graph. So I copied, I am not sure it is not copying right now. Okay, fine, no worries. So what I'll do here is I'm going to select this. I'll be using a same tree over here. I can draw again. I'm going to copy this. Again, I'm going to just paste it over there. Okay, so let's use this same tree over here. So in this specific tree now, let's try to insert, let's try to take one specific case now. Okay, the case number 1. So imagine inside this specific case number 1, I wanted to delete this specific node here. Let's try to delete a node 12 here. Okay, so first I'm just going to tell here as a delete 12. So 12 is basically, it will just traverse. Here is your leaf node, so this will get deleted. So after deleting it here, so normally it will be like 8 will be there and the 3 will be there. Again for 3 it will be 2, again it will be 6 node here and it will be 4, again it will be some 7 here as it is. Again it will be like 10, here it will be 9, here it will be 13. So after node deleting the node 12, this is basically the leaf node, right? It's going to be basically leaf node. It will get deleted. It will look simple thing like this over there. So that is fine here, right? So that is basically that's all right. We can, after deleting a node 13, it will be similar to it. So then what is the specific case 2 over here? So let's take an example of the case 2 now. So for the case 2, so what happens for the case 2 now? So I'm going to take an in-order traversal for this. Let's take an in-order traversal for this specific nodes here. So let's take an in-order traversal. So what all the in-order traversal it is going to be there? So in-order traversal for this, it is going to be like 2 here, then it is going to be 3, then it is going to be 4, after 4 it is going to be 6, then it is going to be 7, after it is going to be 8, then after that it is going to be 9 here, then it is going to be 10, it is going to be 12, then it is going to be 13 is going to be the last node of it, right? So this is going to be your in-order traversal for this specific binary search tree over there. Now imagine for the case 2, I wanted to delete it, this specific node. Let's try to delete one specific node. Which node you want to delete? Let's try to remove the node that is 6 here. Okay, let's try to remove this node that is 6 here. So I'm going to tell I wanted to delete this specific node that is 6 here. Okay, so after delete node, I'm going to mention here as a delete node that is 6 here. So after deleting a node 6, how your tree is going to be there? Okay, so if I try to exclude this node number 6, so the in-order traversal, how it is going to be there? So after, if I try to remove this specific node 6, after 4 it is going to be 7 over there. Okay, so after 4 it is going to be 7 over here. So which element is going to shift now? So basically what happens, after 4 the 7 is going, right? So whatever this element will be there, it will get shifted. So imagine if 7 was shifted to the top, 7 was shifted to the top, and it was 4 was onto the right side. 7 was shifted onto the top and 4 was onto the right side. At that case, you can see the element would have been not sorted. It would have been not sorted. 7, 4 it would have been, right? So that is why if you apply, first take the in-order traversal, and when you are deleting it, so delete it after 4, 7, after the sequence should be there. That should be similar. Okay, and it should not disturb the left and right sub nodes, and in the sorting manner it also should be there. So after deleting that specific node, the tree is going to be something like this. So 8 will be there here, and there will be a 3 here, and it is going to be 2 here as it is. The node 6 is getting deleted after 6. The 4 node is going to take less out here. So you can see if I flow 4, if I just take here, so whatever the 4 node, I am just adding it here, right? Let me make it neat. So whatever the node 4 we are adding, 2 is lesser than root, 4 is greater than 3. This conditions is getting satisfied majorly. Again 7 is going to be here, 7 is greater than 4, so it is going to be here, right onto the right side over there. Okay, and right hand side, that is going to be similar. It is a 10, that is 9, that is going to be 13. So this is going to be same for the left hand side. Okay, so this is going to be the case number 2 when you are deleting a non-leaf node. First I shown you what happens if we delete the leaf node. So in this condition we understood what happens if we delete the non-leaf node over there. Okay, this is going to be your specifically a case number 2. So now let's understand what is going to be the case number 3 over here. So for the case number 3, I wanted to delete the specific node as the specific. So I'm going to tell here the case number 3. So I wanted to delete what? So what I need to delete here? So I wanted to delete the root node over there. So I'm going to tell delete root here. Root node is going to be the case number 3. So I wanted to exclude this root number 8 over there. So now what happens when I want to delete the root 8 here? So again, if I want to delete this specific, now let's try to write the same thing, that is a 2, 3, 4, 6, 7, 8, again 9, 10, 12 and 13. So I wanted to exclude the root number 8 from here. So after excluding the 7, so this is going to be the entire left side, this is going to be your right side. So it should not get disturbed over there. Okay, so this is the things happens over here. So when I try to delete the root number 8 here, what happens if I try to replace 9 here? If I try to replace 9, if I try to replace this over 9 here, so if I take the pre-order traversal, if I replace pre-order traversal, 9 will be there here. So if I replace 9 to here, 9 root node, the 10 will be here as it is right side. So that is going to be that is also is going to be fine. But again, I wanted to first check for the left hand side. What happens first if I try to replace 7 here? So if I try to replace 7, if I try to replace here as a 7 over here, So let's try to replace the element that is 7 here onto the top. So 3 is going to be here as it is, and 2 is going to be here as it is. So 7 has been moved onto the top, right? 6 is there still. So after 3 there will be an element that is 6, and there will be an element that is 4. Okay, so after replacing 7 to the top, that is fine. Then if I delete, then will be as it is 10 here. Then there will be as it is, that is basically whatever the element we are having, 9, 13 and 12. So this can be done, right? So when we are replacing, first we need to check with the existing one. Can I replace 7 with here? Yes, I can do it. So it is a more optimal way to do it. So what we are going to do, this is the correct one. If something was getting disturbed, left and right tree was not getting balanced, at that case you could have moved to the next node and you could have tried it over there. Okay, so this is how, if you wanted to delete the root node, this is how the specific root node is going to be taken place over there. Okay, so I hope you have understood about the operations in the binary search tree. In search operation, we saw insert operations and we saw delete operations over there. In the next session, we are going to look on to the Java program for this. Take care. Bye bye. Hey guys, welcome to the section 5, session number 27.2. So in the previous session, we discussed about operation in binary search tree. So in this session, we are going to look on to the coding example with Java. So let's begin with the coding part of it. So coming back to the Eclipse over here, I'm just going to create a new class. I'm just going to create the specific new class over here. So I'm just going to tell here as a binary search tree. Okay, binary search tree is the specific class I'm going to create it. And I'm just going to click on to the finish over there. Okay, so let's try to see how the Java program is going to be there for the binary search tree over there. So first and foremost, I need to create one specific class. So I'm just going to create a class, that is, I'm just going to create the class that is the tree node as the class over there. So inside this class, I'm just going to initialize the key value, like I'm just going to declare the key, and I'm just going to declare some variable for the specific tree node. So that is going to be the left comma right over there. Okay, so this is what I have been created here. So once I have created this specific class for it, so then I'm just going to create one specific constructor for it. So for that, I'm just going to create a constructor public, that is a tree node constructor. This constructor is going to do what? It is going to take the item, the data, and it is going to initialize the key value, that is going to be the node value to the item. Then whatever the left and right is there, right, that it is going to make it as null. The same thing which we saw in the binary tree as well, right, when the pre-order, in order, and post order traversal, when we have created the program. So that is the initialization is been done. So once it has been created, so then I'm going to create another public class that is going to be a specific like binary search tree, whatever you want, you can just create it. Okay, so I'm just going to create a something like a binary search tree is the specific class. I'm just going to create it. So inside this specific class, I'm just going to create a private variables over there. So I'm just going to initialize the private variable, that is the tree node is one variable, and that I'm going to take it as a root. Okay, so this tree node is been initialized with the root over there. So here I'm just going to create another constructor for this specific public class, that is public, that I'm just going to create again like a binary search tree. So this is going to be the constructor. It is going to initialize the root value to null for the beginning over there. Okay, so it has been done. So once it is done, so again I'm just going to write the specific search operation. Like first let's write the specific insert operation over there. So I'm going to write it in the comment, and I'm going to tell you as it is a insert operation. Okay, insert operation over there. So we are going to insert this into a binary search tree over there. So here I'm just going to create something like I'm going to make a specific function like a public function that is going to be a tree node of insert. So I'm going to copy this tree node. So I'm going to tell here like it is going to be the public class tree node, and I'm just going to create a method name as a insert. So what it takes here is it takes the specific tree node as pass the root for it, initialize the root, then I'm just going to pass the specific key value to it. So this two data I'm just going to take as an input over there. So once it is there, I'm just going to check first condition if the specific root value is equals to null over here. So if this specific condition satisfies, So what I'm going to make it, whatever the root value will be there, that is going to be the new tree. So I'm just going to tell that is going to be the new tree node. That's initialize that value with the key whatever you are passing as the input. Okay, then I'm just going to return that root value to it. Okay, so this is what it is going to do, this specific operation over there. So it is giving me the error saying like the method must return a result type binary search tree dot node. Okay, it is returning it over there. Okay, or else what it has to do, so again I'm just going to check one condition here. So if the specific key value, okay, if the specific key value whatever I'm inserting, if that inserting the value, if it is lesser than the root value, right, that is what we have seen. If it is lesser than the root value, so what we are going to do, we are going to keep that value to the left side. So I'm going to tell make from the root dot left, from the root dot left, insert that specific value to it. So again I'm just going to apply the same method, that is the insert, and I'm just going to pass that is a root dot left over there, and I'm just going to pass the key value to it. Okay, this is going to be the scenario. So again there will be another scenario, so I'm going to use it as the else if condition. So in this again I'm just going to check if the specific key value is greater than the root, the key value is greater than the root dot key, if this is condition is getting satisfied. So what I'm going to make, so whatever the root dot right is there, right, so whatever the root dot right is there, just shift it over towards it. So I'm going to tell again the insert with the root dot right comma key over there. So this is the value we are passing it. Okay, if both the condition is not satisfied, so what I'm just going to do, I'm just going to tell here as a return the root value. So if it is left or right, or it will be a root value. Okay, so that is going to be the scenario. So this is a condition for the insert operation. So now let's write for the delete operation over there. So how the value is going to be the for the delete over there. So again I'm just going to write it again something like a public, that is I'm going to create a tree node. Now I'm just going to apply the delete operation. When I apply the tree operation for the specific tree node, takes the root value and takes the which item I wanted to delete. I'm going to take as a int of key over there. So in this scenario again I'm just going to check the same condition. So I'm going to copy all the things over here. Okay, so here to here, as it is I'm going to copy it over there. So I'll check here if the root value is equals to null value. We need to do what? If this specific condition root equals to null, what I need to do? I need to just return the root value to it, right? That is what I am doing it here. So again, if the specific key value is lesser than the key, so what I am going to tell root dot left of. So here I am just going to apply the delete operation. I'm just going to copy the delete. I'm just going to paste it over there. So again, if this condition satisfies, so if it is if it is existing in the right side, so in this case what I'm going to tell, so root dot right and just make it to delete to it. Okay, this is what I'm going to do it. So else, so if it is not the condition, so it will go to the else part. So inside the else part, so I'm just going to check one more condition, like if the specific, if we have still node, okay, if it is not a leaf node or if it is not a whatever it is, so if it is root dot left is equals to null, there is a no, then that is going to be the specifically what it is. If root dot left is equals to null means there is no existing node, this is the last node. Okay, in that case what I'm going to do, I'm just going to return that specific root dot right over there. Okay, so this is going to happen. So else if, again I'm just going to write another program like else if this condition, if like again I'll just tell here as a root dot right value, if the root dot right value, if it is equals to null value, if these conditions get satisfied, so in this case I need to just apply the root. Again I'm just going to tell root dot left over there. If it is there, so I'm going to replace with the root dot left left over there. Okay, so I'm just going to place these things over there. So keep the indentations properly or else it will throw you the errors over there. So if you have any doubts like that, so just simply use the closing and open brackets over there. Okay, so we are going to use simply the flower brackets to open and close it over there, so it is not going to be any confusion over there. So this is going to be your else part of it. Okay, so if it is having in the else part, again if this both the condition is not satisfied, so what I am going to tell, whatever the key value is there, right, read dot key value, just make that as a minimum value and delete that specific node. Okay, so I'll just create one function that gives the minimum value for us. So that is going to tell the root dot right over there. Okay, it is going to pass the root dot right. So in the same way I need to create one function for min value. So let's create that. So before that let's write complete this function. So after deleting it, just make it that specific node to the deleted node. Okay, so again I'm just going to tell root dot right value is there, right, just apply a delete function, just root dot write value, just delete it and pass the root dot key as the input for it. Okay, so this is how the things is going to work for it. So then if it is there, so again I'm just going to return the root element over here. I'm going to tell as a return the specific root to it at the end. Now I need to create one function called as a min value function over here. So it is going to be what? It is going to be the helper function for us. I'm just going to create that function here. Okay, the function here is the helper function to find the minimum value node in the subtree. So min value takes the root and checks the keys. It is going to run a loop inside the left and the right. So whichever the minimum value will get satisfied, that is going to return as the minimum value of the minimum node. Whichever the minimum node inside your tree is there, that is going to get returned by this specific min value function over there. Okay. So now I wanted to create one more function for printing purpose. So I'm just going to write that method as well. So whenever I try to print that method, basically a method that's basically does what it is going to get. We basically, whenever we are applying a binary search tree, so basically we know, right, we are first going to sort it, right? That should be in a sorted manner. That is there really we are going to apply the binary search tree. So what we are doing here is we are going to use the in order traversal method. So what it does means it's just going to return the syntax is left, right and root, left, root and right. So that is going to return this specific method over there. Okay, this is what which is needed. So then I need to write a method for the search operation as well. So how the search operation is going to be there? So the search is also similar, like whichever the node I wanted to search in the root, I'm going to pass as a key value, and I'm just going to map with if it is no root is not null, and if the root dot key is not equals to key, we are going to return that value root. Okay, if the root value whatever I want to search, if it is lesser than the root, I'm going to search for the right side, or else I'm just going to simply search for the left side. This logic we know, we already seen this logic over there, right? So it's already we know, right? So whenever we are searching the specific root node, if it is greater than root node, we are going to search at the right side. If it is lesser than the root node, we are going to search at the left side. That is what the searching operation which we have seen with the example. Same thing we have implemented into the coding as well over there. Okay, so this is all about the operations of this. So now let's try to give some values as an inputs, and let's try to see the output for it. Okay, so now what I'm going to do here is I'm just going to pass the inputs for the parameter here. For the public static void main, so I'm going to pass the inputs here. So first and foremost, what I had created, I'm going to create a binary search tree here. So I'm just going to create the specific binary search tree. So what are creating a binary search tree? We are just inserting the root value 50, 30, 20, 40, 70, 60, 80. Whenever I insert, basically it's inserted into a one creates the structure. Okay. Then we are going to find the in order traversal for the specific binary search tree. So after that, I wanted to search for an element 40. What happens? It takes the search element. If it is returning the value, it will be telling, okay, this has been element found, or else will tell not found. Okay. If I wanted to delete the specific element 30, suppose I wanted to delete an element that is key delete to 30, it deletes it. After deleting it, if I try to see the in order traversal, the 30 element should not be present over there, right? So that is what we are doing it here. So again, we are getting one error over there. So I hope there is no error here, right? So any error? Yeah, here we are getting the error. So what we can do for this here is, so previously we got same error. So what we declared, we just said here as a whatever the method name where we created, that we declared as the where is that binary search tree, right, is here. So that is previously traversal tree, right? We just declared the function as a static, right? So again, I'm just going to make this is also a static function here. So where is it? It is returning a binary search tree. So here, right? So whatever the it was there. So I'm just going to create the thing as a static over there. Okay. So after creating a static, so for where it is giving a error, basically yeah, it is not there right now. So anywhere we are having the error, somewhere we are having the error. So where it is showing a red color here. So where it is there, so I think here, yeah. So here it is just creating the again here. So again, I'm just going to make this is also a static function over there. Okay. So here you can see the no enclosing root binary must be enclosing instance for the binary search tree. Okay. So yeah, so what I'll do here is a public static. So I'm going to make public static tree insert node over there. Okay, so again we are having this error. So let's do one thing. So previously where I declared the static method, so we have declared the method to the static over here, right? So public class static over here. So I'm going to make it here as a public static class. So even if it did, it's not going that error. So let's do one thing. So we are having a main function name what we have created here. We are creating a binary search tree, right? That is a BST. So where is this function exist? I'm going to find it method. So onto the top. This is going to be a binary search tree function, right? So in that, what I'm going to tell here is I'm going to make it this class as a static over here. Okay, a static class tree node. Okay, close this one. This I have made it as a class static, and this is also a static class. Yeah, now the specific error has been gone. Now if I try to execute the program for this, let's see what is going to be the output. Create here. So you can see after inserting, the in order is 20, 30, 40, 50, 60, 70, 80. So when I found for an element 40, it is telling found 40 in the binary search tree. After deleting an element that is 30, you can see the 30 element got deleted. Now we are having 20, 40, 50, 60 and 70. So this is going to be the program for the specific binary search tree, and where we have written the logic as simple as that, and the same logic has been repeated from the binary search program as well. So this is how the things is going to be there. So in the next session, we are going to discuss about the AVL trees. Take care. Bye bye. Hey guys, welcome to the section 5, the last concept in trees. That is, we are going to look on to the AVL trees over here. So what is AVL trees and why it is needed? So we understood a completely as a binary tree and a binary search tree. Now we'll understand why we need the AVL trees over there. So overall, telling into a high level, the AVL tree is used for to balance this specific tree over there, right? So we know binary tree and binary search tree. So basically, when we try to create a trees concept, so basically it has the trees has to be balanced towards left and right properly. So we are going to come up with the concepts of AVL trees over there. So AVL full form is Adelson, Wilsky and Landis tree, that has been short form been used as AVL. It's basically a used for a balancing the binary search tree here. Okay, so as we know binary tree we saw, then binary search we saw, that is, and exactly with the binary tree, then AVL is also having the two terminologies that comes into the picture, binary search tree here. Okay, so what here we are going to do here is it will be having the two specific children's, like that is a left and a right children's. So what we are going to do, we are going to find the what are the edges of these two childs, and we are going to balance based on some kind of a properties and terminologies over there. So why we are going to use here is it is going to be a more efficient at the time of insertion. So we are going to take care, okay, the tree has been balanced or not. Okay, so we are having a various terminologies in AVL. The first terminology here is a binary search tree property. A AVL tree is a binary search tree, okay, where we are going to apply all this left right things over there. So I'm not going to repeat again and again. So we know what is binary search tree. So it is there is a first terminologies, it has the binary search properties. The second things, this the new jargon word here is the balance factor. The balance factor is basically finds the height between the left and right tree. Okay, where we are going to find some kind of a range values, so that's lies between -1, 0 and 1 over there. So if it goes beyond of this, we are going to tell the tree has been imbalanced. Okay, it is, we need to balance the specific tree. So for that, we are going to apply the LL rotation, LR rotations and LR double rotations kind of things. That things we are going to look on to the next session. So before that, let's understand the balance fault factor, how we can calculate it over there, right? So again, we have the next terminology, that's rotation operation. So as I said, right, if imagine the tree is imbalanced, so we are going to apply the concept of LR rotations, RL rotation and double R and double left rotation. That's some kind of a double right rotation kind of a things. Okay, so the complexity, the space complexity, the time complexity majorly is about the AVL trees is going to be as a big O of log n over there. In the worst case, making insertion, deletion and search operation, that is better than a big O of n square, right? So that is where the things comes into the picture. So let's look up with an example clearly and let's understand it over there. So let's try to create one specific tree over there. I'm going to create one balanced tree. Then I'm going to show you how how we can just notice that is a specific tree is balanced or not balanced. Okay, so I'm just going to create one specific tree. Okay, so this specific tree is going to be an again one more tree. So I'm going to create this has been connected with this. This might be connected with this, and again there will be another. So I'll be taking a big tree itself so that it will be a easily understandable for you guys as well. So I'm going to connect with this. So again, imagine there is a connection for this specific tree here, and again for this there will be like this, and so I'll just create another tree. Okay, so again for this specific there will be two more nodes over there. Okay, so I've taken the big tree itself so that it will be clearly understandable, and let's take one, this is example over there. Okay, so again I'm just going to little bit shift this thing over here. So I'm going to shift this specific things to a right side over there. Okay, so now let's connect the specific thing over there. So I'm going to choose the specific as a black color. Okay, so I'm going to select the specific things. So I wanted to maintain these things neat, so that's why I'm just using this thing. Okay, So imagine this has been connected with this, and again this has been connected with this over there. So this specific tree is connected with this. This is having a left right branches, and this tree has been connected with this. So this again has been connected with this specific two different nodes over there. And now let's imagine these two different nodes, and this is only having a left node, and this has been connected with these two children. So it has the left children, and again it has a right children over there. Okay, so again let's imagine, so this has been connected with this, and this has been connected with this specific node over there. Okay, so if this specific thing is clear, I hope. So now let's try to take an example and let's understand it over there. So I want to create one red color over here. So imagine we have a nodes here. So let's take example A, B, and let's take it as a C. So D, E, F, G, okay, H, I, J, K, L, and M over here. Okay, so here basically the major two terminologies we saw. The first terminologies which we saw here is the basically we are going to find the height. So we are just going to see the height between left and right. Okay, that has to lies between -1, 0 and 1. So we need to get the balance factor, that is -1 or 0 or 1 over here. So let's see how we are going to calculate the specific balance factor over there. So we are going to calculate the specific thing that is called as balance factor with one of the formula that is going to be right subtree. So it can be right tree minus, I'm going to tell as a right tree minus basically left tree over there. So right tree minus left. Okay, left tree, basically calculating the edges, right or left, or even it can be a left minus right, that can anything can be there. So now we need to find the what is the balance factor to it. Okay, so let's understand the balance factor for the node one by one. So let's take a node example left over here. So let's take it basically let's take it as a r minus l over there. Okay, so what all the edges we are having here? So we have an edges 1. So we need to feed the largest edge, okay, height. So A is starting and it will go till end. So that is the last node, right, leaf node. So I'll tell 1, 2, 3, 4. We are having a basically 4 edges. Right side we are having 1, 2, 3. We are having a 3 edges. So what is the 4 minus 3? It is going to 1. So it is in the range between -1, 0, 1. Yes, that is there. So I'm just going to tell the balance factor for A is +1 over there. Now same, let's take it for the B over there. So for the B, what is the balance factor? So 1, 2 edges we are having, right? That is right. Right we are having what? 1, right? Only 1 edge we are having. So I'm going to tell as a 1 minus left we are having 2 here. So 1 minus 2, that is -1. See, -1 is again the balance factor. It is in the range. So I'm just going to maintain as a -1 over there. Okay, now let's take it as an example C here. So for the C, what is the right here? 1, 2, 3. 3 is the largest and lowest is the 2. That is 1 and 2. So 3 minus 2, that is going to be 1. That is also a balance factor +1 here. So again, I'm just going to make it as for the D. So D we are having, how many we are having? So for the D we are having how much? Right side we have 0. Let's say left side we are having 1, right? So that is going to be -1. So it is going to be the -1. So for the what is the balance factor for the every balance factor for every leaf node will be 0, because we don't have left, right? Here 0, let's make it 0, and here it will be 0, 0 over here. Again it will be 0 over there. So let's calculate for the F and G here. So for the H it is going to be 0. For the F, so for the F we have only 1, right? So basically we have a right, we have a 0. For the left we have 1. So it is going to be -1. So I'm going to tell -1. For the G we have 1, 2, right? So basically we have 2 left and 1 is right. So 1 is right minus left is 2. So it will be -1. So I'm going to write it as a -1. What for the J? So J we have basically for the J we have left is 1 we have, and right is also 1. So that is 1 minus 1, 0. That is going to be 0 over here. So now see, when I calculate the balance factor for the entire tree and for the entire round, for all these things, the specific balance factor is 1 or -1 or it is 0, right? So it is in the range between the specific whatever the properties of AVL tree. So I'm just going to declare this specific tree is a AVL tree over here. It is a binary search tree. Along with that, it is going to be a AVL tree. The tree is been balanced properly over there. Okay, so this is all about the specific AVL tree. So let's take another example that is not an AVL tree. So imagine we have a 2 here. Let's tell here as a 3, and let's tell as a 5, and here let's tell as again like a 10. Here let's tell as a 20. So again I'm just going to tell as a 35. Let's tell as a 40. Again I'm just going to make it as a 45. Okay, let's imagine this is your tree. Okay, so if I calculate the balance factor for the 2 here, so what is going to the balance factor for the 2? So 1, 2, 3, 4. 4 is at the right minus only left we are having. So balance factor is going to come as a 3. So here the 3 is the balance factor. Here 0 is the balance factor. 0 is the balance factor. Here if I calculate for the 5, so 1, 2, 3, 3 and 2, that is going to be 2. So we are getting a greater than 1 value. So this trees we can declare this is a imbalanced tree. So I can just mention this kind of tree is a imbalanced tree. It is going to be the imbalanced tree over there. Okay, and it is not an AVL tree. So now we'll understand in the next session like how we can if it is a binary search tree, so how we can apply the AVL operation, and we're going to see about light left tree, apply the rotations for the imbalanced tree and make it a proper one. So these things we are going to look on to the next session. I hope you understood how we are going to calculate the balance factor into this session. Take care. Bye bye. Hey guys, welcome to the section 5. So let's understand the specific coding example on AVL trees, and along with that we are going to look on to the operations of AVL trees into the specific Java over there. So what is the specific operations in AVL? So we are having some kind of a rotation operations at AVL. So they are majorly the 4 primary rotation operations to balance the AVL trees. So the first one we are having left rotation, right rotation and left right rotation, also known as a double left rotation, and the right left rotation also known as a double right rotation over there. So these are all the operations that exist into the AVL trees over there. So let's look up with an example, then we'll move on to the specific coding part for it. So let's imagine we are having some kind of a tree over there. So in this specific tree, let's take an example here. Let's try to create one tree over there. So I'm just going to draw one specific tree. So I'll just select the black color over there. So imagine I wanted to have imagine there is a specific thing that is called as we have a specific 31 over there. So let me tell, there is a 30 is the one node, and we are having another node that is a 20 over there. So I'm just going to mention here as a AVL operations. Okay. So we are having a 30 here and we are having it 40. So what is the balance factor? So if we take the balance factor, it is going to be +1. Here it is going to be the 0 over there, right? That is going to be the balance factor over there. So let's imagine I wanted to insert an element that is 10 over there. So imagine if I try to insert, that is 30 is already there, again there is 20 already it is present. If I try to insert onto the 10 over here, so here the balance factor is going to get disturbed, right? So here the balance factor is going to come here 1, 2, 2 minus 0 will be, it is going to be 2. So basically I can just maintain this is going to be your imbalanced tree, right? This is going to be your imbalanced tree over there. So now we are having all the things has been left. This is a left skew tree, right? So now I'm going to apply the left of left rotation here. So I'm just going to apply the rotation, that is LL rotation. I'm just going to apply the left of left rotation, that is called as a LL rotation, left of left over there. So when I apply the LL rotation to it, so when I try to apply the LL rotation, so now we need to apply the LL rotation left of left, right? So what happens here is, so let's imagine this is going to be like this. So this is the rotation is going to happen like this. So after the rotation, the specific 20 will be here, and the less node that is a 10 here, and it is going to be the greater node that is going to be shifted towards 30 over here. Okay, so now this has been balanced tree. So and this is a balanced binary tree. As I said, the AVL tree property is a binary tree property as well. So when I apply the LL rotation, you can see it has been rotated to like this. So after rotating like this, this is going to be LL rotation. So now we are going to rotate in such a way that the tree should get balanced over there. So this is going to be the operation for the LL rotation over here. Okay, so this is going to be the operation for the LL rotation over there. So now let's understand the next example over here. Let's try to see the next example here. So imagine we are having an again element that is 30 over there. So again I am having an element that is 10. Okay, so that is the specific balance that is going to be +1 over here. So let's try to insert. So let's try to insert an element that is 20. So imagine there is a 30 and we have here as a 10. So now if I try to insert an element 20, so 20 is greater than the root element, right? So I cannot place towards the left, okay, as per the binary tree's properties. So I'm just going to put at the right side, that is the 20 is been coming at the right side over there. So now again if I try to see what is the balance factor, it is 2. So basically this is going to be your imbalanced tree, right? It is going to be your imbalanced tree over there. Now I wanted to apply the left and right rotation. For this case, if it is like this, so you need to apply the concept of all L rotation over here. So or LR rotation, sorry, LR rotation is basically is going to be what? That is a left and right rotation I need to apply it over there. So when I want to apply the right rotation to it, so how it is going to be there? So it is going to, first I am going to shift towards like this. So let me do like this. So let me imagine, like if I just apply this specific thing, so when I try to do a LR rotation, it is going to be shifted towards like this. Then I am going to mention, okay, 30 is going to be here itself and 20 is going to be onto the top. Okay, then again the 10 is going to be layer like this. So still it is not the balanced tree, right? Still it is not the balanced tree. So again I need to apply the another one more time the rotation. So in this specific side, so here the 20 is going to be here. So after this it is going to be 20 is going to come here and 10 is going to be here and the 30 is going to come over here. Okay, so the balance factor is 1 0 0. Again this is the balanced tree over there. Okay, so this is going to be the another thing that is going to be balanced tree over here. This is going to be the LR rotation over there. Okay, so now let's see about another rotation, the double rotation. Okay, the basically as we have mentioned, right? So I'm going to write it over here. That is going to be for your understanding purpose. Like we have understood the LL rotation and the specific RR rotation. LL rotation and RR rotation is going to be the what? This is the LL rotation. This is the LR rotation. This is, you can see there is a two operation is getting happen. So this is the number one and this is going to be second one, right? So we saw the one example for each. So basically LL rotation and RR rotation is going to call it as the, we are going to call it as a single rotations. We are going to call it as a single rotations over there. Again LR rotation, like this is a LR rotation or all L rotation, we are going to call it as a double rotation because there is a two times we need to shift the specific nodes into it. So that is going to be the LR and the RL rotations over there. Okay, so let's take another example over there now. So let's try to imagine we have an element, different elements. Now let's try to imagine we are having here as an element that is a 10 here and we have here as a 20 over here. So inside this 10 and 20, so imagine I wanted to insert an element 30. Now I want to insert an element 30. So it is going to be like this, 10 as it is will be there. Again 20, I cannot insert 30 at the left, right, because it is not going to be the binary tree. So now again I am going to shift towards 20. So after 20 the 30 is greater than the root node, so it is going to come at the right side. So I'm just going to insert at the right hand side. This already we know. So if I try to see what is the balance factor, it is going to be balance factor will be 2 here, it might be -1 here, it will be 0 over there. So now what I am going to do here is I'm just going to apply the LR rotation over RR rotation over. It is basically singleton rotation. So that is going to, we are going to apply the RR rotation if this specific case occurs. So because to balance this specific tree, so the 10 is already here and when I shift like this way, it is going to turn. So the 30 is going to come and placed at the here and 20 is going to come over here. So I'm going to mention here 20 is going to be here and specifically 30 is going to be hut over here. Okay, so now the specific tree is balanced over there. If I just going to see the balance factor 1 0 0 over here, so I can just tell this is going to be your R rotation. Okay, this is going to be the RR rotation over here. This is going to be the RR rotation. So this specific tree is balanced over there. So this is how this specific able tree is going to be occur over there. Okay, so I hope you have understood this specific concept. The RR rotation we saw, LR rotation we saw, and singleton rotation and doubleton rotation we saw over there. Okay, now let's try to create one AVL tree. Okay, so let's try to create one more AVL tree. So imagine there will be a question like you need to create a specific AVL tree. Create a specific AVL tree for the specific node. Let's imagine 40 and let's imagine 20 and 10, 25. Again, let's imagine there is a node 30 and let's imagine there is a node 22 and there will be a node that is 50. So you need to insert, keep on inserting and create a tree in such a way that the tree should get balanced over there. Okay, so that is how the things you need to create it now. So imagine first I'm going to tell 40. I'm just going to take it as a root node. Okay, and imagine 20 is basically comes on to the left hand side. So I'm just going to insert on the left. Again 10. So I cannot place 10 at the right hand side, that tree will get balanced. So I'm just going to mention 10 is going to be here itself. Okay, so after here I'm just going to insert, I'm just going to mention I need to insert an element that is 25 over here. So first and foremost I need to balance this specific tree. So I'm just going to apply a balance. This is a RL rotation over here. So I'm just going to apply 20 is going to come on to the top, 40 is going to go to the right hand side and the 10 is going to come over here. So the tree is going to be balanced over here. So it is the balance factor here. It will be 1, it will be 0, it will be 0 again. So again after inserting an element 25, so where I need to insert the element 25. 25 is lesser than the root node, right? So I'm just going to mention onto the left hand side. So 25 will be placed over there. So again I wanted to insert an element, that is, so 40 is done, 20 is done, 10 is done, 25 is done. So I need to insert an element that is 30 now. So where I can insert an element 30 now. So I'm just going to mention 20 is there. So 30 is basically greater than the root node. So I need to place at the right hand side tree. So already there is a 40, right? Already there is a 25. So if I place the 30 here, the tree is not going to be balanced, right? Because it is not greater than the root node. So I'm going to mention for the root number 25 here. So the node 25. So the 30 is greater than the node element 25. So it is going to come on to the right side according to the properties of binary tree. So 30 is been placed over there. So in this, if I tell there is a 1, 2, 3. So it can, the load factor is going to be 3 here. It is going to be 2 over here. Then it is going to be 1 and it will be 0 and it will be 0 over here. So as I said, right, see someplace I can maintain -3 or +3. So as I said, you can do the operation L minus R or you can do R minus L. Okay, this is going to be the balance load factor, right? So you can do anything like that. So that is why I'm using, sometimes I'll use R minus R or L minus R or R minus L specific formula. Okay, so now basically I need to apply the LR rotation to it because it is not balanced. So I want, after applying a LR rotation, so 20 will remain as it is here. Again 10 is going to be as it is. So what I'm going to do here is I'm just going to apply the LR rotation to this specific tree over there. So after applying a LR rotation to this specific tree, so the 30 is going to come onto the top and the next, the 25 and 40, right? 25 is going to come at the left and 40 is going to come at the right side over there. Okay, so now if I take this specific, this tree is been balanced over there. Okay, so this specific tree is going to be balanced. So here it will going to be 1, again it will be 1 minus 1, it will be 0. So it will be the 0 here, again 0 and 0. So this is going to be the balanced tree over there now. So now still we are having a 2 element to be inserted, that is a 22 and 45. So I'm just going to mention here that is I wanted to insert an element that is 22. So let's see how it is going to be inserted now. So where I can insert an element 22, let's see here. So again I am going to tell here as a 20. So 22 is basically a greater than 22. So it is going to insert the specific node at the right hand side of the tree. So the left hand side, it is going to remain as it is. The -10 will be there here. So here 30 will be there as it is. Again there will be a 25 as it is here. Again there will be an element that is 40, already here it is. Now I need to insert 22, right? So when I want to insert a 22 here, so where I need to insert it here. So 22 is lesser than the root node, right? So lesser than the root node. So definitely I can insert the 22 over here. So I'm going to insert at the here over there. So now if I see the balance factor, so it is going to come as a -2 or a +2, whatever. So it is not the balanced tree here. So basically 1, 2, 3, 3 minus 1, 2 will be there. So this is not the balanced tree. So what I'm going to do here is I'm just going to apply the RL rotation to it. So I'm just going to apply the RL rotation to it. So for which I need to insert for this specific elements. So I'm just going to tell for this specific node, I wanted to apply the specific RL rotation to it. Okay. So after applying this specific RL rotation, so how it is going to be, the tree, how it is going to look. Let's see how it is going to look. Okay. So now what happens here is when I apply the RL rotation to it, so this 25 has to come onto the top according to the root node. So I'm going to tell here that 25 is going to be in shift onto the top. Again 20 will remain here. So basically I'm going to shift this onto the top, not 22. If I shift 22 now, what happens? The 22, basically 25 will be greater than, so here the tree will get imbalanced. So I'm going to shift the 25 to the as a root node. 20 will come over there. So after 20, here I'm just going to shift the specific value. So 10 is going to come over here. So 10 is going to be lesser than 20. So again the specific value, that is 22, whatever the newly inserted value is there, I'm going to place it onto the left hand side because it is this property is getting matched, right? 28 is greater than 20, right? And 10 is lesser than 20. So the property is getting matched. So right hand side, the 30 will remain as it is. And again, the specific 40 is going to remain as it is over here. So after RL rotation, so this specific things is going to happen over there. So now there is another element I need to insert, that is 50. So I want to insert element 50. 50 is greater than the root node. So I need to look onto the right side. So 50 I cannot insert at the left hand side because it is going to imbalance the binary search property tree. So the 50 I need to insert here 40 after 40. So 50 is greater than 40. So I cannot place onto the left hand side. So I can replace at the last element as a 50 over there. Okay, so this is how this things here. So let's see what is the balance factor here. So here 1, 2, 1, 2, 3. So 3 minus 2 is going to be what? 3 minus 2 is going to be what? 2. Okay. 1, 2, 3. 3 minus 2 is going to be 1, right? So basically it is balanced. Again here if I take this as a load factor, so what is the load factor will be 0, 0, 0, See, 0 will be there. So what is going to be the load factor? 30. So here it is going to be 1, 2. So here it is going to be 2. Here it is going to be 1. So still this is not imbalanced, right? So it is again, it is imbalanced. So it is again imbalanced tree. So now I wanted to again balance this specific tree. So what I am going to do here is, again I am just going to shift this towards it to over here. So again I am going to apply this specific rotation over here. So after rotating, so 25 will remain as it is. Okay, again here 20 is going to remain as it is. Again here it is going to be 10 as it is. 22 it is going to be as it is. So here the 50 I cannot make it as a root node. If I make it as a root node, it is going to be higher and the balance tree will get imbalanced. So what I am going to do here is, I am going to place 40 as onto the root node, the middle element, and 30 is going to come on the left, and 50 is going to come on the left over there. So now this is going to be the balanced AVL tree. Okay, I hope you understood. So when you given an array of element to create a specific AVL tree, so you need to apply the rotations, then you need to keep on inserting the specific value so that your tree is going to be balanced over here. So if I tell here 1, 2, so basically you can see it is balanced here, it is also balanced. I think it is all 0, 0, 0. So the specific tree has been balanced over there. So this is how the specific concept of rotations is going to come into the picture. So now let's look on to the example, the Java coding example for this. Let's move to the Eclipse over here. So in the Eclipse, I'm just going to create one specific new class for it. So I'm just going to create the specific class name here as AVL trees. Okay, so I'm going to create this specific public static void main. I'm just going to finish it over there. So here let's try to see how the specific Java program is going to be there. So as and foremost, same we need to create the specific tree node as how we have created into the previous session. So I'm going to just create one specific tree node over here. So I'm just going to create a tree node over here. So I'm going to make this specific static class. Okay, specific static class, that is a tree node. So that's case the basically left, right values and height it takes, and majorly it is going to do what? It is going to take the tree node, the specific data, and the height of that specific node it is going to initialize with 1, and the left and right value is been initialized to null over there. Okay, so then again I need to create another specific static class to create the specific AVL trees over there. So I'm going to create another class, that is a AVL tree class. Okay, that's initialize the root node and basically gets the height of the tree here. Okay, how much height of that specific tree is there based on the n. So basically if there is no, it is going to return 0, or else it is this specific program, that this specific function that returns you the what is the basically height of the specific tree it is there. Okay, then I need to specifically get this specific balance factor for every node, right? So I need to get the specific balance factor now. To get the balance factor, again I'm just going to create another method, that is a get the balance, that takes the tree node basically, and if it is basically a 0 null, it returns the 0, or else what happens, what is the height of the left and what is the height of the right tree, it is going to return it over there. See, this is basically a method, as I said, right, the method which we return it, the height, that's basically returns what is the height. So what I'm going to pass, I'm going to pass all the left nodes for it. Again, I'm going to pass all the right nodes for it, and what are the left and right node of the specific root node will be there. So it is going to minus with that, and it returns the specific balance factor to it. Okay, so this is the specific method that returns the balance factor to us. Next, now we need to apply the R right rotation subtree rooted with the specific node Y's over there. Okay, so let's see how it is going to be there. So next method, I'm just going to create a tree node. So basically we are creating a right rotate here. So we are applying the right rotations here. Okay, for the subtree here. So how a right rotations happens here? Basically what we are doing here is we are going to apply what, like basically, you know, right, the left will go into the right and right will go to the left. So basically we are shifting it. So here these lines we are just applying the shift here. Then after applying, just marking the specific node X and T2, then we are making the specific whatever the left node is there, I'm making to the right, and after whatever the right node was there, I'm just marking towards the left. So you can see here X is equals to Y dot left, right? So we are storing the left node here. So after storing the node of left, so what then I'm making R dot right, whatever the left node is there, I'm just initializing to Y, and I'm just going to store that whatever the Y node value is there over there. Okay, again I'm applying the same thing for the left as well. Then after doing that, again I'm updating the heights of it. Okay, again I'm updating the height, that is it goes to the height function which we have written. It takes the left right values and basically apply the math operation. Then we are adding with 1 and we are just returning that height, what is the value of height Y and what is the height of X. that basically returns the node over there. Okay, so basically it is going to update whatever the value will be there, it is going to return the X node, basically whichever we need to do over there. Okay, that is going to be the right rotate subtree over there. So in the same way, the opposite of it, now I need to create another method that is going to be the left rotate. Now so right rotate we saw, so left rotate is basically opposite to it. So here we have a left right, we are need to make it as a right and left, rest all the things will remain same as it is, there is no change here. You can see after doing that we need to just get the updated height values of the specific nodes over there. Okay, so once if it is done, it returns the node y to us. So now let's see how we can we need to create an inserting for the naval tree. So for insertion of a tree, I need to create another method. So that is going to be a very big program. So say I'm not typing, because if I type it will take half an hour. So probably let's understanding is more important here. So now see how we are going to insert a AVL tree. So when I insert an AVL tree, we created a function for a tree node, that is a insert, that checks the node value and what is the key value for us. Okay, so if imagine if there is no node, basically it returns the new tree, or else it's basically the left, if the whatever the node value, whatever the root value is lesser than the key, we are going to what we are going to do, node whatever the lesser if it is there, we are going to place that node to the left, we are inserting. If it is greater than, we are just going to apply to the right side, and we are returning a node. So this program is similar to the binary tree which we have already seen, just inserting the specific tree. So when you are creating an AVL tree, it is like 90% it's same of inserting the AVL tree like a binary tree itself. Okay, the same code is also has been there here. Then after insertion, we are updating the heights of it, the left and right whatever there, and we are getting the what is the balance factor for that specific with the get balance function. Again we are just checking the specific, again we are just checking the balance factor here. So if we are having a balance factor at the specific left hand side, what we do, we are just going to rotate towards the right, or else we are going to rotate it towards the right side of the key over there. Okay, so it is going to be the specific balance factor. So again, if we try to do it for the right side, it basically does the balance factor for the right hand side. If it is left right case, it is going to be there. So basically it is basically we are applying the rotations here, which rotations it has to take, whether it has to take LL rotation or RR rotation or a double rotation LR or RL rotation, that is going to be there. So this is going to be the cases. So we saw with an example, right? So when the specific things will happen. So we can see where we need to apply the double rotation and single rotation. So here you saw we submit the double rotations when you need to do the double rotation. So when we are applying a double rotation, again the key balance, it is imbalanced. Again 2 times if we want to do, at that time we are going to use the 2 times the LR rotation over there. Okay, so once we're done, this is going to be the program for the all rotations over there. Okay, so now what happens here is when I need to create a specific minimum value node, again we need to find what is the minimum value tree node over there. So for that we are going to have another method that is going to be a tree node that is going to return the min value of a node. Basically we are going to find the leftmost leaf node of it. Okay, to find which is a minimum node inside the entire tree over there, to keep track of the which is the minimum node over there. Okay, so now again we have another thing. So this is an extra thing which I am going to show you. So that's basically returns what? Basically for a deletion purpose. So deletion operation is going to be similar here as well. When you are trying to delete the node, whenever you are deleting a node, see whenever we are deleting a specific node, this delete node operation works. Okay, inside basically when I try to delete any node from the AVL tree, imagine I found it after having an AVL tree. So we saw only the insertions over here. So imagine if there was a deletion operation, when you are deleting, again you need to check whether your tree is balanced or not, right? So if it is not balanced, again we need to apply the same specific stuffs. So this whatever the program you are seeing, that is similar to the top of the program which we have having here. Okay, so there can be 2 scenarios, right? If there can be a child node, whatever the node we are deleting, it can be a child node, or it can be a non-leaf node, or it can be a leaf node, or it can be the root node over there. So we are going to find the successor and what is the in order for it. So it is what this specific program is going to be there. Okay, to get this specific thing. So whenever we are deleting it, basically whenever we try to delete it here, so basically we need to get the what is the in order traversal, right? So the in order traversal already we have seen. This is the in order program which we have already seen. In order is basically left, root and the right, that is the formula for us. Same thing that is already we seen. This is the function for it. Now let's try to create an AVL tree and let's try to see what is the how that is going to be there. Okay, so I'm going to call a method inside our public static void main. So imagine I wanted to create a new AVL tree. So I created a specific new AVL tree over there. So after creating a new AVL tree, what we are doing here is we are just constructing the tree here. So we are inserting 10, 20, 30, 40, 50 and 25. So when I try to insert, the constructed tree is going to be looking something like this. Okay, then we are just going to check what is the in order traversal after deleting. after what is the in order traversal for it. So basically after finding an in order traversal, definitely we'll understand, okay, if the in order traversal is correct, then it is going to be your AVL tree over the like that. Okay, so here I am getting an error, like what is the error we are having it here. So basically it's telling me, I think I need to forgot to close on bracket here. No, it is correct. So if I try to close another bracket over here, okay, this means cool now. Okay, so when I try to execute this specific program, so let me execute this specific program. So when I try to execute, so here if I try to execute the program, so you can able to see here the in order traversal for 20, 30, 50, 60, 70, 80. So after deleting a node 40, I am getting the in order traversal after deletion of 30. So we are just getting the 40 over there. Okay, so this is how this specific program is going to be there for this specific node. So here, okay, so still I think I need to run the program. I think I ran another wrong program for it. So it has to tell me in order traversal and in order traversal after deleting node. Okay, it is giving the key to delete is 20, so it is taking a different program, sorry. So here you can see it is giving an same error like previously which we had here, that is basically it is creating an error where it is creating an error at our place number here. When creating a new ability, it is creating the bug over there. So what I need to do, I need to make it all that functions as static functions over there. Okay, so let's try to create the functions as static here. I'm going to tell here as this is going to be a static public class method. Okay, so after making as this specific class as a static, now it is cleared. Now again I'm just going to run this specific program. Now you can see now it is we are getting the proper output here. So in order traversal after constructed the AVL tree 10, 20, 25, 30, 40, 50, that is correct. So after deleting, you can see it has been deleting at the specific correct place and we are getting the proper output over there. Okay, so this is the Java program for the AVL trees. I hope you guys understood, and we are going to look on to the next section that we are going to look on to the hashing concepts. So this is all about the specific trees over there. Thank you guys. Hey guys, welcome to the section 6. So let's move on to the hashing concept. So we are going to look on to the what is hashing, and we are going to look what is functions and table, how the hashing techniques is going to work into this session over there. So we have seen how the specific data structure concepts with the arrays, linked list, and how we are going to store the data while inserting, while searching, while deletion. But in the same way, we are having an hashing data structure concept which gives more efficient ways of key value pairs. So that's we are going to map with the indexing positions, and we are going to store the values into it. So this is the hashing is basically a technique which is going to store a data and retrieve the data and search the data in a more efficient way using the hash maps over there. So that is where the hashing concepts comes into the picture over there. So here we are going to oftenly deal with the indexes and keys over there, and we have one specific formula hashing, and we have some hashing techniques which we are going to use for doing the specific storing the data efficiently while searching and retrieving so on. So basically the hashing techniques we are having a hashing functions, hash tables, or a hash map we can call it, and we see the storage and retrieval how it happens, and we are going to look on if the collision happens, and we are going to see how we can handle the collision techniques over that. So let's begin with the next specific example. So I'm going to come back to the notepad first. So let's see what is the example for it. So here let's imagine we are having one specific structure over here. So let's try to imagine we have some kind of a structure there. We are having a data like a linear search and a binary search data over there. So let's imagine we are having this kind of an indexes, so where we are going to store some kind of a data into it. So let's say this is going to be your linear search. So I'm going to say here this is going to be your linear search. So we know how the linear search is going to work, right? So imagine we have some kind of a data like 3, 2, 7, 9, 11 and 12. So how we were going, we were just going in this way. So we are going the specific linear way, right? So this was having the time complexity was the big O of n over that. So this was not good. And again we saw specific thing that is something a binary search. So the binary search we saw something like we had some an element 2, 3, 4, 9, 12 and 15. So we were marking as low, high, and we were finding the mid value, and we were working on to the so on. We have seen. So the time complexity was there will be the big O of log n, right? So now taking an hashing example over here. So how the hashing is going to work here. So imagine we have some kind of an element 0, 7, 8 and 10 and 13, like 5 and 22, like let's goes on 60 over here. Okay, so if it is a 60, so imagine the size of the specific element, the specific indexing position will be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it keeps on going. Imagine it was still 60 over here. The size of the specific indexing position was 60 over here. Okay, so I'm just going to tell here the specific boxes over here. I'm going to draw these specific boxes. It is going to be like this, and it goes on, and it is a 60 element we are having it here. So in the hashing, how we are going to do here is basically a similar like a high level overview on it here. Basically we are going to store based on the indexes over there. Okay, so whatever the key value will be there, we are just going to store it in the specific indexes over there. Okay, so whatever the element we are having, suppose we have to store 0, we'll store in the 0 element, and 7 I wanted to store, I'll store it into the 7 indexing position. 8 I wanted to store, I'll just store it at the 8. So 10 I wanted to store, I'll just store it to it, and 13 I wanted to store. Imagine if it is 11, so imagine the 13 was coming somewhere here, I'll be storing here. And I wanted to store 60 element, I'll just store it over here as a 60. And 5 I wanted to store, I'll just store it here as a 5. 7 I wanted to store, already I have stored it, and so on. Okay, so whatever the element is there, basically in the indexing position, I'm just storing it over there. So here the time complex, what is the time complexity if I wanted to search anything? Suppose I wanted to search an element that is 60. Suppose I wanted to search an element that is 60. So I was just doing what? I was just going to find the index position of 60 over here. So I was getting the value to it, right? So here the time complexity, I can just say it as a big O of n over here. So what is the space complexity? Space complexity is going to be high, right? The space complexity is going to be high here, because imagine if there I had a suppose an element, imagine I had some 1000 element here. Okay, and 1000 as an element. So I was storing somewhere here at the last, imagine this was your 1000 index. Okay, so whatever the remaining spaces in the array is going to be, that is going to get waste, right? So array space, whatever the array space is going to get, array space is going to get increase rapidly, right? It is going to increase rapidly. So that is why it is not a good suggestion to use directly a hashing technique in this specific way. So we need to use the concept of hashing concept. So we'll see how that is going to be there. So to apply the overcome of this specific, we are going to have another thing, like let's see how, what is that method we are having it. Okay, so I'm going to scroll a little bit down. So let's try to create one specific scenario. So let's try to create one specific scenario. I'm just going to create one specific shape over there. So let's try to have one specific shape. Okay, so I'm going to just change the color. So I'll just change it to black color over here. So for this, I'm just going to create another box. So let me create one kind of a box over here. Okay. Okay, so rather than doing this, so I think I have one more option to insert as a table. So what I'll do here is I wanted to insert the table over there. Okay, so I've just inserted like this table over here. Okay, so what I'll do here is, this is the one table I have inserted it over there, and inside this specific table. So let's try to create a table. So again I wanted to create another one. Okay, so I wanted to draw another one. So I'll just create another table for a single. So I'll just draw the bigger one over there. Okay, so we have this table over there. So because imagine we have this kind of a table. So in this specific table, I wanted to store this specific indexing based on this specific indexing position now. So in this table, let me add some kind of information to it. Okay, so let's try to create some elements here. So imagine I have an element here as a 2, we'll be having 12. Again, I'll just tell 3 here, and 13, I'll be just going as a 4, and 10 and 14. Okay, imagine we have some kind of an element. So imagine this is going to be your keys values over there, and this is going to be your hash table. So this is going to be your hash table over there. So there will be indexing position for the hash table. So let's tell 0, 1, 2, 3, 4 is the index, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So basically imagine this is your 14 indexing specific hash table over there. Okay, so we have a 14 of a hash table over there. So here basically we are going to, what is the size of the hash table? So the size, if we talk about the size, it is going to be the 15 over there. So we are having a two types of functions over here in the hashing. So I'm going to tell here as well, there are two types of functions that comes majorly in the hashing. So the one is directly one-to-one function, which is basically, and we have a many-to-one over there. Okay, so there is a one specific hashing formula, so which we are going to use it. So that is basically going to be h of x is equals to x mod 10 over here. We are going to modify with the specific 10 over there. Okay, so we'll see how it is going to be there. So let me copy this entire. So this is going to be a reusable component for me. So I'm just going to copy this entire box. Okay, so let me copy and paste it somewhere else over there. So because I don't want to lose this again. Okay, so let me imagine this. I'm going to just store it over there. Okay, so here it is. I'll just delete this. Okay, so this is going to be the reusable component. So I have just marked it as a bottom over there. Okay, so now what is the formula for it? So we have a h of x is equals to 10 over there. So what we are going to do, we are just going to map that specific thing to the bottom over there, right? So here it has been not copied properly. So let me control C and let me control V. Okay, if I just copy it, is going back to it. So it is not copying this. So I will just control C, control V. So let's see how it is going to be. Okay, it is not. Okay, so I have rectified that specific thing. So let's imagine now we want to apply the specific formula h of x is equals to x mod 10 over there. So imagine I wanted to store the value that is 2 over there. So I am going to evaluate. I'm just going to mention h of 2 is equals to 2 mod 10. So what is the value of 2 mod 10? It is going to be 2. So when I can't divide with the number, so whatever the numerator value will be there, that is going to get satisfied over there. So what I'm going to do, I'm just going to map the specific value to the 2 indexing position with the 2 over here. So I'm just going to store it the value that is 2 here. Okay, so this is how the things is going to work. Again, imagine I wanted to just store the another value that is the h of 12 here. So when I wanted to store the h of 12, so that is going to be 12 mod 10, that is going to be again 2 over there, right? So if I try to store the again value that is 2, so what happens over here? So previously we saw like if you wanted to use this specific hashing technique, you can just simply make use of it. 2 will get stored over there. Again 12 will get simply stored over here. So in the place here, if I just store here, it is going to be stored at the 12, and 3 is going to just store at the place 3 here. 13 will get stored again at the place that is 30. Again 4 will get placed at the 4 here, and 10 will just store at the place that is 10. And 14 will get simply stored at the 14th place. Okay, so in this case the specific things is going to be not correct. Like basically it is going to make use of the waste memory here. So this is a one type of function, right? That is a one-to-one. So in a many-to-many, basically if I try to apply this specific formula and use it, so in this, imagine in this specific formula, so whatever the formula we had applied over here, so this specific formula, so imagine this specific formula, if we try to do it over here, so here it is going to be mismatch, right? So it is going to be 2. So you can see it is 2 is getting stored over here, 2, that is fine. So when I wanted to store 12, so here you can see the collision is getting occurred. So that collision is getting occurred over here. So basically it is applying the collision over here, right? The collision is getting happened. Again, if I just try to tell here as h of 3, that is a 3 mod 10. So I'll be storing 3 at this specific position, that is a 3. So when I wanted to store an h of 13, so the 13 mod 10, again there will be a 3. So if I try to store again, so already there is a element. So here the collision occur, right? So again here the collision is occurring here. So this scenario we need to rectify. So to rectify this, we are having a different methods to do it, like quadratic probing, chaining method. So let's discuss this specific method into the next session. Take care. Bye bye. Hey guys, welcome to the section 6, session number 29. So let's understand the hashing collision techniques which we have occurred into the previous session. We saw how the collision occurs when we do the hashing concept. So let's begin with the hashing concept. Like we are having a techniques mainly on open hashing chaining, that we are going to mainly call as a chaining, and we are going to have the something called as a linear probing and the quadratic probing method over there. That is, we are going to call as closed hashing or a open addressing. And in the open hashing we are having a concept that is a chaining, and in the closed hashing we are having a linear probing and the quadratic probing over there. So let's look on to this with an example, then we'll move on to the Java coding part for it. So let's look up with one specific example. So coming back to the specific notepad, so we saw in the previous session how that specific technique we have seen how the specific collision occurred over there. So now first method we are going to look on to the specific, that is a chaining method over there. Okay, so let's imagine how that is going to be there. So let's imagine to handle this specific collision technique and hashing collision technique, this is going to be your hash table, right? So basically this is going to be your hash table, and we have some kind of a key values over there. So let's understand the first method, that is the chaining method. Okay, chaining, that chaining is the thing, the name itself is telling chain in the sense in the data structure, that is going to be your linked list, right? So that already we have seen, that is going to, we are going to apply the concept of linked list over there. So how it is going to be there here? So let's imagine the formula is going to be same. H of x is equals to x mod the specific 10 over that. So I wanted to store an element that is 2. So I am going to just tell here as a 2 mod 10. We are going to get it as a 2. So 2 is going to get stored over here. So 2 will get stored over there, right? So again, imagine I wanted to store for an element 12. So 12 mod 10, again we are getting as a 2 over there, right? So what we are going to do here is we are going to apply the concept of chaining over here. So how we are going to apply? So it keeps on going it, okay? So we know how the specific linked list is going to work, right? So already we are having a 2 in the specific indexing position. So we are going to create one chain and we'll just map it to the next specific chain like this. I'm going to store it again the value that is 12. And if there is another element, it keeps on going it over that. So now already 2 is already filled inside our specific thing in the specific hash table. So what we are going to do here is we are going to apply the chaining method over here. So I'm just going to tell here, okay, you need to store the element 12 over here. The chain is getting stored over there. So again, imagine here there is an element that is 22. I need to store again. So I'll be telling like 22 mod 10 again will be getting a 2. So again it will be like it creates this chain again 22 will get stored over here like this, okay? Like this it keeps on going it. So if I want to store the element in this way, so that keeps on going it over here, okay? So this is what we are going to call the concept of chaining method. So imagine I wanted to next, it is like a 3, right? So I will just tell here as a 3 mod 10, 3 will be getting here. Again we have something here as a 13 mod 10 again will be getting 3. So 23 is going to 2 is getting stored here again, and 2 is also getting here again, 22 is also getting here. But what happened, it is applying the concept of chaining. So when I want to store the element 3 will get stored over here. So again if I wanted to store an element 13, it creates a chain that is the 13 will get stored into the linked list manner over there. So this is going to be faster over there. So imagine in this case specific functionality, I wanted to search for an element 22. So what happens if I want to search for an element 22, I can apply the formula again 22 mod 2, that is mod 10, we are going to get the value that is 2. So I'll be first looking for the indexing position 2 here, right? So in this specific indexing position, if it is found, that is the element will found, or else simply will search in the fashion of the linked list over there, okay? So 2 will be there, again 22 will be there, and keep on whatever it is. So whatever the data we want, I am just going to find the indexing position first. So after finding the indexing position for that specific index, whichever the chain is getting linked, that in there we are going to just search it. So in this case, this is going to be a faster, right, as compared to the previous concept. That's where the collision was occurring. Okay, this is we are going to call it as the specific what chaining method over there. So now let's understand the specific second method, that we are going to call it as this is the first method, that is the chaining method. So now let's understand the second method, that with the specific thing that is going to call it as the linear probing collision method. Okay, linear probing, that is a collision method over here. So this also keeps on, it is kind of an interesting method. So here what we are going to do here is we are just going to apply one kind of a formula here. So what is the formula? It is going to be there. So the formula is going to be here like this. So I'm just going to write it here as a formula is going to be, that is the h of vx plus f of I, and what is the size of the specific table of u. Okay, we need to declare what is the size of the specific table over here. Okay, so in this case this is going to be the specific formula of it. So the size of a table, I like this. Okay, so imagine the size of a table is going to be a 10 over here. So in this case what I am going to do here is, in this specific case we are just going to tell like we are having an element that is h of x and f of I mod size, right? So in this case I am just going to apply this formula. So here I am going to tell, imagine I wanted to store h of 2 plus what is f of I. So what is I here? I belongs to the value that is 0, 1, 2 and keeps on going it. Okay, so first I'm just going to take an value of 0 over here, then imagine the size is 10. Okay, here what is the h of 2? H of 2 is going to be what? The value h of 2, the specific, if I just try to apply the h of 2 formula, that is going to be what? Mod 10 formula, right? So that specific mod 10 formula, that is going to be h of 2 is basically, we don't have any element, we are just going to store an element that is 2 to the element, that is we are going to just store it here as a 2 over here. Okay, plus what is the f of 0? F of 0 is, for the f of 0 the first initialization value will be 0 itself, and if I just try to apply the formula, we'll be getting 2. So we have just already stored the value that is 2 here itself. Okay, imagine now I wanted to store an element that is h of 12 here. So the h of 12 plus f of I, okay, and mod 10. So this is what is h of 12. The h of 12 value is basically, if I try to apply into the formula, h of 12 value, I wanted to apply the formula over here, right? In the h of 12, if I just try to apply, that is a 12 mod 10 will be getting 2 itself, right? So I'll be telling here is a 2 plus f of I. First I value is going to be 0, takes the indexing position 0. So if I just apply this specific formula with 10, so again we'll be getting as a 2 here. So in this case, 2 is already filled, right? 2 value is already filled. So now what if filled, if the value is filled, okay, you need to apply what? You need to increment it. Just increment the value. So what I'll do here is so 2 plus again f of value I will be using, okay. Here 2 will be there. So what is f of I value will get incremented. Basically I plus plus happen. So previously f of 0 was there. So now I'm going to tell f of 1. So f of 1 is going to be what? Indexing position. It is going to return as a 1 over here. So in this case, we need to store it at the indexing position 3 over here. So 3 is the specific 2 was filled here. So 3 is having a space. If it is 3 is filled, 12 will get stored over here. Okay, the 12 will get stored over here. Okay, so this is how the formula is going to work. And in the same way, if we take another example here, so I wanted to just store it for the 3. So basically, imagine 3 mod 10 will be what? 3 itself. This is very simple. You can just store it as a 3. So what happens? 3 spaces, we don't have a availability for a 3 space. So I value, in this case, I value will get incremented. So it will be like 3 plus 1. We need to look on to the next indexing position, that is 4. So 4 is available. So 3 will get stored at the place here. Okay. Again, I wanted to just store it for the 13. 13 mod 10 again will be 3. So 3 value is already filled. Okay. Then I value will get incremented to 1. So again 3 plus 1, 4 will be there. So 4 is also stored. 4 is also filled. Again, I am going to tell 3 plus 2. So 5. 5 indexing position is there. Yes, 5 is having an empty space. So 5 will get stored over here. Okay. 13 will get stored over there. Again 4. 4 is already filled. If I increment, 5 will be stored. So it will be stored it at the indexing position 6. Again 10. So 10 mod 10 is going to be what? 10 mod 10 is going to be 0. So the value of the 10 will be stored at the indexing position 0 over there. Okay. So this will space here. So 14. So 14 mod 10, again 4 will be there. 4 is stored. Again will increment I value. 5 is also stored. Again will increment I value. It will be 6. 6 is also stored. Again will increment the I value. 7 will be getting. 7 is empty. So we are going to just store the element here as a 7 over. The 14 will be get stored over here. Okay. So this is how the specific linear probing is going to occur. So I'm just going to tell here as a 14 over here. It is going to be stored here. Okay. So in this, what is the demerit? So we have some kind of a demerits here. This is a good method, but we have some kind of a demerit. So you can see all the things is getting clustered, right? So the clustering is the one of the specific demerit. So finding will be difficult. Find is difficult here. So I can just tell the finding an element is difficult. How? If I imagine I wanted to search for an element, let's imagine I wanted to search for an element that is 13. So imagine I wanted to search for an element that is 13. If I go to the indexing position 13, that's not an issue here, that we cannot go in. So if I just go to the, according to the formula, if I try to search here, so I need to search for the indexing position 3, right? So if I go to the 3, you can see the element is not found here. So here there will be a lot of iterations to do it over there. Okay, if I imagine I wanted to search for an element that is 25. Okay, in this case 25 mod 10 if I wanted to do, so I'll be getting 5. So I'll be, if I go to the indexing position 5, there is a different value itself. Again, if I try to keep on incrementing, still again I won't be able to find it. So in this case, what happens? The specific probing technique is going to get failed here, right? So it is little bit, it's fine, but the specific clustering happens, and to find the element it's difficult here, and searching is also going to be difficult over there. Okay, so this is the one of the another technique, that is the linear probing collision technique. The chaining was the better than the linear probing technique, but here we are using a chaining method. In this case, we are storing the, here everything is fine, but just the clustering is getting happened over there. Okay, so it is the another thing over there. So now let's understand another method, that is going to be the quadratic probing. Okay, so let's understand the last method inside this. So let's imagine I'll be giving a color here, right? Not red, purple. Okay, so let's imagine the third method, that is going to, which according to the PPT we saw, that is a quadratic probing. Okay, so the quadratic probing is another method, the same method, like where we'll be having, this is going to be your hash table, and we'll be having a hash values over here. So here the same, everything is same, but the formula is going to differ over here. So we are going to tell here as a h of x is equals to same, that is a h of x plus f of I mod size. So this is going to be the same formula, but here what happens here is the whatever the f of I will be there, that is going to be taken by the I square. It is going to take as a I square over there. Okay, so the I value is again the same, that is a 0, 1, 2, 3, 4, and keeps on going to the n value over here. Okay, so now let's try to insert the element 2. So h of 2 will be inserted. So let's imagine h of 2 plus f of I is going to be, initially it will be going to be 0. Okay, then the size, whatever the size will be, then imagine the size can be anything here, right? So the size is going to be here as a 10, imagine. So in the size of it, right now I have given as a 14. So let's imagine there is a size 10 here. Okay, so h of 2 is basically an element I wanted to store it. So it is empty at the indexing position. So simply 2 is going to get stored at the place here at the hashing table 2. Okay, so we'll be having 2 plus 0. So mod 10 basically will be getting, so if I just apply the formula properly, mod 10 will be getting 2 itself. Okay, now again I wanted to search for an element that is 12. I wanted to insert an element 12 here. Okay, so for the element 12, what happens, I wanted to tell here h of 12 plus f of I square, okay, mod of size. So again I will be telling h of 12. So h of 12, if I try to tell here, again it will be like 12 mod 10. So basically 2. So 2, we don't have a size, we don't have this specific thing here. Okay, h of 2. So basically I'll be telling here, we'll be getting indexing position 2 here, plus f of I square. I value is going to be 0 square. 0 square, if I just tell 0 square, if I just make it 0 square, it will be 0 itself. So here if I just apply the same formula, again we'll be telling 2. So 2 is not filled. I am going to tell filled. Already this is going to, it is filled. So I am going to increment the I value. So I'm going to tell here as a 2 plus 1 square. Okay, that is going to be 3 mod. So basically it will be getting as a 3 mod 10. Basically we will be getting 3. 3 is available. So the 12 value will get stored at the place that is 3 over here. So imagine we have an element again 22 here. Okay, imagine we have an element again 22 and here as a 33. We are having a element 22 and a 33 to be filled. So in this case, what happens? Now again I wanted to search for it to 20. I wanted to search for the 22, right? So I'm going to tell h of 22 plus f of I square. So if I evaluate the further formula, so it will be like 2 plus first 0 will evaluate. Okay, so again if I evaluate to 0, already 0 value has been filled. So if I evaluate to 1, the already 3 value will get filled. Then again I want to test 2 plus, again it will be a 2 square. I value incremented. So in this case 2 plus 2 2s are 4, right? That is going to be 6. So I need to store at the indexing position 6. So what happens here, the 2 value will get stored at the indexing position 6 here, that is going to be 22. You can see here there is a no clustering happening, and whatever the elements are there, we are just keeping far away from the indexing positions over there. In the same way, now imagine, now I wanted to store an element that is, so I'm going to tell here I wanted to just store an element that is 3. If I wanted to store, first 3 plus 0 will be there, so easily 3 value will get stored at the indexing position 3. Okay, so here you can see the 3 is already filled here. 3 is already filled, right? Now I wanted to apply the again probing, so that is going to be 3 plus 1 square. So that is again, it is going to be 4, right? So the 3 value will get stored over the 4 over here. So if I same thing, if I have done with the the above method, the step number 2, that is the probing method. So what happened at that time? What would have happened? So 20 would have stored at the next indexing position. 3 would have not stored here. 3 would have stored in the very far away index. But using this quadratic probing, we can keep the element whatever the based on the indexing position, we can just store the values. If it is not going to be much far away over here. So that is what overall concept of the quadratic probing. So again I wanted to store the 13, right? So imagine I wanted to store 13. So 13 plus, so 1 value is already stored. So in this case it will be 3. So it is going to be filled, right? It is going to be filled when I take the element first. So 3 will be there. Again I'll be tell 2 square, that is a 3 plus 2 to the 4, that is 7. So you can see the element 13 will be stored at the indexing position 7 over here. So still the elements are being kept far away over here. So imagine 33 again. So again if I just try to tell for the 33, let me put here. So again if I tell 3 will be getting, after 2 to the 4, 7 values been getting filled. So after that we will be getting 3, right? 3 will be the 3 square. So 3 plus 3, 9, that is going to be 9 plus 3, it is going to be 12. So the 33 would have been stored at the indexing position 12 over here. Okay, so this is how the specific quadratic problem is going to come into the picture over there. Okay, so this is all about the hash tables. So basically this is how the formulas evaluates. So we saw all 3 methods: chaining, linear probing, and the quadratic probing to handle the collision technique. So all the methods are good, okay, but the quadratic is more better then all other, and the chaining is also better. And next comes to the linear probing method. Okay, so the next session we are going to look onto the Java program for hashing. So take care, bye bye. Hey guys, welcome back to the hashing concept technique. So we'll understand the coding problem using Java on hashing. In the previous session, we understood how the hashing is going to be in take place over there. So welcome back to the session 30. So let's begin with an example over there. So coming back to the specific Eclipse, so I'm going to create one new specific package over here for the hashing. So I'm going to just create the package called as hashing. So I'll just create a class. I'm just going to tell here as a, so let's understand the specific linear probing over there. Okay, so I'm going to tell here as a linear probing, that is hashing, something like this. Okay, so I'm going to create a public static void main. So I'm just going to click onto the finish over there. So now let's understand how this specific linear probing hashing is going to take place with using Java over here. So it is going to take a package. So we are going to use the package that is import. So I'm going to mention here as import the specific java.util.arrays package. So java.util.star. I can just import all the specific package at once. So then once we taken care of this, so let's create the specific private variables over here. So let's create one specific private variable. So that's basically takes the specific array, right? So imagine this is going to be your hash table. Okay, initially I'll just keep it as an like this. So again, I'm just going to initialize what is your table size. So private int of the specific table size of it. Okay, so what is the specific table size of it? Okay, so whatever the examples we saw previously, the table size we have taken as a 10 there, so that for an easy understanding purpose. Okay, so now let's create another method. So let's create a method that is a public method, public static. Okay, so let's create a method called as a linear probing hash table method. So that takes basically what it takes the what is the size of the table as an input. Okay, so in this one I takes the pass the input as a size. So here I'm just going to initialize what is going to be the table size. So I'm going to tell here as a table size. So whatever the table size we have declared onto the top, so just make that size as the one which we are passing as an input over there. Okay, so once we have just created this one, so let me remove the static here. Okay, so I'm going to tell here as an int size, table size I'm going to just make it like this. Again, I wanted to initialize the hash table. What is going to be the hash table? The hash table we are just going to create a new hash table. So I'm going to tell new int of whatever the table size will be there. I'm just going to map that specific thing to the specific stuffs over there. Okay, so I'm going to just create it as a table size is equals to specifically new int of a table size over there. Okay, so this is how the things will be there. So I'm going to just do one thing. So I'm just going to keep the same name over here. Okay, whatever the name we have created, so I'm just going to keep the same name over here. Okay, the constructor. So whenever the constructor initializes, basically we are just creating the table has to this one over there. Okay, and again I wanted to fill the specific array with the what is the specific values is going to be for the empty slot. So for the empty slot for right now, I'm just going to fill the value with the -1. I'm going to tell here arrays dot fill method. So I'm going to tell in the specific hash table we need to fill an element that is -1, basically using a -1 to indicate the empty slots over there. Okay, this is what the code we have written it over there. Okay, now let's create another method. Let's create another method that is basically writes initialize the formula to it. So I'm going to tell here as a private int. So it's going to be a hash formula. So the hash formula is going to be like basically it takes the what is the key. Okay, and it's going to return is basically returns the key percentage by table size, right? That's what we did. Key percentage table size. Whatever the key value mod 10 we did into the program, right? So if the table size is 10, so it is going to take the whatever the mod of that. Okay, so it is going to be like this. Key that is percentage that is a table size over here. Okay, this is going to be your specific function that is a hash function. Now I wanted to insert an element now. So while inserting, let's see how we are going to insert it over here. Okay, so I'm going to create a public method. So I'm going to tell as a void. So I'm going to apply the method that is insert. So while inserting, I need to pass the specific key as a input parameter. So in that, I'm just going to initialize what is the hash index. So which hash index it has to store. So I'm going to tell whenever I want to tell. So basically I'm going to pass this formula, the hash formula, to get the what is the indexing position I need to store. So I'm going to pass the key value to this specific formula. It will return me where I need to store it. So there that is going to be your hash index value, right? According same thing we have done in the while seeing the practical example as well. So once we have done, so again I'm just going to tell what is the original index. So I'm going to store, this is basically that is the original index where the hash index has to store, right? The hash index is the original index where the specific element has to store. So I'm going to create another input in like a variable that is the original index. So that is going to be your hash index, whichever the function has written as the value. So then I need to, if it is the value is not filled, I need to do what? I need to increment to the next specific index, right? So initially the indexing position will start, I value is start from 0. The same thing as we discussed, right? See, the same formula we are doing it here. First we were just doing this formula, we did it, right? So after applying this specific formula, if the specific indexing value is not there present, we are going to increment. First I am going to check with 0, then I'll be keep on moving on to it. The same thing here also we are doing it, right? So the first I value is going to be start with the 0 over there. Now I need to find what is the next slot available. So basically I wanted to see what is the next slot available using the linear programming. So I'm going to apply the while loop over there. So in the while loop, I'm just going to tell here as a hash table. Okay, in the specific hash table, I'm just going to pass the specific hash index value to it. So I'm going to tell in the hash table, I'm just going to pass the hash index. If the hash index is not equals to -1. So what we did initially, all the arrays table, hash table, we filled with the -1. If the value is -1, that means this slot is empty, right? So that's why we are checking. If it is equals to -1, then we'll insert it. If it is not equals to it, we'll just simply increment it, right? So we are just going to simply increment it. So when I'll increment it, I'm just going to tell if it is not equals to -1, we need to increment it here, right? So I'm going to tell hash index, basically whatever the hash index is there. So whatever the original index we have created, we have just stored the original index, right? So in the original index plus I. So I wanted to increment the original index with I. Imagine I wanted to, that slot 2 is already filled. Next I need to go with the slot number 3. So it is what happens. So after going to the slot number 3, again I'm just going to do the table size. I'm going to apply the specific table size over here. I'm going to do the mod of the specific table size. So after that I'm just simply going to increment the I value. So basically until then the specific condition satisfied, wherever it finds the -1, in whichever slot it finds the -1, till that this while loop is going to get evaluated. Okay, if imagine if the specific I value, we need to check one condition. If I value is equals to table size, imagine I don't have any size, I don't have a space into my table. I don't have a space into my table. So at that case, what I need to do, I'm just going to simply tell SYSO. So I'll just tell the specific the specific hash table is full. I'm going to tell something like hash table is full. I'm just going to simply tell hash table is full. By telling this, I'm just going to tell return. So I'm going to just return the specific things. So along with that, I'm just going to tell hash table is full, cannot insert whatever the key value will be there. I'm just going to pass it. Okay, I'm going to tell cannot insert the specific key value to it. Okay, imagine if we found the -1 slot, I need to just store the specific value to it. So I'm just going to tell here as a hash table. I'm going to tell for the hash table of specific hash index, just store that specific value. Okay, hash index, just store the specific key value to it. That's it. So very simple, right? While inserting, if you find a -1 slot, we'll just store it, or else we'll keep on incrementing the while value. I hope you are getting it. So it's similar exactly what we have seen with this specific example. Okay, this program is very amazing, and it's an interesting part to understand. Okay, so now let's write the one more function for the search operation. So let's see how this search operation is going to be there. So the search operation, I'm just going to create like a search. Basically, I will check with the boolean. If it returns true, the value is found, or else the value is not found. So I'm going to search first for the specific key value. So while searching for the key value, here also I'm just going to mention the what is the hash index, original index, and whatever it is. Okay, so I'm just going to copy the top 3 element here. I'm just going to paste it over here. So we have a hash key here, and along with that we are having the original index we are storing. We are just passing the specific thing over there. So here also I'm just going to pass the same thing over here. So whatever the while loop we have created, the same while loop I'm just going to paste here. So again I'm going to tell, well, hash table is hash index not equals to -1. In that case, what I need to do it here. So again I'm just going to apply one more condition over here. So here I'm just going to check if the specific condition satisfied. So again, I'm just going to check one other conditions over here. So like I'm just going to check these conditions. Okay. So let's tell if the hash table index is equals to key. So imagine first whatever the value we are passing as an input, if it is equals to key value, will return true, or else we'll increment the hash table size. We'll just increment the value in the while loop. Again, if it is equals to table size, we'll tell we have looped through the whole table. Basically, we don't have, we will return false over there. Okay, so we are just simply searching the element over there that is going to be there over here. So here I'm getting here as a public boolean, public static. I'll just make it as a static. Okay, if you make static, it's giving an error. So it's giving an error. So what is the error it is giving? Okay, so I need to return right the specific boolean value. When it is del boolean, we need to return it here. So we'll tell rather than returning this specific hash key over there. So imagine if this specific condition is not found, then also it is going to be returned false over here. So only it is going to return you true. Only this specific FALSE. Only it is going to return you true if the key value is found in the hash table, or else it is going to return you the false over here. So this is going to be the specific scenario over there. Okay, that is how the things is going to be there. And now let's try to pass the specific inputs, and let's try to print the hash tables over here. So imagine I wanted to create one function that prints the specific values from it. So I'm going to tell create a public. So I'm going to tell here as a public void. I'm going to tell here as a print hash table is a function which we have wanted to print it. So this I'm just going to simply run one for loop and just simply print the whatever the values we are having it. So let's tell here as a for, I'm just going to tell int of I value is going to initialize with 0, and I value should be lesser than the table size value. Okay, then I plus plus. So that's incremented. So in this I'm just going to print whatever the values we are having in the hash table. So I'm going to tell here first I'll just pass the specific index position. Okay, in this specific indexing plus I value I'll be passing as an index. Along with that plus I'll just pass some value to here. Okay, so here the thing is it's creating an issue. Let me create like this. So along with it, it has to tell me the index and what is the hash table value we are having it. I'm going to tell here as a hash table of I value. Okay, this basically prints me the index and the what is the tables value we are having into it. Okay, this is going to be the specific scenario. Now let's try to pass the values to it, and let's check whether we can do it or not. So I'm going to create one specific linear probing. I'm just going to tell linear probing hashing. I'm going to tell has a table. I'll just create one table is equals to new. So again, same thing, that is a linear probing hashing over here. So let's try to give the table size as a 10 according to our example, whatever we have created. Okay, once I just created an example, let's try to insert an elements over there. So let's try to insert an element. So I'm going to tell here as a from the specific table dot I wanted to insert an element, that is imagine I wanted to insert a key value 5. Okay, and so on. Like I'll just insert 4 more value 1, 2, 3. Okay, so I'm just inserting 1, 15. So I'll be inserting all 25. Then let me insert here as 6. Okay, and I'm going to tell here as 66. So let me insert an element that is 66 over here. Okay, 6 and 66. So we are inserting 5, 15, 25, 6 and 66 over there. So now I'm going to tell here as sy soc. So let's tell as sy soc. So I wanted to just tell hash table after insert. I wanted to see how this specific hash table going to look after insert. Okay, so for that I'm just going to tell here as a table dot print hash table. Okay, I wanted to just call a function print hash table. So let's execute this specific program and see how the hash table is going to be looking. So here you can see guys, amazing, right? You can see here the value it is storing. You can see at the indexing position 0, -1, 1, wherever the values is not stored, it is storing -1. The value where it is applying the specific linear probing, the 5 will store at the indexing position 5. Again 15 means 5 will get 5 already filled, so it will go to the next indexing position, 15 will get stored, 25 and 6 will get stored. This is really amazing, right? So imagine I wanted to insert a table. So this is what I wanted to show you. I wanted to insert a specific table dot, I wanted to do what, like table dot insert. Again, let's try to insert an key. Now let's try to insert 2. Okay, and along with 2 I wanted to store the 22 here. Again I wanted to just store the specific 12, and again I'll be storing 22 here. So according to the program which we saw practically, right? So now see, it will be 2 will store at the indexing position 2, and 12 will store at the indexing position 3, and 22 will store at the indexing position 4 here. So if I just try to execute here, so you can see guys, the indexing position 2 is stored, for the 3 12 is stored, and for the 4 again 22 is get stored. So this is how the specific linear probing that occurs, right? It's a really amazing part over there. Now let's imagine I wanted to search for the specific element over there. Like I wanted to apply the searching method over here. So for searching, imagine I wanted to let me paste it over here. So let's type it here. So I'll just tell SYSO. So I'm going to tell searching for a key element 50. So if I just tell table.search, if it is there, it will tell found, or else it will tell not found. Okay, it is a ternary operator. Okay, table.search 55. So let's imagine 500 I wanted to search, it will tell not found. So first I should get as a found, then I need to get it as a not found. You can see 15 is found because 15 is present and 50 is not present, so it is getting as a not found over here. Okay, so let's understand another method, that's for the delete method over as well. Okay, so let's try to write one more function, that's a delete method that we are not discussed in, but imagine if I wanted to delete, how it is going to be the function over there. Okay, I'll be giving you that function as well. So imagine this is going to be the function I'll be pasting here. So you can see there is a public void delete method that takes the key element. Again the same thing repeats, same while loop will return. So imagine same while we found the element, what we are going to do for that specific indexing position. Okay, if the element I wanted to imagine according to the output, if I wanted to delete 15, so in the place of a 15 I need to replace the 15 value with -1, right? It means the element is not found, the element will be empty, slot will be empty. We are doing what? We are just making the hash index with -1 and will return that key has been deleted. Okay, so imagine if the table size is basically we are not having any element which I wanted to delete it. So we'll go to the entire table. If the key is not found, we'll tell the not found. The specifically key is specifically not found over there. Okay, so let's apply the specific delete method now. So let's try to delete the delete method. So let's try to see how it is going to be there. I'm going to paste this one. So imagine I wanted to tell table.delete, I wanted to delete 15, and same way I wanted to delete an element that is 2 over here. Okay, let's delete as an element that is 2. So after deleting the specific keys, that is a 15 and a 2, so those specific elements should be minus now. So those specific elements should be -1 for us. If I execute it over here, so if I see the output, you can see previously output we had this data. So we deleted the element 2. You can see after deleting it is coming as a -1. Again we deleted an element 15. You can see after deleting element 15 at the indexing position 6, you can see the element 6 is coming as a -1 over there. Okay, so this is how the specific linear probing occurs. This is how the specific hashing techniques we can follow for the using the Java program. So it is going to save you a lot of time. Space complexity is good and time complexity is going to be good over there. So I hope you have understood. So this is the end of this section 6. So we'll see in the section 7 a little next, that is dynamic programming. Take care. Bye bye. Hey guys, welcome to section 7, dynamic programming. So let's see how the dynamic programming works in the concept of data structures and algorithm. So basically a dynamic programming is a computer science concept in DSA. Again, it's a very powerful technique to solve a wide range of problems actually. So what we are going to do here is, whatever the program will be there, the problem will be there, we are going to optimize in a very high level way by breaking down into a very smaller sub problems over there. And we are going to solve a very sub problem into a very efficient manner over here. So that's once we get the specific result, that we can make use of those specific sub problem result to another sub problem, like basically just making use of the code again and again. And the approach is basically very often here, where we are going to have the bottom down approach and top down approaches. We are going to use such kind of things and we are going to solve the specific problems of it. So just for now, you understand the DSA problem. The dynamic program is basically solving a wide range of problems into a very sub problems and a more efficient way over there. Okay, so in this you can see the dynamic programming is particularly useful in a situation where a problem can be divided into overlapping sub problem. So imagine there is a one problem where we will be getting a sub problems and we'll get a sub results, and the code will get repeated again and again. So there we can use the concept of iterative method and recursion method. So we'll make use of the iterative or a recursion method based on some conditions, based on some sub problems over there. So here we are going to make use of the memorization, DB tables actually, and arrays over here. So imagine we are going to look onto a main terminologies in dynamic programming, that's optimal substructure, overlapping, problems, memorization, recurrence relations, and initialization. Here the majorly we are going to work on with the bottom up or a top down approach here. So the dynamic programming can be implemented even in the iterative or the recursive, as I said, right? So iterative is basically a bottom up and approach, or if you want to talk about the TD method, that is a top down, that is going to be recursive, okay, approach. So basically we are going to follow up for the larger programs depend while based on some kind of a problems. Like imagine in dynamic programming we have a greedy method and dynamic programming. In dynamic programming, basically every stage we are going to take the decision here, okay. So based on the every stage we are going to take the decision and we are going to solve the sub problems over there. In greedy method there will be decision will be already fixed what you have to do, but in dynamic programming is there, right, we going to take the decision on the every stage of solving the program. That is where the things will come. So let's look up with one example to understand dynamic programming. So we'll understand with a very good example by taking a Fibonacci series over there. So the Fibonacci series, you have seen what is the example, what is the Fibonacci series. So the Fibonacci series is going to be getting something like this, right? So we will be getting something like Fibonacci of 5 pedestal. It will be 0 1 1, again 2 1 plus 2 it is going to be 3, again 3 plus 1 1 plus 2 it is going to be 3, 3 plus 2 is going to be 5, 5 plus 8 it is going to be 8, and it keeps on going it. That is basically we are going to call it as a Fibonacci series, right? So the dynamic program, let's see what is going to be the formula. So if I try to write the formula for the Fibonacci of n. So imagine if I wanted to find the n value is lesser than or equals to 1. So basically imagine if I wanted to search for a Fibonacci for the lesser than or equals to 1 value. So at that time I'm just going to simply return the value of that is 1 over here. Whatever the n value will be there, that will be getting returned over there, right? Or else what we are going to do, we are just going to return the Fibonacci of n minus 2 plus Fibonacci of n minus 1. So this is the major formula for the Fibonacci, right? This is going to be the formula for the Fibonacci, the Fibonacci of n minus 2 and the Fibonacci of n minus 1. So imagine if I try to draw the tree for us. So imagine I'm just going to draw the Fibonacci series for 5 here. So if I just tell here, again I'm just going to tell Fibonacci of 5 minus 2 is going to be 3 here. Again the Fibonacci of n minus 1, that is 5 minus 1 is going to be 4 here, right? Again let's imagine Fibonacci of 3. So 3 minus 2, the Fibonacci of 3 minus 2 will be Fibonacci of 1. Fibonacci of basically a 3 minus 1 will be Fibonacci of 2. If I do it here, it is going to be here as a Fibonacci of 2 minus 2 will be 0. Fibonacci of 2 minus 1 will be 1 over there, right? So this is going to be the Fibonacci of series here. And again let's imagine for here, so Fibonacci of 4 here. So in the Fibonacci of 4 we are going to get Fibonacci of 2, again we will be getting a Fibonacci of 3 according to the formula. Again for 2, again I need to write it, that is a Fibonacci of 0 and Fibonacci of 1. Again for the 3 here, again I need to just tell her as a Fibonacci of 3 minus 2 will be Fibonacci of 1 and Fibonacci of 2. Again for 2 I need to write it as a Fibonacci of 0 and a Fibonacci of 1 over here. So what is the time complexity here? Time complexity will be big O of 2 power n here. Okay, see here already we found the Fibonacci of 2, that is Fibonacci of 0 and 1. So again after founding it, again I am drawing this specificity. See the specific things which is repeated here. You can see these things are getting repeated more than one time. Here you can see the things are getting repeated, right? So here is in the recursive method. It is basically a recursive method which we have seen right now. Okay. So for that we can come up and follow with the another method, that is basically we can just see the another, that is a top down method over here. So let's understand the same problem with the top down method. So that's basically gives us a more better understanding for this. So imagine I have a Fibonacci of series. Imagine I'm just going to make use of the top down approach over here. Top down approach, basically previously we saw the recursive method, now we are going to look onto the iterative method. So it is basically an iterative method over here. So imagine we have specifically I'm just going to tell here. So we have an array here. So 0 1 2 3 4 5 and imagine 6 and 7 over here. So let's going to draw this array. Okay, so in this specific method I wanted to apply the Fibonacci's now. So let me take the color as like this. Okay. So I'm going to tell here as a Fibonacci's of n is equals to Fibonacci's of n plus 1. So I wanted to find the Fibonacci's of 5. It is going to be the 5 plus 1 calls. Okay. So basically it is going to be 6 calls for the Fibonacci's, and it is going to be the better than previously. That is going to be big O of n is going to be the time complexity, right? So now I wanted to find the specific top down using top down approach. Well, let's tell here as a Fibonacci's of 5 is there, right? I wanted to tell Fibonacci's of 5, Fibonacci's of f of n minus 2 plus Fibonacci's of n minus 1. So if I tell here as a Fibonacci's of 5 minus 2 plus Fibonacci's of 5 minus 1, it is going to be 5 minus 3 plus Fibonacci's of 5, that is 4. What is the Fibonacci's of f of 3 plus f of 4 is going to be there. So in this thing we'll understand, okay, the Fibonacci's of 1 is going to be 1 and the Fibonacci's of 0 is going to be 0 itself. Okay, so we need to find Fibonacci's of 3 plus Fibonacci's of 4 over here, right? This is going to be the Fibonacci's of 5 for it. Now let's do it for the first thing here. So let's do it for the Fibonacci's of 3 and Fibonacci's of 4 over there. Okay, so I wanted to do it for the Fibonacci's of 3. So let's imagine Fibonacci's, or let's try to do it for the first, that is Fibonacci's of 4 over here. Okay, so for that I'm going to tell 4 minus 2 will be Fibonacci's of f of 2 plus Fibonacci's of 4 minus 3, that is going to be Fibonacci's of 3. So what is the Fibonacci's of 2 here? What is going to be the value of Fibonacci's of 2? So Fibonacci's of 2 value is going to be 1 plus what is the Fibonacci's of value of 3 is going to be. So Fibonacci's value will be 3 here. So it is going to be Fibonacci's of 3, it is going to be 2 and that is going to be 3 here, right? So first let's understand what is the value of Fibonacci's of 0. So that is going to be 0. Fibonacci's of 1 will be 1 here. So let's find that is what is the Fibonacci's of 2. So it is going to be Fibonacci's of 2 minus 2 will be 0 plus Fibonacci's of 2 minus 1 will be 1 here, right? It is going to be 0 plus 1 here. So that is for the 2 also we are going to get the value that is 1 here. Okay, so when I want to, let's identify the Fibonacci's of 3. For the Fibonacci's of 3, I wanted to tell 3 minus 2, according to the formula 3 minus 2 will be Fibonacci's of 1 plus Fibonacci's of, again Fibonacci's of 3 minus 1 will be Fibonacci's of 2 here. So here rather than evaluating the Fibonacci's of 2 again into the same formula, this data we are going to collect it from the table, that is the array list here. So the Fibonacci's of 2 is already 1 here plus the Fibonacci's of 1 will be, again I am going to take it from the table, that is a 1, that is going to be 2 here. So I am going to just store it here as a 2. Now when I try to find the Fibonacci's of 4, as it is, you see, so the Fibonacci's of 2 was 1, I have copied here, plus Fibonacci's of 3, whatever from the data table is there, we have copied over here. So you can see that we have copied from the data table these values, okay, and we have just make it as a 3, that we are just getting as a 3 for the Fibonacci's of 4 here. And same for the Fibonacci's of 5, the Fibonacci's of 3 and Fibonacci's of 4. So again this data I will be copying from the table, that's why I have kept it as an empty. See, Fibonacci's of 3 is 2 here plus Fibonacci's of 4 is 3, that is going to be 2 plus 3, that is going to be 5 over here. So this is how this specific tabulation works. Okay, we are going to make use of the concept of tabulation. Okay, so that is how the specific iterative method. So in this method you can see, to solve this specific problem Fibonacci series, we are having a 2 approach, that is the specifically a recursive approach, and we are having a top down approach. So it is basically a recursive and it is an iterative method. So it depends which you are going to use it for your specific solving this specific problem. And here majorly we are going to already we have going to use the iterative method for a more better way, that is the bottom up approach. So we have the next that is the knapsack problems for the dynamic programming. There again we'll understand into the more better way. So for now this is the one example I have given you. So let's try to solve this Fibonacci series using a recursive method and the specific iterative method using the Java program over there. So let's open the specific Eclipse over there. So let's understand how it is going to be there. So I'm going to create the specific new Java class. So I'm going to mention here as the specific Fibo. I'm going to tell as a Fibonacci. So let's tell as a Fibo. This is going to be the memoization technique, basically a recursive method. Once I just click onto the specific finish, it has been created here. Okay, so let's see how the program is going to be there. So I'm going to import one specific package, that is import java.util.hashmap. We are going to make use of the hash map over there. So I'm going to initialize one specific hash map to it, that is a hash map that basically takes an integer and here we are going to make use of the memo, again memoization, right? Memo, I'm going to integer as a lower here. So now what I'm going to do here is I'm just going to create one specific method. That is the method. Let's understand with the code here. So we created a method that is a fib, okay, that takes an integer. It is basically, as I said, if it is lesser than or equals to 1, it returns the whatever the value will be there. So we are just check if the result is already computed. So we are just in the memo, we are just checking whether the result is already computed or not. If in the memo, what we are doing, the result is already computed, we are just going to store it inside the specific memo over there. If it is there, we are just going to get that specific value. If the result is not computed, basically what we are going to do, we are just going to apply the formula, that is Fibonacci of n-1 plus Fibonacci of n-2, right? And that after evaluating that specific formula in the memo, in the memoization, we are just going to put that specific value to it, and we are just going to get the specific result here. So here basically we are not applying the recursion here, we are using the memoization here. Okay, memo is basically does what? It stores in this specific, we are going to evaluate one result, we'll store it here. Again, if I wanted to evaluate the same result, I am not going to apply the formula, I'll get that data from the memoization. Okay, basically it is kind of a iterative method as well, but it can be a array method as well. Like it is going to be used to make use of the memoization over there. It basically returns the method. So now if I just try to do it for this specific scenario, so let's try to run the program for the Fibonacci series. I'm going to tell here as a create a specific Fibonacci method for the recursive. It is basically a recursive like memoization. Okay, in this case basically we'll get it from the data. So if I wanted to pass it, so if I just execute this program, so you'll be able to see the specific Fibonacci of 50 is some very big number, right? The largest Fibonacci number is there. So if I just do it for the 5, whatever the number will be there, that is going to be there. The Fibonacci of series of 5 is going to be 5. Okay, basically that's basically creates the element for us. Okay, this is how the specific Fibonacci occurs for the very iterative method over there. If I just do it for 10 over there, if I execute it here, so we'll be getting the element, you can see it is getting as a 55 is the Fibonacci series for 10 over there. Okay, so now coming back to the tabulation method, so let's create another method that is for the tabulation. So for a tabulation, the thing is going to be same here. So let's create a new program, Fibonacci tab. So I'm going to tell here as a F5B Fibonacci for tabulation method. Okay, so that is how the thing is going to be there. So whatever you want, you can just create it. So let's create a name called as Fibonacci for the iterative method for the tabulation. Okay, something. So I'm going to just create this specific okay, here what happening here, it is telling a Java name must start with or end with the blank. Okay, so now I'm going to click on to the finish. So we have created. So now we are going to see basically the iterative method here. So previously we saw the recursive method, now we are going to see the bottom up approach known as tabulation method, which already we've seen. So for that, let's try to import the specific thing, like let's create one method. That method is a Fibonacci method inside here. So basically what here it is going to do, it is going to take the Fibonacci fib and basically it gives the same thing basically here, right? If it is less than or equal to, it returns the n value, or else what we are going to create, we are creating a fib table array. We are just creating a 0th and first index will be 0 and 1, that's correct. We are going to run a loop, okay, for the method that is 2 to the specific number. We'll just iterate the data from the fifth number I-1, and we are just going to see from this specific table whatever the value. Imagine I wanted to access the indexing position fib of 0 here, directly I'll be accessing from the table. If I wanted to access the element fib of 1, you can see, which we have seen, if I wanted to access from the table, directly we are accessing. If I wanted to find f of 3, I'll go to the indexing position 3, I'll access the number, right? In the same way here also we are doing it. Basically this is going to be the iterative method. So everything is similar. The time complexity here only gets changed. The time complexity is going to be big O of 1 for the iterative, and for the rest of the thing it is going to be big O of n over there. Okay, that is going to be the major scenario over there. So now let's try to create the Fibonacci. So if I just want to print the element for here, so if I execute this append, so if I execute the program, so you'll be able to see the Fibonacci of whatever the number will be there, it is going to be coming as the same, but it is going to be little bit of a faster way over there. Okay, so that is how the things is going to be there. So basically only the thing you need to understand here is, so I'm going to paste this specific thing to you. So here the thing is basically this is the major thing. So what is here, right? So here you can see the iterative recursive method with memorization using a hash map stores the Fibonacci's value. So reduces the time complexity to big O of n here. Okay, by big O of n. but space complexity will be also big O of n. But in the iterative method, that is a bottom down approach, the big O time complexity will be big O of n and the space complexity will be big O of n over here. That is going to be the scenario over there. Okay, so the optimization can be happened basically in the if you optimize it, the space complexity is going to give it as a big O of 1 over there. Okay, that is going to be the optimization method to us. So this is all about the one small example for the dynamic programming. We are going to look on to the next session, the knapsack problems, like where actually a dynamic programming where we are going to use it in a more better way. So thank you guys, take care, bye bye.